Hello, mother lovers. It's time for stats. October 2020 is first. Let's go. Number one, then, we have some probability stuff. Looking at question A, then, write down any pair of mutually exclusive events. What that tells us is that they both can't happen at the same time. So if we took two events, A and B, and we thought about their intersection, the probability of that thing should be 0. What that means for our diagram, when we look at the two circles or any of the circles, they shouldn't have any overlaps, any intersection points. So we can see A and C would be good, yeah? A and C. You can get D and C as well. They don't cross over. So we'll call that C and D. And then we're also going to get B and D. No intersection between those as well. So B and D. Any of those will get some marks. Give them a circle. Big tick. And I move on. Next one then. We're told that the probability of B is 0.4. So that's the entire circle, yeah? And we know that all of these three bits should add up to 0.4. So what do we have? That's going to tell us that 0.24 plus the 0.7, or 0.07, plus P will be 0.4. I'm going to write this as 40 though, because then we can think like, okay, got 24, yeah? Got 7 here, 31 altogether. Need 40, so I've got 9 left to go. So it should be 0.09. Again, big circle, lovely, jubbly. Oh, now we're told then A and B are independent. What does that tell us? That again, we want the intersection. And it's what you first learn about with probability when you're in like GCSE. If you were flipping a coin, you'd do heads times heads to get 2 of them, yeah? Because you can just times them together because the events are independent. One coin flip does not affect the second coin flip. And this is what we're trying to say. We want that to be true. So we can work out the intersection, i.e. the two events both happening, by just timesing them together, the chance of them individually happening. And this works two ways. If this thing is true, then they are independent. Because that's just like, it doesn't mean anything. It's just a name. Do you know what I mean? It's a description of this certain type of thing happening. So we want to fill in this equation then. The intersection of the two is going to be the only bit of A and B that we're in both. Let's color in the A circle in red maybe. And the blue one in blue. Blue one in blue. The B circle in blue. The only bits in both then, that middle one, 0.24. And looking at the B then, it's all of those bits in it. So 0.24, well, we were told actually, weren't we? 0.4. That's for B. The A is a bit more complicated because we don't know all the bits. Let me rub these out. They're probably in the way actually. A bit easier without them. So the A circle then. Go away. How do we get rid of you? We do that. The A circle then is this bit, and this bit. So if we open some brackets up, we'll have that 0.24 and the 0.16. That makes a 0.4. And we're going to add on that Q that we have in there as well. Times that by the 0.4, and that should give us the 0.2. Lovely, jubbly. Now then we want to get Q. So don't expand the brackets. I think it's a bit easier if we just divide this across, yeah? 0.24, so 24 over 0.4, 40, should be, well, they're both multiples of 4. So let's divide them down. We're going to get 6 on 10. Divide that down, 3/5. Or I think 0.6 is what we want. So 0.6 equals 0.4 plus Q. So that's going to tell us that Q itself is equal to 0.2. Lovely, jubbly. Next bit then, we've got some conditional thing. Let's just circle that so it's easier to see. But we'll do it, say, no, we'll do it blue, it's all right. Yeah, let's look at this one then. So conditional, that little notation means the probability. What's the chance of B not happening if C's already happened? So we know we're caring about the world where C occurs. What's the chance of B not happening inside that world? We have a formula for this. We want to find the intersection of the two events divided by C. So the given that event, like we know that C is going to happen in that world, then what's the chance of this happening? The tricky bit then, what's this thing? We want B intersection, not C. So let's duplicate that, take it with us. There you go, over here I come. That's what we're looking for. The way to do this then, intersection, we need to satisfy both of these. So it's the and condition, yeah? Both of them need to be true. So that's going to tell us that we want to get 2 ticks. We're going to go around, and every single one of these values, we could ask the question, are you inside C? And are you not inside B? That would work. We can have a little shortcut though. We know we need to tick both boxes, so we might as well just go and look at the C circle, because anything that's outside C is definitely not going to be allowed. So our only question then is, are P and Q not in B? So if we ask the question, are they not in B? It fails there and succeeds there, because this is not in B, but this is in B. So the only bit we need is going to be that R. All make sense? Hopefully so. Let's keep going then. Let's put these ticks on there so you can see that, yeah, the only section we get is that is R, the only bit with 2 ticks, yeah. I won't do, I'm going to confuse myself there. Let's just keep going. R's on the top, and like we said for C was R plus the plus P for the entire circle. P that we found earlier, where was that? 0.09. So it's R plus 0.09. And that equals what they told us above, the 0.64. Beautiful. This thing you can do, yeah. No issues doing that. So let's do it quickly. We'll times this across, and we'll need to expand these brackets with the 0.64. So timesing that together, what do I get? 0.64 times 0.09. I get a number of 0.0576. And that's going to equal, we need to add on as well, R times 0.64. 0.64, lots of R, and so that equal to R. Beautiful. Let's subtract everything away, collect like terms. I'm going to have 0.36 lots of R equals 0.057 and a 6. And then divide by this 0.36, whack that down there, give it a division. What do we get if we do that sum? So divide that by 0.36, I get the lovely answer of 0.16. And that looks good to me. Let's check we are correct. So any of these, question number 1 needs to be on. Yep, they look good to me. 0.09, 0.09, 0.2. Yeah, 0.2 is good, and 0.16 is good as well. Okay, number 2 then. What have we got here? Some scatter graph. Describe the correlation. Well, it's going down, isn't it? So it's going to be negative. The variable on the x-axis is temperature. Okay, temp measured in degrees. Usually large data set knowledge. What's on the y-axis? Well, it's going to either be rainfall or it's going to be pressure. And what are the units of those things? We have millimeters and we have hectopascals. That's just from the data set, yeah, just stuff enough to have read. Stav then, on the next part, believes that there's a correlation between sunshine and humidity. He calculates the PMCC of these two variables for 30 days. He gets this value down here. Suggest a suitable test, or carry out a suitable test, to test his belief at 5%. State clearly your hypotheses and your critical value. Right. So hypothesis test, it's like a template. Same thing happens every time, yeah? We're going to have our null hypothesis. For correlation, that's always that there's no correlation. So i.e. rho is 0. The null, sometimes it'll specify. Up here, he believes that there is a correlation. And at no point has he said like which way you think it's going to be, yeah? So the null hypothesis, no, alternate hypothesis, is that this is not equal to 0. Just there is a change. He hasn't suggested a direction for that change. Next thing then, we get the observation. That's that 377 number, yeah, or 377. So some R value is negative 0.377. And what we want to find then, so one way that we can view this is if we look at all the distributions, well, of the distribution of all the different possible correlations. So it's going to look something like this, kind of symmetrical. And the end down here will be -1, this end will be 1, and this will be 0 in the middle. We want to find some number, some R0, or we'll call it rho 0 maybe, that on the left-hand side of that is exactly 5% in general. But with it being rho, it's 2.5, yeah? So there's going to be some other number the other end. Same idea, we'll call this like rho 1. And the 5% has been split. So each one of these is 2.5%. And our goal then is to see basically whether the observation we have is inside this blue region or not inside this blue region. Because if we took just a load of samples, load of samples, and you pick 2 variables from, like loads and loads of variables, pick 2 of them, and compare the things on a scatter graph. Look at the correlation. This is just the display or distribution of all the ones we got. So our goal is to see the things that we're looking at right now, are they really unlikely just randomly? Or is there a big chance of them just happening in general? So that's our goal. What we have then to do is use our number and use the books on the left. We're told 5%. That gets split into 2.5s, yeah? So let's go to this column on the left. We have 0.025. And we have another column, sample size on the right. Our sample size was 30, yeah? So let's go down to the row with a 30 in sample size. And we wanted 2.5%. So the column with a 0.025, going down, what intersection point do we get there? We get a number of 0.3610. So that's our row 0.3610. This is the, I suppose they're the same value, so let's just call it like row 0 and row 0. But the one on the left is the negative. And then our goal is, yeah, where's our number? Well, we had 377, yeah? So that's in here somewhere. Negative, I know it's negative in it, but this graph is symmetrical, so like the negatives don't make any difference really. I mean, it's going to be the same thing if you're on the left or the right. But yeah, we're in the blue zone. That means we're a bit of a weirdo. There's very low chance of this happening, less than a 2.5% chance of this just randomly happening. That's a bit odd, isn't it? So what we have is basically the idea that what we originally thought is odd. It's wrong. It's not correct. There is sufficient evidence to believe, or not to believe, to reject H0. That's the general idea. Why is, if we do the maths of it, we had the observation, the negative 0.377. If we look at the size of that number, so again, ignore the negatives, it's bigger than what we got from the book, the 0.361. Again, size of that, but negatives don't matter too much. So our observation is bigger than the kind of expected weirdness threshold value, what we get from the book. This is like 5% chance, or 2.5% chance, sorry, you have this correlation, just randomly. We were more extreme than that, more strange. So we should change our mind that nothing's going on, because this is just so unlikely that it randomly shouldn't happen. Always try and put this in context. So how I'd write this here, like there's sufficient evidence to suggest that there is a correlation between sunshine and humidity. I'd use like the full bits, do you mean? But yeah, that should be good. Don't say negative here because we haven't been investigating negative. We've been investigating just correlation in general. So we haven't proved negative. We've just proved that there's not one of these. Lovely. Hopefully that's all good. Part D then. What do we get? On a random day at Heathrow, the humidity was 97. Comment on the number of hours of sunshine you'd expect on that day. Give a reason. Well, we just showed negative correlation. Well, I suppose we did. Well, this was a negative side, so I suppose we showed we're in this gap. There is a negative correlation, really. You don't need to mention in this bit. But in that regard, then, high humidity would be low hours of sunshine, yeah? Yeah. Lovely. See it from the graph, too, innit? One goes up, one goes down. 97 is pretty high, so this should be quite low down. Lovely. Looks good to me. Let's keep going. What have we got now? 27 people completing a puzzle. Time taken for each of them was recorded. Here we've got some box and whistle plots. Find the range. Well, that's going to be the top value, Q4, and the bottom value, Q0. And what the difference between those two. What numbers are these? I get a 7 on the left. That's 68. Looks 68 to me. So 68. Take away 7. I get 61 left over. Interquartile range. Same idea, but for not Q0 and Q4, but Q1 and Q3. So what are they? They are 14 and they are 25. 25 take 14 gives me 11. That's all nice and straightforward, yeah. For these now then, find the mean. So for the mean, we want to add them all up, divide by how many there are. So 607.5 divided by n, there's 27 of them in there. Let's do that quickly then. 607.5 divided by 27 is 22.5. Now the standard deviation. So sigma, we need to do the mean of the squares and then the square of the mean. Write that a bit more. We're going to have the sum of the squares over n, so the average square. Take away the square of the square of the mean, the thing we just found about that, 22.5, yeah. You can put that in there if you like. No, we'll leave that, and then we'll do, now this row, we have all the values, yeah. So this one is going to be 17623.25 over n, which was 27. Take away the thing we just found, 22.5, all squared. If you got the first part wrong, but then you did this net plot correct just with your wrong answer, you will still get all the marks, so don't worry too much. Let's plug this in, see what we get. That's too many fractions. 17623.25 over 27. And we're going to take away 22.5, square that. We'll get quite a big number. What do we get? 146. Obviously, that's wrong, yeah? Look at that. Wrong, in it. What we've done wrong is we've not square rooted. So the formula we've done is for the variance. Standard deviation, square root, all of this stuff. So let's get rid of that number. Square root the answer we get. And it gives us an answer of 12.1. Which looks pretty good. Circle these as well. Always double check. The answer you get out, does it seem realistic? 140 odd? No. 12? Yes. So a little sanity check, always useful. What have we got now? Adam and Beth complete the puzzle in A minutes and B minutes respectively. A is bigger than B. So Beth's fast, Adam's slow. When the times are included with the date of the other 27 people, the median time increases. Okay, what does that tell us? Well, if you're going to drag the median up, let's think about A and B. We have B is bigger than A. So on a number line, the median can either sit on the left of B, in between the two, or on the right. If we're in between, one below, one above, we're not going to move the median, yeah? It's going to stay where it is. If we're like this, these two are smaller, so the median like moves to the left. If you're like lining all the numbers up, it moves to the left by one. So this will drag it down. But that side drags it up. So it moves towards them basically. If it's in the middle, it doesn't move obviously. But like whichever side it on moves towards these values. We want to increase it. So we need to drag it to the right. So we want to make sure our median is less than these values. Next with them, the mean doesn't change. So if you're if you're combining samples and you keep the mean the same, those two samples are the same, have to have the same mean. So these two values, I know it's a very small sample, just two of them, but we need their mean when we add them together and divide them by 2 to have the same mean that we had above. Doing that then, A plus B must equal, well, the mean above was 22.5 times by 2, we get 45. So two numbers, add up to 45, and they're both bigger than the median. What was the median? Let's go up here. 20, yeah. Let's put that in. So we can come down here, fill that in. We know that this is going to equal to 20. And right then, two things we have now. Both numbers bigger than 20. Add up to 45. What things are possible? Well, we can have 21, 24. Or we could have 22 and 23. These need to be ordered. So that's going to be B. The first one is smaller than A, the second one. That looks good to me. Lovely, jubbly. Right, next one. Suggest a possible value for A and... Oh, sorry, we've done that one, haven't we? Without carrying out any further calculations, explain why standard deviation of all 29 times will be lower. So what is standard deviation? It's not exactly this, but it's effectively, if we were to like look at all these things, you've got your mean somewhere, wherever our mean was it 22.5? In here somewhere. It's looking at the average distances away. It's not really. It's actually working out, like say you had 30. You are going to draw a big square and you work out the average size of all these squares, like all the values, how big are all these squares away from where we are. And we work at the average size of those and then square root it. Why do that and not just work out the average distance? It's just quicker on a computer. That's it. Only reason. So we do this way around. And what this represents then, yeah, roughly is average distance in terms of the units, like minutes here. We are away from the mean. So by adding in these two values, they're very close to the mean, yeah? So on average, our values are going to be closer to the mean. So that should reduce the standard deviation. So you say both of them are close to the mean, both close to mean. So that's going to imply that the standard deviation decreases. Decreases. On these sort of ones, these explain questions, let's just look at the mark scheme. Exactly what words have they used? Yeah, that's what the mark scheme is. It's a guide for how to answer the questions. So on these explain ones, just see what they want. You say this thing, I say this thing. I get the marks, we're both happy. Lovely. What does it say then? Both values will be less than one standard deviation from the mean, and so the standard deviation of all 29 values will be smaller. Looks good, yeah? Wonderful. It's only one mark, so we've definitely ticked the box, haven't we? You understand that. They'll understand that you know what's going on because you said that. Let's keep going. Number 4 then. Oh, distribution. Some random one. Find the value of k. So with a distribution, what we know is the sum of all of these probabilities, like d is equal to d, needs to equal 1 when we go over every single value of little d. What that means then, add all these bastards up. So number 4 then, we've got some distribution. Let's have a look what to do. So the one thing to think about, when we have a distribution, this is fact is always true. If we add them all up, so every single value of little d, they add up to give us 1. So what that means, yeah, just add them all up. So we're going to have a tenth of k. I'm going to take out a factor of 1 on 10, yeah, k on 10. We've got 1 a lot there. I've got half of them there. A third in that bit. There's a quarter and a fifth as well. And they should all add up to 1. So doing that, what is that big bracket going to be? 1 plus a half plus a third. 1 plus 1/2. And then let's get out of that fraction. Plus 1/3 plus 1 on 4 plus 1 on 5. We get the lovely answer of, this is going to be 137 on 60. So we have 137 times that by the 10 on the bottom, 600. Lots of k is equal to 1. And get rid of that little dash in the middle. Pop. And now let's get k by itself. Let's times by this, well, divide by this weird fraction, yeah. 600 on 137. It's always nice when stuff pops out that looks the same, and that's good. The random variables d1 and d2 are independent and each have the same distribution as d. So independent is going to tell us a thing here, whether we need it or not, different question. But generally, it tells us that the intersection, let's do this way around. So d1 intersection d2 is the same as just times in their properties together, yeah. Same as what we had earlier on. And that's good. Whether we need it here, different question, but that's a fact that's always true. So it's probably worth writing down, if you see that thing. Here then, we want to find out what's the chance of them summing up to 80. How can we do that looking at these values? Well, the biggest we can get is 50. So we need at least 30 to get there. So we can either get 30 and 50, or we can get 40 and 40. Let's write that 5 a bit better. 5. One thing to think about though, we could also get 50 or 30. Like 50, 30. Do the other way around. They should have the same chance. D1 and D2 are identical. There's no difference in them. So these things, they have the same value, each one. The chance of each one happening is the same. So you can really just think about the fact, oh, it's 2 times that thing, and just get rid of that bit. But that's good. So these are the possible cases to look at. And let's think about that then. So what is the chance of us having these values of 30? Let's do these different rows of 40 and of 50. But we get them from above, don't we? We've got this k value. We've got k on 10, and we k on 30, 40, and 50. Nice and straightforward. I want to keep everything in terms of k. The actual value of k is not so nice, is it? So that's good. And the cases we want then, if we think about doing 30 and 50, we're just going to times them together. Because we want them both to happen, and they're independent. So we can just times them together. So what we're going to get, for this one, it's going to be k squared, yeah, on the top, over 30 times by 50 on the bottom. Very similar then in it for 40 and 40. we're going to have k squared over 40 squared. And like I said, we have two different ways that we can get to this. So we need to double that one, 2, and then add it all together, yeah? So we're going to have 2 times k squared on 30 times 50 plus k squared on 40 squared. This then is good. Let's add this all up. What do we get? So 2 times 1 over 30 times 50 plus 1 on 40 squared. We're going to get 47 k squared on 24,000. Let's now plug in the value of k squared. So times in this by 600 over 137. Lots of k. Lots of k. Oh, all squared. We get, oh, not a very nice number. Should we get this number? No. Yes. Yes, we should. We should indeed. 0.03756. I'll always do 4 figs for stats. You don't need to. But I always say, like, if in doubt, do 4, basically. So the numbers here are, yeah, often going to be horrible. So I wouldn't doubt yourself, like, the numbers are so bad. Even though it kind of, you naturally want to, don't you? But they will often just be horrendous. This is looking good. Last bit of this, then, is a little bit strange. What I'm going to do is just shrink this up out the way so we can still see everything. I will at some point, like when I post this, I will at some point like make this bigger and put the actual answers for part C on the next page. Do you mean? So what's going on? We now have a single observation, so not interested in D1 and D2 anymore. The value D is the common difference of an arithmetic sequence. The first 4 terms are measured in angles. The angles measured in degrees of a quadrilateral. So what do we know? The first 4 terms: A plus D, A plus 2D, A plus 3D, yeah? If we add those all up, because it's a quadrilateral, they will make 360. Let's collect some like terms. What do we get? We've got 4 A's and 10 lots of D. That gives me 360. And I will just half all that to make it a little bit easier. So 2A plus 5 lots of D equals 180. Lovely. Am I good there? No, sorry, not 5 Ds. It's 6. It's 6 to begin with, and then it goes down to 3. 6 and then 3. There we go. We can have a little think about this. So we may as well make D positive. Why? Well, let's say we had 10. These went out to 360 for a sec. But let's say we had 10, 20, 30, 40. And that would start then. A is 10, D is 10, and we add up all the way. That's exactly the same as having A is 40, D is minus 10, and it's going down. So there's some relationship, because we have a fixed sum, there's some relationship between A and D, where like if you have, there's one value for A and then like a negative value for D, and then the positive version of that is a different value of A. So we may as well just look at this side. I think that's a phrase of like without loss of generality. I'm still kind of relearning it. It's been a while since I've been there. Do you know what I mean? So I think that's what that's called. And like you can look at 2 different cases, and just one of the cases works the other way around. Do you know what I mean? It doesn't change anything really. If I'm wrong there, someone correct me, but I think that's what it means. So doing that, what that tells us that the first term, A, is the smallest, which is nice. And we want to make sure that it's bigger than 50. Smallest angle, bigger than 50. So A is bigger than 50. That's good, yeah? That looks good to me. Let's write some things down then. If we know A is bigger than 50, 2A is bigger than 100. So these 3 Ds, they can only go up most to 80. Any bigger, and we know we're definitely over 180, aren't we? Because these bits are at least 100, so they can't be more than 80. So that's less than 80. Divide that over them, what do we get? 80 on 3 is roughly 26, isn't it? 26 and a third, 2/3, something like that. Let's find out. 86 divided by 3. 26 and 2/3. Not that we need the 2/3 here, because the main bit's going to be that is smaller than 30. Because we can only be 10, 20, 30, 40, or 50. But that's less than 30. It's also, you want to say really like it's bigger. It's bigger than 20 as well, do you mean? But what the main goal of that really, like why we've done this, 10 then can either be 10, D, sorry, can either be 10 or 20. which looks good. So exact probability of doing that. What that really means is the probability that D is either 10 or 20. With it being or, add up the probabilities. So I should have K on 10 plus K on 20. If we do this, what is this? This is 2 over 20, yeah. So it's 3 over 20 altogether. 3K on 20. So if I take my K number, which was 600 on the 137, times it by 320, and it's going to give us a value of 90 on 137. As decimals, 0.6569. Does that look good to me? 90 on 137 is what they've got in the book. Beautiful. All sounds good. I'm just going to go to the toilet, and then we'll do, is it the last question? Yeah, last question, this one. 135. Oh. Right then, last question. Number 5. What have we got? Blah, blah, blah. Claims about the time, modeled by a normal distribution, mean of 10, deviation of 4. So let's call that T, and it's going to be distributed normally with a mean of 10, standard deviation of 4. So 4 squared goes in there. Make that a better 2. That's a good 2, isn't it? Oh, lovely. Right then. Find the probability that time spent is more than 50 minutes. Probability T is more than 15. From this then, calculators, yeah. We will put in, just in case you're not sure on how to do these, we want the normal one. We can put in our stuff. The mean was 10. Standard deviation was 4. And we want to be above 15. Change that to above. What value do we get? 0. Oh, what have I done? Stretch you back out. 0.1056. Does that look good at the mark scheme? Does indeed. Lovely. They've rounded it to 106, but yeah, that's fine. Some patients complain that the mean time the doctor spends with them is more than 10 minutes. Takes a random sample of 20 patients, finds the mean time is 11.5. Okay, so on this one, yeah, it's a sample mean, not the one distribution itself. This is one person. When we get this value out, probably of one person taking more than 15 minutes. When we're doing a sample mean, we have the bar on the top to represent mean as always, distributed, and we're going to take the same mean that we had earlier, so the 10, but now that sigma squared was 4 squared, yeah? We divide that by the sample size, which was 20. The reason we do that, as you just add more people to the sample, so the average distance away from the mean should decrease, yeah? Add loads of them in, and you get closer to the average. It's a bit beyond the kind of course to think about why that happens all the time, like the maths of it, I think, but maybe not beyond what you can understand. So this is good. We want to change it via that then. Same idea though. Probability that it's going to be, let's see, mean was 15. Okay, we're testing. We're testing. So what do we get for our hypothesis test? 5% evidence to support their claim. more than 10 minutes. More than 10 minutes. So, null hypothesis is going to be that the mean is equal to 10, because that's what we thought beforehand. The null hypothesis, she's thinking it's going to get bigger, more than 10 minutes. We have our alpha of 5%, significance level, 0.05. And we had a sample, like an observation of 11.5. So we want to find the chance that the sample mean that we got is bigger than the 11.5. So let's go to our calculator. Mean is still 10, that's good. What do we need for this? What do we need for this then? So let's move this out of the way a little bit. We have 4 squared over 16. What does that give us? 4 squared over 16. 4 squared over 20. So that's 16 over 20, 0.8, yeah? 0.8. We want to be bigger than 11.5. So bigger than 11.5. Let's press recalculate, and I get a number of 0.0304. That number is smaller than 0.05, the alpha value that we had from above. So what's that telling us? This means there's a 3% chance, roughly, 3.04% chance of, we have a normal average of 10 minutes. We've got 20 people doing it, and we've got their average of 11.5. There's a 3% chance of that being either 11.5 or more extreme, like bigger than, so like further away from the 10. Same idea as when we did this one earlier, wherever it was. Where have I drawn that little shape? Down here. Yeah, this same idea, do you mean? Same thing has happened, exactly the same thing. Just these numbers have slightly changed. This is now the 10, and the thickness of this has changed as well. But process is the same idea. Which group are we in? What we have observed is very unlikely to just randomly happen, so it changes our mind. Because again, we're in that same kind of rejection group, rejection H0. What we actually observed was very unlikely. This is our observation, and this is our kind of threshold. Difference then, here we're talking about probabilities. In the other version, we were talking about the correlations. How you want to compare them is up to you. Whether you want to find probabilities and compare them that way, or find the actual values. We could have done the inverse normal here, taking this 11.5 in, and sorry, other way around. We're taking the 0.5% or the 5%, and we'll get at like what number that is, and compare these numbers and see, is it bigger than smaller or smaller than 11.5? And we would see, in this case, it's closer to the threshold, will be closer to the mean. It'd be something like 11. So the observation was more extreme than the threshold. All good, yeah? Hope that makes sense. From here, then it's that statement at the end, yeah? Are we going to reject or accept? So from this one, we're going to reject H0. The observation we had a 3% chance of just happening. Our threshold for weirdness was 5%. 3% is more weird than 5%. So we reject our original thought. What we observed is too strange to think that we were originally right. I flipped a coin 10 times. I've got 9 heads. And I'm like, nah, man. I don't trust that coin's fair anymore. So I get rid of it. Beautiful. Next bit then. They're doing some more faff. What have we got? Claims that a dentist time, the time spent with a dentist during a routine appointment, multiplied by this distribution. So you spend twice as much time waiting than you do seeing them. Using this model, find the probability that a routine appointment takes less than 2 minutes. Okay, this is just calculate again, yeah. I will do them all on here just to show you. So make that so you can see. We have a mean of 5. This is going to be 3.5 squared. I don't think I can do squares in here. So what number actually is that? 3.5 squares. 12.25. I think you can do them on your calculator, can't you? So it's not an issue for you. And what we're looking for, less than 2 minutes. So below 2. Click the below button. Click calculate. We get a value of 0.4033. Make that about 3. Does that look good? No. What have I done wrong here? I didn't change my. Oh, that's standard deviation. Yeah, ignore me. This should actually be, because my number's above, right then. Yep, sorry. My number up here, where we got this number, I thought my value in here should have been the variance. It should have actually been a standard deviation. So I've used a 16, and I should have used a. Yeah, what we did, we've done 4 squared over 20. to get us 0.8. That is actually the variance. So I want to square root 0.8. That gives me a number of 0.8944. Oh, I'll get rid of that 4 this done. 0.8944. Get rid of the 9. 0.8944. Is that right? Yeah, that's good. So just to clarify, this is sigma squared. So that tells us that sigma should be the square of that thing, yeah? 4 over root 20. If we do that, the number we get, just to double check, 4 over the square root of 20. Yep, 0.8944. So as I go through, the only thing that changes about what we've done is this actual number that we've got out of here. So if you do notice that you've made a mistake by doing that in the exam, you don't need to cross everything out. It's just this one from the observation. So we're going to go through, press recalculate. It needs to be now, this was above 11.5, yeah? So go back to the above one. The mean again was going to go back up to 10, sorry. Press calculate, and we get a different value then. So that 304 became 468. Thankfully, here, we were still on the same side, yeah? The comparison we did is still valid. It's the same comparison. So nothing else changes. It's just that actual value. Like, where does that come from? It's from the books. I think I wrote it over here. Yeah, that comes from this thing and it from the table. So that's all good. Sorry about that little slip up. I will try my best not to do them. If it's too big, I'll edit it out. But if it's just that, then I hope that's not too bad. So yeah, that changes what's going on here. Let's just re-clarify then. We want to use the mean of 5 and a standard deviation of 3.5. And we were looking for the phrasing of it. Find the probability that a routine appointment with a dentist takes less than 2 minutes. It's probability that T is less than 2. So I'm going to be below 2. Yeah, we've got that on there. That's good. Plug that in. 0.1957. Does that match them? Does indeed. So blue, circle that. Big tick. Lovely. Down here then, conditional stuff. So we want to find the intersection on the top. So T is less than 2. Intersection, T is bigger than 0. And on the bottom then is, what is the second one? So T is bigger than 0. That looks good. Thinking about the top then, how can we rewrite that? Well, we want to be less than 2 and bigger than 0. So less than 0 is less than the thing we're looking for, T, which is less than 2. Probability of that, and then probability of T being greater than 0 on the bottom. So we want the like between ranges, yeah? What's our lower bound? 0. What's our upper bound? 2. Plug that in. What do we get? 0.1191. If we do just above, do that from 0, what do we get? 92. So 0.9234. Let's do that sum, see what we get on the other side. 0.1191 over 0.9234. And we get a value of 0.12. What's 8979? There's loads of I things now, so it's 9, yeah, 90 if you're going 4 different places. Rounds up and up and up. Does that look good? Oh, it looks very good. Spot on. Next one then. Hence explain why this normal distribution may not be a good model for T. Well, yes. So one thing to spot. This thing. Let's put it in blue. Here. T bigger than 0. What are we actually talking about is the wait time at the dentist, yeah? I don't know of any dentists that serve me before I arrive at the dentist. If I'm walking to the dentist, I don't have them like FaceTiming me like, "Oi, what's on? Teeth hurting, yeah? I'll help." No, they wait until you get there checked in. So this is kind of like, it should be 100%, shouldn't it? But it's actually 92%. So this dentist is claiming that like what, 7 and 2/3% of the people get seen before they arrive. I don't think that's quite true. So why is that not a good model? Because people cannot be seen before they arrive. Yeah, makes sense. Big tick. I'll write this down. Cannot be seen before arriving. So that's it in terms of words. What does that mean? It's the same as saying really like T cannot. So T has to be bigger than or equal to 0, yeah? It probably has to be bigger than 0. Walk in, you just get seen straight away. Just walk in the dentist straight under the seat, Jimmy. I'm here, boys. I'm ready. Right. What have we got for the next one? She believes she cannot do it in less than 2 minutes. Not surprised. She suggests that the health centre should use a refined model, only including bigger than 2 minutes. Yes. Find the median time for a routine appointment. Use this new model, given your answer correct to one place. Okay. So what we want to find, we want the probability that the distribution of the times, some random value we get, some random person that comes in, we want to find a time. We can do greater than or less than. Let's find less than. Let's do greater than. It's a bit easier, I think, with what's going to happen. So that we are longer than that time, given that we are at least 2 minutes, yeah, so only considering the people that arrive after 2 or take longer than 2 minutes to wait. What time is the middle time? So what time is there half a chance that we take longer than it for? Exactly the same for a negative, yeah? Makes sense because it's just a half, yeah? What's the middle number? Only looking at the numbers that are bigger than 2, the times waiting that are bigger than 2. What's the middle number? What number has to be bigger than to be exactly half the numbers? Let's do the formula then for the left, the conditional. We want to be the intersection. So t is bigger than our time. I'm going to call this like t1 maybe. And intersection, we're bigger than 2. And over then, probably it's bigger than 2. Let's move that all left a little bit. So this is good. We know from the condition that we're bigger than 2. That's the only thing we're looking at, yeah? All the times bigger than 2. So this top row, where we want to be both bigger than our median time and bigger than 2, that's just the same as being bigger than the median time. Because we've got to define all times are bigger than 2. So by definition, it is also bigger than 2. Some of these, like, you think, oh, how are you going to know that? You just got to use a bit of common sense. There's not going to be like a definitive list of all the ways that these questions are going to be asked. Sometimes it's just a bit of common sense. We're only looking at times bigger than 2. So this one must be bigger than 2. So this thing is just the same as just itself. From here then, let's fill in all the values we have. Like I say, this is still equal to 0.5 from above. We're looking for that t1, so let's get that thing by itself. T is bigger than t1, and it's going to be a half that 0.5 of this probability. That's what we found above somewhere. Yeah, down here, this 1957. So it's a half of that number, 0.1957. As we do that then, what do we get? So 0.5 times 0.1957. We get 9785, but we're going to just round that up a little bit. So 0.0979 looks good to me. So again, what's that representing? We have some new distribution now. Well, yeah, we're capped at 2, so we can draw a line at 2. But then we've still got some, like, I don't know what shape it will be. It's going to go off and then go down to 0. And this whole thing, what is this? There's t in it. This whole thing will again have an error of 1 because it's a probability distribution. And we've basically found that we want to be bigger than some number, and it should have a very small, oh no, tell a lie, this has got the rest of it. So if we to draw it all out, it's going to stop here and be like 9%, yeah. But it's the same as then, it's like that number, if we flip all these bits around that were like invalid and like distribute them over the rest of the shape, what was splitting this into like 9% and 91% now splits it 50-50 because of all this kind of like excess bit that was invalid before being shared over. This number that was 9%, 91% is now the median number, so slap bang in the middle. This is looking good. Double check I'm right. I don't think I'm right. What have I done wrong? T bigger than 2. T bigger than 2. Sorry, that's t less than 2. So it should have been 1 minus this thing. 1 minus that. Sorry about that. Move that over a little bit. 1 minus that. 1 minus that number. So let's just slightly change the things we did. 1, take away that. What do I get? So it's not 97 stuff. It's going to be 4022. The way I explain this is the same. The numbers have changed, obviously. It's now going to be like it was 40% and 60%, and now it's 50-50. But same explanation. This is good then. So that is the probability for us on our original one to be bigger than 40. So or bigger than 40, having like 40% on this side. So what we want to do, we want to think about doing the inverse normal. So let's go and get our inverse normal calculator. And we know we want to be, we have a mean. I'm always going to do the inverse normal, the inverse standard normal. So we have an area we want to find is 4022, 0. That's 0.4022. And let's just plug that in. Or should we? No, I think we'll do it the way that you do it. So we can just do the mean and the standard deviation here. So what was our mean? Our mean is still 10. Our standard deviation is still 3.5. Oh, sorry, our mean is 5. Mean is 5. Doing that then, what number need to be above 5.8668? So yeah, from the calculator, that's going to tell us that T1 is equal to 5.8668. Lovely jubbly. Is that the last one? Yes, it is. I'm going to take a little break while this one edits and loads and stuff, do you know what I mean, and processes. The other ones, I'm just going to keep doing this now. I don't know what time I'll finish whenever I get tired and bored. Probably, like, I'm thinking in my head, like 2 a.m. is when I'm going to stop. So yeah, enjoy. How many you want, I don't know how many I'll do today. I'm going to do at least 4, hopefully if not more than that. But the rest of them I will just do tomorrow. So by the time you go to bed tomorrow or wake up on Tuesday, they'll all be out, yeah. Happy days. Thank you very much. Enjoy. See you later. Hello, Marvel lovers. Back again. Stats again. October 2021 this time. So let's get going. We want one disadvantage of using quota compared with simple random sampling. Well, it's not random. Nice and simple. Another one we could say for this is it's biased, or it is not. We can't infer from it, so there's no inference. No inference. Any of those would be fine. Next bit then, in a university, 8% of students are members of university dance club. Random sample of 36 is taken from the entire university. X represents the number of those students who are members of the dance club. Using a supermodel for X, find the probability that X is 4. So we want our binomial calculator. We want to get the PDF. So this being equals is PDF, yeah? So let's look at this stuff. Probability, what do we have? 8%. So getting that up. What we're going to have, 0.08 for that one. Oh, without those bits at the front though. 0.08. Number of trials we're doing, 36, isn't it? 36 people. Looks good. And successes we wanted was 4. So then, calculate. What do we get? Top row from that, the equal, 0.16739. Does that look good to me? Yep, looks spot on. Let's circle the answers we've had so far. All of them in it are good. That one looks nice. Greater than or equal to 7. Change this 4 to a 7. What do we get from this one then? So greater than or equal to 7 is that bottom row with all the 2's. 0.2224. There should be a 0 before those 2's though. Does that look good? It does. Yep, looks very good. If your calculator can only do the CDF, so just a note then, the CDF, let's do this in blue, always means that probably is X, well in this case, yeah, X is less than or equal to a number. So just try and make sure that when you do the 1 minus, so I think this one is, yeah, X is bigger than 7, or equal to 7. It's the same as 1 minus, probably of anything else happening. So if you want it to be less than or equal to, you just have to make sure that all the numbers are included between these two ranges. So this one is everything 7 or bigger. So if we want something and lower, be 6, yeah. Can't be 7, because we've already got the 7 over there. Can't be 5, because then where's the 6 going? So had to be 6. And that'd be the same. Then you like plug that in, you'd end up with like 76, yeah. 7776 should pop out just for that thing. One take away it, we'll give you all our 2's. Oh, sorry, 9 in front of that, yeah. 9 and then all the 7's. Lovely. Next one then. Only 40% of the university dance club members can dance the tango. Find the probability that a student is a member of the university dance club and can dance the tango. So we want probability that they can do the tango, given that they're part of the dance club. So in that case, we want the, given that, because we know that we're only looking at the dance members, yeah. So what's the chance of them tangoing, given that they can dance? So intersection on the top, dancing on the bottom. So intersection, what have we been taught? 40% can dance tango, but of the dance club members. So these should be independent, or we want to work out the percentage in it. So it's going to be 40% of the 8% that are actually in the club, divided by how many are actually in the club. So next bit then, only 40% of the university dance club members can dance the tango. Find the probability that a student is a member of the university dance club and can dance the tango. So looking at that, what we can say, we want to have the 8% that members of the dance club and the 40% that are part of, well, that can do the tango, yeah. So working that out, what number do we get? 0.4 times 0.08 gives us an answer of 0.032. Is that good? Yes, it is. So what that's saying is there's like 3%, 3.2% of the total university students can do the tango, because we knew 8% of them could dance or in dance club. 40% of those can do the tango. So we've worked out, yeah, together, like thinking about that way around. This 40% is the probability that you can do the tango if you already can dance. It's not just tango. Do you know what I mean? This is what we're saying. This is just tango, basically. So we're kind of reverse formulation to get this thing out. And this bit obviously is being the probability that you can dance. So this bit on this side is probably that you can just do the tango. And you can get like the rearrangement of these sort of bits. So lovely, that looks good. A random sample of 50 students is taken from the university. Find the probability that fewer than 3 of those students are members of the university dance club and can dance the tango. So what we want in 50 people, and we're going to basically use the probability that we've just found. So yeah, because it's from the entire university, that is the 3.2%. So what have we got? Some binomial distribution. Let's call it y. Why not? And it's going to have 50 as the number of trials. The percentage is what probability? 0.032 for the 3.2% chance that a random student from the entire university can do the tango. So what do we want to find? We want fewer than 3. Fewer than 3. If you're doing the CDF stuff, this is going to be y, therefore is less than or equal to 2. Yeah, anything less than 3. Same answers. These are all the same things. We can really go and put this like over here. It means the same thing. Let's do that. There we go. No. Come on. There we go. Lovely. Let's use our calculator then. Change this value. Success now is 0.032. Number of trials has changed to 50. And the number we're interested in, we could do 2 or 3. We'll do 2 just from the question. Just from the CDF, just so they can see it straight away. So less than or equal to 2. We have that number of, that middle one there, 78508. Does that look good? Looks very good. Spot on. Number 1 done. Number 2 on the way. Mark took a random sample of 16 students. Okay, that's our sample size. He's got the length of their names, first and last name. So his results are shown in the scatter diagram on the next page. So X is last, Y is first. This is last, this is first. Initial observations, looks like it's kind of going down here. Not too much, but it's definitely going down. It kind of, let's do something like that to keep a mark of it. Nice, that's good. Okay, it's going down, then it negative to describe that correlation. Spot on. Mark suggests that parents with long last names tend to give their children shorter first names. Comment on Mark's suggestion, giving a reason for your answer. So yeah, it looks pretty good, doesn't it? Like, you can see that fits. The longer we make the last name, generally the shorter the first name is becoming. How do we phrase that then? Well, in these ones, just look at the mark scheme. What they're actually saying. So the words they've actually used, his suggestion is compatible because it's negative correlation. So compatible because negative correlation. And these are like the underlined words, do you mean, in the mark scheme? So on these like explain ones or comment ones, just see what they want. See what they say, do you mean? Easy peasy. Nice, what have we got then? We have the actual observations. Okay, use your calculator to find this value. So nice, I don't have a calculator like here, so we're to go for that. But we can just see what the mark scheme says. We are going to get 0.4259 for that one. Lovely. Nice, let's keep going. Test whether or not there is evidence of negative correlation between the number of letters in the last name and in the first name. Okay, so hypothesis test. We're always going to have a null hypothesis, which for correlation is that there's no correlation. Our alternate is that there will be. Do we have a direction? Yes, negative. So it should be less than 0. We have our significance level, 5%, so 0.05. And what we have is that, yeah, it's a one-directional test. So we can kind of visualize it. Let's draw out some distribution. This is going to be our correlation. And we're going to have some shape then that does something like this. Let's try and do it a bit better. Should be perfectly symmetrical. My drawing obviously might not be. But it should be perfectly symmetrical, with 0 being in the middle. And these extreme ends being at 1 on that end. And -1 this end. What we've been trying to find then, the 5% tells us that we want to find some value, we'll call it R0, that represents, like if you took just a random set of different variables, loads of different variables, and you compare the correlation of all of them, 5% of them would just randomly have a correlation more extreme than this one. That's the number we're looking for to compare it to the observation we have. So the observation that they've given us, that we found in part C, yeah. So our observation is that 0.4259. And our job then is to find some value of the correlation, this row 0, such that that's equal to 5%. How do we do that? We use the tables. In the formula book, in the back of the book, there is this one for the PMCC. We need to know the sample size. We were told earlier on that that was 16, wasn't it? Yep, 16 in there. So we'll use the sample size column that we have, go down to 16. We're then told the significance level was 5%, so 0.05. We're going to go to, I'll try and make it so it's like the most left-hand column that we have, yeah? There we go. So the most left-hand column is the one we want. We want the row where the sample size is 16. Let's actually write down maybe an n is 16 as well. Using that then, let's see what number we get. I get 0.4259. 0.4259. Is that good? Yes, that is good. So that is our naught. That is, yeah, our naught, which is good. So we can fill that in. It's obviously negative. This whole thing is symmetrical. So the positive negatives, don't worry too much about, like if you've got a negative value out of a positive one. If you get the positive one, it's just the negative version of it, yeah? We're just looking at one side compared to the other side. So that's good. What do we want to do then? Take the value that we got given. Hold on. These shouldn't be the same value. What have I done wrong here? Oh, this one. Sorry. I just got this in the book, didn't I? I just wrote down the wrong answer. That's not that correct one. The correct one for the answer before should have been negative 0.545. Just a quick note, obviously we should have had a negative value, shouldn't we, from the correlation. So that's the way that we could have caught that one spot, like, oh, we didn't actually get a negative number, but we had a negative correlation. So something about that was wrong. But that's going to be all good now. That's the one from the book. So, yeah, we have the same idea, but this number now is correct. The observation, though, is what's changed, and that's become the 545. Negative of that. 545. So our job then is to see on our little diagram, where is that number? Well, it's over here, isn't it? Negative 545. It's firmly in our blue region. Our blue region is very unlikely to occur randomly, just to happen naturally. So what we've said, the observation is just very unlikely, very random. We don't think that just happens naturally. So we have evidence to change our mind that there's no correlation. What we've seen is so unlikely that we think there must be something going on deeper inside there. Hypothesis tests are like the first step of investigation. Is it worth having a look? In this case, because our observation was less than kind of the textbook observation from the diagram of like what is the 5% observation, so that the kind of natural boundary or the critical value that we're going to call it, the critical value, our observation was more extreme than that. So if we think about the size, not worrying about the positive negative, but the magnitude of our number, the observation we had was bigger than that critical value. To just put that in the numbers we had, so the negative 545, that is bigger than 0.4259, and that's going to lead us to reject H0. One thing to note, we only ever accept or reject H0. We're saying nothing about H1. This is just the direction that we're going to like do our checks in. That's all that's there for, really. But the whole goal is like, is this true or not? Do we think that we want to change our mind about this? We're rejecting H0. So yes, we are changing our mind. You should always write this as like a full sentence though at the end, yeah? Always write a full sentence for that. And like make it kind of to do with what's on about here. So I would say, yes, this suggests that there is sufficient evidence to reject the null hypothesis, and therefore suggests that there is a negative correlation between, what were these two things? The length of first name and the length of last name. Lovely. Looks good to me. Let's keep going. So what do we have? Sav is studying the large data set. He's coding the mean daily pressure with this thing. So just taking off 1010. Data for all 30 days are summarized. State the units of the variable x. Well, it's the pressure in it. So is it hectopascals? Yeah, HPA. That's good. Find the daily mean pressure for these 30 days. So it's the mean. So mean of that, they're calling it y, yeah? No, we're calling it x still. It's still x for a second. So the mean of x is x over n, or the sum of x over n. Why is it still x? Because we're doing the daily mean pressure. Daily mean pressure is x. So we're still using the x values that we should have. Unless I'm being silly and I'm overthinking it. And I'm guessing they're just going to use the model. No, we are just using, yeah, okay, I was being good. I was being smart. So what we're going to do is firstly, we're going to work out the mean for y in the same process. How to do that? Exactly this. Sum of the y's over how many y's there are. That was 30. So we get a value of about 7, don't we? Was it 7? 214 divided by 30. We get 7.13 recurring. So 7.13. That's good. That's the mean for y. X is just y plus 1, well, 1010. So that should tell us that the mean for the x is that plus the 110. So 1017.13. Yep, mean for the values here was 7. X is, we've just taken every value, added 1010 to it. So that would add on the same amount to the mean as well. You can do it this way around. If we have like a function of the mean where we take in our data set, that would be the general like value for the mean. Say we're going to do the same thing, but take in some linear operation on our data set. So we're taking every value of our data, timesing it by a, adding b to it. What does this do to the normal, like the mean we did have beforehand? Well, it takes that mean, so let's move everything over a bit, and it's going to times it by a and add b to it. Which kind of makes sense. If you double the values, it doubles the mean. Add 5 to the values, add 5 to the mean. So this is the thing that's always true. Basically means that the mean is a linear operator. You can do linear things to the values inside it, and it just does a linear thing to the actual value itself. All sounding good, yeah? Hopefully so. Let's keep going then. That was part B. Part C is to do the same thing, but for the standard deviation. So if we do a very similar thing up here, standard deviation, if we took in some, again, linear combination of our data, well, moving it side to side doesn't change the spread, no? Stays the same. So the B has no effect. And what A does is doubles all the values. Say it was 2, do you mean doubles all the values? That doubles the spread between them as well. Here, though, we're measuring the square of that spread. So it's going to times everything by a squared. So whatever value we did have for standard deviation, we will square it. Well, we'll square the scale factor of the x. And you can see here, they're 1 to 1, yeah. So this is 1. So that's going to tell us the standard deviation of the x's is the same as the standard deviation of the y's. So if we can work out the standard deviation of x, we have standard deviation of the y's. Beautiful, that sounds good. Let's go and do that. So standard deviation of x is equal to the standard deviation of y, which we know from the formula should be the sum of the squares, yeah, over n. Take away the mean of the y's squared. Let us put these all in. I'm just going to move these bits up a little bit, yeah, just to give me some more space. Off you go. What was the sum of the y squares? 5, 9, 1, 2. On the bottom is the n, how many there are, which is 30. Take away 214, all squared. Whack this in our calculator, see what we get. 5, 9, 1, 2. Divided by 30. Say it again. 5, 9, 1, 2. On 30. Take away 214, all squared. This gives me a very negative number, which is not good. What's gone wrong? That's not the mean, is it? 214. The mean we found, it was 7. We should never get negative this. It should always be a positive value because it's a variance. It's a measure of spread. Think of it like a length. It should be positive. So if I change that to the correct value for the mean, what do we get? 7.13. I get 146. That's really big, yeah? It doesn't change that much. Like if the sum of all of them is only 214, how is the spread 146? Like an average spread that much. We've forgotten to square root. This formula we've used is for the variance. So we need to square root all of that stuff. Square root all of that as well. So square out the answer on my calculator. 12.1. Lovely. Jubbly. What's next then? Oh, there's win stuff. Okay, yeah. Some of these large dataset things I don't know, so I'm just reading the mark scheme. I know some bits, but it's not always true. So we want to think about which way the wind is going. On here, I can't remember exactly how the map was going. So let's just draw a rough thing of the UK. Heathrow is already down here, isn't it? Let me double check where all those places are. So Herne location. Imagine there's a lot of people have been Googling that this week, isn't there? Herne location, where is it? Is that south? Yeah, it's south coast, isn't it? Okay, it's by like Portsmouth, Bournemouth, that way. Okay, it's down here. And I think the other place I can't say it's like Luchars, it's something like that. I don't know. I have no idea. I want to say it was France, but it's actually Scotland, isn't it? Location. Yeah, town in Scotland. Okay. So this is LEU, Chars. So that's where they are. What we have are these wind directions for them. We're not sure where they are. But what we have is very high pressure. And it goes clockwise in high pressure. So the wind itself is going to be doing this, yeah? Rounded that way. But when we talk about wind, we talk about where it comes from. So northerly wind comes from the north. Southerly wind from the south. With that then, let's think where are these coming from? Which ones are available to us? So looking at the top, blue charts first, that could be like a westerly one, do you mean, or a south? That's probably fine. Here, I want to guess north for Heathrow, and then probably something eastwise for Herne. Looking at these then, okay, it's going to be east for Herne, isn't it? I'm going to say it's the west then for Luchars. So let's fill these in. So Herne will be the east. Let's cross that out. The Luchars will have to be the west, won't it? And therefore, let's just leave Heathrow with northeast. And that looks good as well, Jim. It's coming in that direction. It's coming from the northeast. Looks good. Yeah, lovely. Looks good to me. Let's keep going. Number 4, what do we have? Probability stuff. So lots of things in there. Blah, 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 blah. Don't really need to know. Find the proportion of students who read exactly 2 of these magazines. So exactly 2 are going to be this section, and this section. Which looks good to me. Sorry, exactly 1. That I was correct about exactly 2, but we want exactly 1. So it's that one, and that one. We're in just one circle. We're at no point are we in 2 of the circles. So it's going to be 0.08 plus 0.09 plus 0.36. Adding these together then, what do we get? That's 45. Another 8 makes 53. 0.53. Is that correct? Just double check. Number 4, yep, all good. Big circle. And let's move on. No students read all 3 of the magazines. Okay, so that middle section, P is 0. So we'll get rid of P, don't need it anymore. Just a 0 now. Okay, find the value of P. 0, lovely. Value of Q. Well, we're told probably of G was a quarter, yeah? That's going to be the entire circle, G. Let's add everything up. We're going to have 0.08 plus the 0.05 plus the 0 and plus the Q. Should be 0.25. 8, 5 gives me a 13. And we have a 25 on the other side, so I've got 12 to go. So Q should be 0.12. Does that look good? Does indeed. Next bit then, we've been told about some conditional probability. That's S given E. So let's write that out as the formula. We know it's going to be the intersection S and E over just E by itself, the second one. And that should be 5 on 12. From here then, what do we want to do? Well, we go and look up at the diagram we had, and let's see which bits they are. So S and E are those bits, yeah? So that's R. And on the bottom is E. So that's the whole thing. So it's R plus 0.14, yeah, for those bits. R plus 0.14. And that equals the 5/12 we just found. That looks good. Let us times this bit to the right. So I'm going to have 5 times those bits. 5R plus 5 times 0.14, 0.7. This 12 will send you over there. 12R on that side. If I then take away, I'll have 7Rs equals 0.7. So R is 0.1, yeah? Does that match up? Does indeed. Anything else we need to find? T. So where's T? Up here. Do we know anything else? Let's fill in the values we do actually have. This is Q, 0.12. R we just found, wasn't it? 0.1, 0.1, yeah. I'll make it 0.10. So what's left over is just T, isn't it? Yeah. I have this, this, and this, this, and this, and this. Yeah, just U at the end. Little lonely guy on the outside. So what have we got? 8 plus 12 is 20. 25, 34, 44, 50, 80. So left over 20, get to 100. 0.2 on the outside. Is that good? Yep, that's good. Anything else we need? Okay, determine whether or not the events S intersection not E and G are independent. Okay, so S, what we're doing? S intersection not E. Let's go figure out where that is. So the way to do this, well, we have an intersection, so we need to satisfy both conditions. We need to be an S and not be an E. So we can go through and just ask the question of every point. Are you an S? No, no, no. Yes, 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 and no. So that can be the blue side. Do you mean that can be blue ones? We'll do the green for the E or not E. Are you not in E? Well, you're not. You are. You are. You are. You are. You're not. You're not. You're not. With the and, we need 2 ticks. So everywhere they've got a green tick and a blue tick is part of our region. So looking at that, where did we get? I got here and I got here. So altogether, it's the 0.12 plus the 0.36, 0.48 together. All make sense, yeah? Another way is, well, we need 2 ticks, so we have to be an S. So I'll just look at these ones, and I can't be an E. So just cross out the ones in E. What's left over? 0.12, 0.36. So that's good. That is, I'm going to make a little list of things I have. The probability of S intersection not E. 0.48. We want probability of G. I think we got told that somewhere, didn't we? Or we did something to figure that out, maybe. Yeah, it's up here. 0.25. We're going to want the intersection of those things. So S intersection not E intersection G. Don't worry about brackets here. Think of this like multiplication. If you're doing them all together, then don't worry, like it's like doing 4 times 5 times 3. It's the same as 3 times 4 times 5, etc., etc. Order here doesn't matter at all. Same for union, but if you have like combinations, then yeah, do brackets there. This is like, yeah, so one is intersection, one's union. I'll do brackets around those. Here, though, doesn't matter well, doesn't matter at all. Right then, let's figure out what section that is. Well, it's going to be smaller than this because we've got that condition and an extra condition. So where we had these ticks earlier, we can imagine doing like an and G. Let's do a different color maybe. Let's have this pink, like an and G there, and we can see, are we going to like satisfy that condition too? We need to ask the question now about these two. We did for Q, but we don't for the 3, 6. So our intersection point is just that Q value, the 0.12. We have everything then. Let's fill in the equation that we would normally know for independence. So the thing that's always true if they're independent. We need to check whether that intersection, like the triple intersection, S, intersection not E, intersection G, is equal to the product of those two individual probabilities. The S intersection not E and the G. So filling it in, what do we get? 0.12 on the left. And on the right, we have S and E, which is 0.48. And then, yeah, okay, this is good, 0.25. That's a quarter in at 25. Quarter of 48 is 12. So that is good. Big tick, let's do a bigger tick. And that tells us they are independent. Lovely jubbly. Same works in reverse. Like if we knew they're independent, we could write this fact down. So it's like they're both true or neither true. Lovely, that's all good. Did we do everything on the page? Yep, we have. Let's keep going. So the height of females from a country are normally distributed with a mean of 166.5, standard deviation 6.1, 1% shorter than k centimeters. Find the value of k. Okay, let's call it height. Distributed normally with a mean 166.5, standard deviation 6.1. So it goes in there, gets squared. We want to find the probability that h is less than k, so being shorter than k, is 0.01. So we need to do the inverse normal. We have the probability. We're going to go and find out what was the input. Where is the inverse normal on here? Is it this one? No, no, it's not. It's this one. So what values do we have? Well, the area, that's probability, 0.01. Mean, what do we have? We have a number of 166.5. Standard deviation, does it 6.1. And we want to be below, don't we? Because we want to lower. H is lower than some value. This is the shortest height. So below, let's do below there. Symmetrical. So like if we get, you could work out how far it's from the mean, just do the other way around. But easier, you might as well just do it this way around. That's going to tell us from the calculator that k is equal to 152.3. Don't need all the decimals. 4 sig figs is plenty, yeah. Let's double check that's the right answer. Yep, they even accept 152. Lovely. Looks good to me. Find the proportion of females from this country with heights between 150 and 175. 150, 175. So, other way around now, not inverse normal, just the normal. Normal. What numbers have we got? Same numbers, 166.5, standard deviation 6.1. And we want to find between, don't we? Between 150 and 175. Calculate. Oh, I get quite a big one. 0.9148. Does that make sense? Well, how tall is this? Is it 5 foot? Nah, you're 4'11", aren't you? 4'11" there. And that's going to be then for like 5'10", maybe 5'9", something like that. 91% of people being between, or women between 4'11" and 5'10". That seems pretty straightforward. That seems pretty good, yeah. Lovely. It's always worth checking. Like, does it make sense? If it doesn't, double check it. Do you know what I mean? If it does, be like, okay, maybe I'll look later. Right. Next bit then. A female from this country is chosen at random from those with heights between this. Okay. So that tells us that whatever we're doing, that we'll find that probability now, but it's been given that thing above. 150 is less than h, is less than 175. what we've been asked about, height is more than 160. So how do we know it was given that? Just because, yeah, we're choosing at random from those people, not from everyone. The one that we had before chooses from everyone in that country, not just the people of like the middle 91% of height, or like this range of heights. So how do we work this out? It is a given that formula. So we want the intersection. We can think a little bit smart here. You could obviously write down like intersection of this and this thing, but what does it mean? We're going to be bigger than 160 and between 150 and 175. Those two together, let's actually write them down as a number line. We can think about being, yeah, between these two. So this is 150, 175, and we want to be bigger than 160. So think about this point, go in that direction. Can go as far as you like, but just being bigger than 160. So we can split off the entire number line into these three regions where we need to be both, yeah, intersection, 2 ticks again. So here I don't get any ticks, do I? Here I get 1 tick, not 2. Here I get 2 ticks, and here I get 1 tick. So what region is that? We want to be at least 160 and at most 175. Bottom then will just be the given that thing. So actually it's going to be this whole thing, isn't it? Let's just steal this. It'll be that thing. Get rid of you. Put you in its place. Lovely. That we do know though. We can fill in the blanks there. The bottom of that is that 9148 we found. And the top we'll get from the calculator. So by 150, I change to 160. So now we're between 160 and 175. I get a new number of 0.7749. And let's do my division. So what do we have? Fraction 0.7749 over 0.9148 gives me an answer of 0.8471. And that is what the mark scheme says. So that's a good sign. Let's keep going. Well, heights of females from a different country. So different country, but they're still heights, yeah? So I'm going to just relabel. Height 1, height 1, height 1, 1, 1, 1, 1. All of them? Yeah, I think so. So height of country number 1. Now, we're going to have a new height of country number 2, which is distributed still normally with a standard deviation of 7.4. So 7.4 squared in there. Mia believes the mean height of the females is less than 166.5. Takes a random sample of 50. Finds her mean sample is 164. So, we don't have the actual value of the mean of country number 2. What we're going to do then, she thinks it's less than this one. We're going to test about that. So let's assume that it is. We'll put the 166.5, sorry, assume it's the same, and then we're going to test whether that's true or not. Looking at that then, one thing to notice, this is the way that we would randomly generate, or like the distribution of heights of one person, one woman in country number 2. We have a sample now of 50 women from this country. So we want to find, of the women in country number 2, their heights, the sample of them when we've got a sample size of 50. So that's distributed normally, the same mean, 166.5, but now the standard deviation will be 7.4 squared. Oh, well, this is the variance, yeah, 7.4 squared over the sample size of 50. So our standard deviation is the square root of that thing. Let's just work out what that means. So doing this, it will be 7.4 over root 50. So just square rooting this value, yeah. And we get a number to decimals of 1.0647, we'll say. So that's good. In your calculator, I think you can just do that, but I can't do that on here, do you know what I mean? So I have to use the decimals. Right then, what do we want to do? Hypothesis test. And what is she claiming? Believes that the height of females is less than 165. Okay, so our null hypothesis is that the mean is going to be the same, 166.5. And the alternate then was that they're less than 166.5. Do we have an observation? I think we do, don't we? Yep, 164.6. And we did have a sample size as well. What was that? It was 50. So same as always, let's draw this to kind of understand what's going on. We've got some distribution of the heights of these people, of these women, from country number 2. We're assuming that if we were to draw them out and kind of do like a box plot and see where those of them are, we would have this middle would be at 166.5. We have a level, significance level, yeah, 5%. We need that as well. 5% significance level, so 0.05. So effectively, we wanted to find some number here such that the area of this bit is 5%. And what number is this? This is going to be called the critical value. So yeah, the crit value. Lovely. And then see basically whether or not the observation that we had, which side of the line that's on. So is our value going to be over like here or over here? 2 ways of doing that then. One, either find the correct value and just compare it to the observation we have. Like if this is 160, then we're on this side and we're in the OK region. If this number is, if the correct value we get is 165 on the dot, then we're over here and we're in the no-no zone. So not allowed over there. Or what we can do is go and find out what is the percentage of this, like the probability of this happening. So I think this is like a tracker in it, 5% chance, like as we get the area as we go through. So if we can find out what's the chance of this, let's say it's 3%, then we know we're in this zone and have to be on this side of the line. So what can we do? I think the easiest way is to just use the calculator normally. We're going to have a mean of still 166.5. Deviation has dropped now, didn't it, to 1.047. And we want to find us being below the observation that we had. We're always looking at being more extreme than that observation. 0.6 there. So that 164.6 that we have. When we calculate that, this is what we see. So the probability that our height for the second women, when we take a sample of size 50, is less than the observation that we had, 164.6. That was 0.0348. That's less than 5%, yeah. So what we're really saying is that there's a random chance. If I took 50 women that did have a mean of 166.5, they did have that mean. I took a big population. All that's the mean of it is 166.5. Take a sample of that population, 50 women, and randomly 3.48% of the time, their mean height will be either 164.6 or lower. It's continuous variable, so that exactly that height doesn't mean anything here. But so there should be a random chance that there's a 5% chance of that happening, being less than this height. What we saw, there's only a 3.8 or 3.48% chance of it happening. Less likely, so more extreme. We found that we live in this zone because we're more extreme than what was going on. So 164.6 was very unlikely. Random chance of that happening is quite low. 3.48% chance of it happening. We saw 5%. So we observed something that's so unusual that we're going to change our mind. This causes us to reject H0. You should always write this as like a full sentence with kind of some context. Do you mean context of the question? So I'd say here, this supplies sufficient evidence to suggest that the mean height of women in country number 2 is less than 166.5 centimeters. Yeah? Lovely. Last one. What have we got then? Some distribution. This stuff goes up in order, A to B to C. All the probabilities are greater than 0, and they are all integers as well. So find the values of them all. It's a distribution. What do we know? If we add them all up, it equals 1. So log base 32 of A plus log base 30, 32, 36. Not good with the numbers, me. Of B plus log base 36 of C should equal 1. This, we have a sum of logs. A summer log is a log of a product, A, B, C, equals 1. Lovely, this is good. Log rules then. Let's raise both sides to the power 36. A to B to C. So A times B times C is 36. They're all integers. And they're all different. So let's have a look at different ways that we can split up 36. We could write it with the 1 at the front, yeah? That's the smallest number. Can't have another 1 though, but we could have a 2 and an 18. We could have another 1. We could have a 3 and a 12. A 1, a 4, and a 9. 166 isn't allowed, no, because you can't have two 6s. Next then, let's look at these. We've got 2. We've got a 3. Yeah, so 2 would give us 18, and then 3 and 6. Anything else going to work? 2 and 4, and that makes an 8. No, it doesn't go. Nothing, I think. So then it's down, yeah, 6 and 3 again. The next one, 3, isn't going to work, because then we're left with just 12. 4, we need another 3, so this isn't going to work. So they're all the possibilities. All probabilities are greater than 0. Actually, what that tells us, log of 1. So yeah, let's take this row. Log base 36 of 1. What is that? So let's have a look, double checking. If I'm not mistaken, I think I'm being really silly. It's just always 0, isn't it? Yeah, it is. We can get rid of 36 and just put anything. So of anything at all. What that tells us is A and B and C cannot be 1. So we look at our list down here. Nope, nope, nope. Yes. And we need the order. We've got 2, 3, 6. A must be the smallest, B's in the middle, C's at the top. So 2, 3, 6. That's probably something you haven't been taught. The only fact you've been taught about that is that they all add up to 1. Stats sometimes, probably sometimes. It's not so much calculation, it's about understanding all the different eventualities and thinking about, okay, what's going to happen? What weird things are going on to rule out some of my possible outcomes? And why are they being ruled out? Will make sense, yeah? Lovely. Next one then. We want to think about 2 variables now, but they each have the same distribution as above. Work out the chance they have the same thing. So one way, yeah, let's visualize this in a nice way. It's the last question. It's if you're still here, you want to do some math, don't you? Is it the last one? It is the last one, yeah. So let's have a little, how do I view this question? We have 2 things to do. We need to do x1 and x2. What things can happen when x1 occurs? Well, we can either get A or B or C. So this is doing x1. We then need to do x2. And you can imagine there's going to be A, B, C. But when we think about this, making them be the same, this second branch, like the second kind of step in the process, we only need the branch that's going to A. The other branches exist, but do not satisfy the condition we're after. So why bother waste the time investigating them when they're not anything useful to us? Same thing happens for B. Same thing for C. We have all the chances, didn't we? I'll just like log of those numbers. So this one, if you think about this branch, they're going to have log of A here, log 36 of A. Exactly the same thing here, log 36 of A. So at the end, it's going to be log 36 of A squared. I'm actually going to work out, like, are they nicer? Do they have any nicer bits? Do you mean A was 2? Is log 36 of 2 any good? Log 36 of 2. No, it's not. I'm going to leave it as that then. So that's good. We'll have exactly the same idea. A was 2, wasn't it? A was 2. Exactly the same ideas then. We'll have now, but with a 3 for the B. So get rid of U, put a 3. Have U twice. And then we'll have the same idea. C was a 6, wasn't it? 2 times 3 is 6. Another 6 gives me 36. So log is 36 of 6. As we calculate these then, you've done this before, haven't you? Down there, down there, down there. So I'm going to have log base 36 of 2 all squared. I always want to write like that, but I don't think you guys have seen that before, so I'm not gonna do it. And this thing then, we get exactly the same with the 3 and the 36. And the 36 and the 6 at the end. And then we just want to add all those up. So it's the sum of all of those. Yeah, let's write it down, do it proper. Duplicate those. Come on. Duplicate this. And this one. Add them up. And it's going to give us some number. It's not a very nice number. So let's have brackets. Log base 36. I'm wondering if there's nicer ways. Like the 6 is nicer, isn't it? Oh, and that middle one should be 3. Sorry, not 36, isn't it? Yeah, that should be 3. That should be 3. Let's double check. 2. Close, squared, plus log base 36. Oh, let's do that again. Open brackets. We got log base 36 of 2. Close that, square it. Add on. Open a bracket. Put a log in there. Base of 36. Put a 3 next to it. Close the brackets. Put a squared. Open the brackets. Put a log. Put 36 in the base. Put now a 6 inside it. Close the brackets. Square everything. Don't square everything like that. Just square the log part of it. Press equals. And I get a number of 0.3814. Does that match up? This is question number 6. 3814. That's good, doesn't it? Happy days. Yeah, happy days. I'll have more for you soon enough. Right then, mother lovers, loads of the stats papers here for you from A-Level Maths. Let's get going. Right, first one then, what have we got? Ellen believes the random variable C, representing cloud cover from the large data set, is a discrete uniform distribution. Write down the probability distribution for it. So what we have, there's 9 outcomes, yeah? So for every single value, it's just 1/9. So what we can do, we can write the probability that C is equal to some small number C is always equal to 1/9, where C is any number from, is it 1 to 9 or 0 to 8? 0 to 8, isn't it? 0 to 8. Lovely, looks good to me. Find the chance that it's less than 50%. So what we're having is less than 50, well 8, half of that is 4, yeah? So less than that, 0, 1, 2, and 3. There's 4 of them. Each one has a 1/9 of a chance each, so it should be 4/9. Looks good. From this, what you got? She's used all the data from the large data set in 2015. Found the proportion of days less than 50% was 0.315. Comment on the suitability of Helen's model in light of this information. So 4/9 is 0.4 recurring, yeah, all the 4s. This is much bigger in it than 315. So what we can say is that it's we're modeling a higher value than what we're actually seeing, a higher percentage. So it's not very suitable. So it's unsuitable because we have a different probability. So it's a different percentage or proportion. For a different proportion. Proportion, lovely. Appropriate for refinement then. What's that going to be? Something non-uniform, basically. There's not just an equal chance of cloud coverage. Do you mean it's going to vary? Kind of, probably not. Well, most definitely non-uniformly. Lovely, looks good to me. Let's keep going. Tessa owns a small clothes shop in a seaside town. She records the weekly sales figures and the average weekly temperature for 8 weeks during the summer. Oh, gets a PMCC, very small, negative 0.915. Stating your hypothesis clearly and using a 5% level, test whether or not correlation. Okay, test whether it's negative. So H0, our null hypothesis, is always that there's no correlation. H1, we want to see if it's negative. We have an alpha, that's the significance level of 5%, so 0.05. And we have an observation that we saw. The observation we have is the negative 0.915. So what do we want to do? We need to use that and the 8 weeks actually, so n is 8, and go to, where do we need to go? To the formula book. And in the back of this book, we have this little table. So we have one column there, sample size of n. We're told that's 8, so we go down, get row number 8. We then are also told we have 5%, and we're doing a one-tailed test. So let's zoom in a little bit. We want that 5% column on the left. And we want to go to row number 8. So what you can see there, we get the 0.6215. So 0.6215. The number we saw, the observation, was negative 0.915. So if we look at just the size of those numbers, so ignoring any negatives, our observation was bigger, yeah? So our observation being bigger, what that's going to tell us is that we reject H0. So observation is bigger than our kind of threshold probability. That tells us that we are going to reject H0. So just to clarify that, this number represents the probability. If you just take like a random set of variables and you pick 2 of them, any variables you like, and we just compare their correlation, there is a 5% chance that it gets to 0.6215 when there's only 8 of them. What we saw though was 91.5. Yeah, well, 0.915 for correlation. That's a very strong correlation. Our threshold for the strength was like 62. We got 91. We're too big. There's too much correlation for us just to like randomly think this happened. So it suggests we reject the idea that there's no correlation. All make sense? Lovely, jubbly. What's she doing now? She suggests a linear regression model. State, given a reason, whether the correlation coefficient is consistent with this. Yes. So what we have, the size of our number, the observation, the 915, that's roughly 1. So that's implying that it's strong correlation. So this is saying that it's consistent. Like, yeah, it's a good idea to do that. The stronger the value, the better the guide. It's going to be a linear regression, yeah? It's going to be close to a complete straight line. If it's 1, it's a perfect straight line, and this would be like the ideal thing to do. Which is the explanatory variable? That is always the x-coordinate, isn't it? Yeah. Yeah, it's the one that's going to explain like what's doing the reasoning, do you mean? So thinking of this, like temperature affects the sales figures, not vice versa. So it will be the temperature, or weekly temperature in this case, or average weekly temp. Looks good. She has a regression model, given interpretation of the gradient. So this negative 171. What is this? Well, it's sales figures, isn't it? And this one was in temperature. So what it's saying, every time we increase the temperature by 1 degree, we're going to lose 171 quid. So we have an increase of 1 degree. That implies a decrease of £177 per week. It's not a nice amount of money to lose, is it? I'd rather be gaining 177 than losing it. Definitely. Is that us all done? Looks like it. Yeah. Let's keep going. Number 3. In an experiment, a group of children each repeatedly throw a dart at a target. For each child, random variable h represents the number of times the dart hits the target in the first 10 throws. Okay, so we've got binomial, yeah? 2 assumptions we've made. Well, we've made 4, haven't we? We have a fixed n, number of trials. We also have a fixed probability of each of those trials. We have that our trials are independent. And also that we have, what's the last one? Where am I going this from? I can't think there's a 4th one. What is it? Consistent. They're independent. Trials are independent. What is it? I'm being really thick. Well, either way, that gets all the marks, yeah? These are good. There's a 4th one, isn't it? Who knows? Well, either way, that's good enough. For this one then, part B, find when h is bigger than or equal to 4. So this is just a binomial calculator, yeah? Let's get that one up. Top left. We want to fill in our variables and our values. Probability of success, we'll get a big keyboard this time. 0.1, yeah, the thing inside the brackets there. Number of trials, not 260, only 10 of them. Lovely. Number of successes, we're looking for 4, won't we? Yeah, 4. So, let's get calculate. We want to be bigger than or equal to 4. So look at that, it's this one, yeah? It's the one on that one. Oh no, to the right, down there. So, 0.01279. Kind of makes sense. There's a 10% chance they hit it once. If you do it 10 times, you don't think you're going to get 4 or more, do you? Only 1% chance of that happening. So that's good. Each child then, the random variable f, represents the number of the throw on which the dart first hits the target. Using Peter's assumptions, find that they first hit it on the 5th one. So how can they do that? They need to fail, succeed. Yeah. How do we do that then? Well, what's the chance of them failing on the first go? Is going to be 0.9, yeah? 10% chance of hitting it, 9% chance of not hitting it. So this should be 0.9. And then the next one, we've done a binomial. So we didn't change this probability. The next one should be the same for the next one, and the same for the next one. So we're going to do that 4 times, yeah? 4 fails, and then we're going to succeed. So that success, what's the chance of that? Is going to be the 0.1. Only way this can happen. We've got no other way that we can succeed on our 5th go, and that be our first success that we've done. The only way we can get there, fail 4 times, and then succeed on the 5th go. So, times all of them together, what number do we get? We get a number of 0.06561. Looks good to me. Circle some of our answers here. We got that one. We got that one. Let's keep going. Thomas assumes that in this experiment, no child will need more than 10 throws for the dart to hit the target for the first time. Ooh, look at you go, Thomas. Big assumption, isn't it? It's got this model doing weird things. Find alpha. So as always, add them all up. When we add them all up, they'll equal 1. So we're going to have 10 of these, yeah, because we're doing 10 throws. So this bit will give us a 0.1, won't it? So we're going to have that bit become 0.1. This stuff then, alpha is just a constant. And then we should add up this thing, n minus 1, going from when n is going to equal to 1 to 10. Want to do that then? It should all equal to 1. Let's do that sort of thing. Beautiful. Take this away, 0.9. And this then, let's think then what numbers are in there. We're just adding up. Let's plug in 1. We got 0. Plug in 2, we get 1. Plug in 3, we get 2. We're adding up all the numbers from 0 up to the biggest number. When we plug in 10, we get 9. So it's the sum of all the numbers 0 to 9. If you know that, it's 45. If you don't, you can just whack it in a calculator doing, work them all out. So we have 45, still times by the alpha at the front, equals 0.9. One way we could think about that, rewriting that a little bit different, is going to be 90 on 100, yeah? I can divide that, I get 2. So alpha is 2 on 100, or 0.02. Looks good. Looks very good. Let's keep going. Find probably that f is equal to 5. So now okay, just fill everything in, yeah. Probability that f equals 5. What do we have? We get that 0.01 plus, well, n minus 1, n is 5. So it's going to be 4 times alpha. So 4 times the value of alpha, we got 0.02. Well, that's 2 times 4 is 8, plus a 1 gives you a 9. 0.09, yeah. Nice and straightforward. Anything else on here? Yeah, what they're doing. How do their models differ? Well, this one, if we expand the brackets a little bit, what we're going to get, it's going to be 0.01, take away 1 alpha, and then times by alpha n. So 0.02n, take away 0.01. This number is, well, this is a straight line, yeah? Y equals mx plus c. Got the m, got the x, got the plus c. That isn't staying the same then. This is changing. We assumed up here fixed p and independent. So what the main kind of difference is, the probabilities differ. And actually it's an increasing gradient. So what we're saying, what Thomas is saying, not me, I don't make the same claims as Thomas. Thomas is modeling that they're going to get better over time. As they throw it, they have a higher chance the next go. Starting off, the first throw is going to be 0.1, 0.01, like 1%. And they gain 2% chance over time, effectively. So let's write that down. Thomas's model, his model shows an improve. I'm trying to think how to phrase it. They get better, don't they? Show they get better. They get better over time. Shows the kids improve. And who's the other guy? Peter. Peter's don't. Lovely. Oh, sounds good. Yeah, that sounds good. The way that they phrase it, like the actual terminology they want to use, is that the probability is consistent for Peter. So here P is consistent not constant. It is constant, I suppose, but consistent, like it doesn't change. Do you know what I mean? No, I read it wrong. Yeah, constant. And here, P is not constant. Lovely. That's a lowercase p there. Yep, looks good to me. Same thing, just like the actual phrasing they've used for it, do you mean? Lovely. Number 4 then. Charlie's studying. The time it takes his members of his company to travel to the office. Stands by the door from 8:40 to 8:50. One morning, asked co-workers how they arrive. State the sampling method he's used. He's used opportunity. State and briefly describe an alternative method of non-random sampling Charlie could have used to obtain a sample of 40 workers. So if it's non-random, you could do something like quota. Briefly describe it. Well, he stood here for 10 minutes. How about instead he just goes out once every... He'll go out every 10 minutes and just wait until he's asked like 2 people. Do you know what I mean? So, yeah, stand outside every 10 minutes. Every 10 minutes. 10 minutes. Ask 2 people. So how that works, we've got quota. The quotas themselves are the 10-minute slots. And the quota size is 2. So every 10 minutes, like say from... Let's make it a bit more... So, yeah, from 0800 to say 0900, just an hour before work, to stand outside every 10 minutes and to see the next 2 people that come in ask the question he was asking, do you mean, where he was asking about the time taken. All makes sense, yeah? Lovely, jobly. Next one then. He decides to ask every member of the company the time it takes him to travel to the office, yeah, blah, blah, blah. Doing the same thing, isn't he? State the data selection process. Because he's done every member, that tells us it is a that every member means population, and when we ask every member of the population, the name for that is a census. Looks good. Let's circle our answer for opportunity as well. Nice. He's got some results down here. Got some outliers and some weirdos. Write down the interquartile range. That is a 26 there. What's that? 58. Gap in there, 32. 58, 26 is 32. Calculate the mean, standard deviation. So the mean, what do? Add them all up. Take away. Divide by how many there are. And that then is going to be the big number. Well, the median number. 4133 over how many there are. 95. Not very good. 5. Try again. There we go. Fraction then. 4133. 95 on the bottom. What do we get? We get 43.5. Sounds good. We can use that then to find the standard deviation. So in general, we're going to do the sum of the squares over n. Take away the mean we just calculated squared. That gives us variance. So we square that thing for the standard deviation. Let's move this up a little bit. Let's go up here somewhere. Plug in these values then. What we're going to get? Well, the big one, the 202.294 over the little one, 95, minus the new one, 43.5. There was more decimals to that, but yeah, we don't care too much about those. We should really, but like in the real world, you should use the like answer key, do you mean? But in the exam, I think it's fine to do this. Like they're fine with rounding, do you mean? On the way, it's stats. Stats is all quite subjective, so some rounding on the way is not too bad. Do you know what I mean? What's going to go on here then? We're going to plug in the calculator, and remember we have a big square root. So let's do that. 202.294 over 95. Take away 43.5. Oh, squared. Square root that thing. And I get a number of 15.4. Does that look good? It does. Indeed. Next one then. State given a reason whether you recommend to use mean and standard deviation or median interquartile range. Well, we've got these weirdos, haven't we? We've got outliers. So outliers imply interquartile range and the median. Lovely. Yeah, outliers are going to have an undue effect over these ones because they're involved in these bits, yeah? So they drag it up a lot more. If we look at it, like we end up with 43.5, that's here-ish. Yeah, down in that bit. So much to the right of the median. Because we've got this long tail, this positive directional tail, so this positive skew. Let's just write that down, yeah, this is positive skew. We see that the mean is bigger than the median because these values are influencing it a lot more than all the other ones that have not been skewed, like think that you can have like this one is how much farther away. It's nearly 100 away, isn't it? They're like 80 away compared to this one. Most of them are, a lot of them are within 8 from it. So these have 10 times as much influence as like these ones. Maybe not 10 times, but you know what I mean? A lot more. So when we have that, we want to ignore them basically. Doesn't really matter about this one little data point. These are the ones that really matter. So we're going to focus on these ones. That's good then. So next, let's keep going. They both work for the company and have moved house since he's done a data collection, or her, not actually too sure. They've changed from 75 to 35, and they've gone from 60 to 33. Ooh. They redrew the box plot and changed two values. Explain which two values Tirani must have changed and whether each of these values has increased or decreased. So let's put some marks on there where they are. 75 is there, and 60 is there. Do a different color. You can be green. And green is going to go to 33, which is around here. And the blue is going to go to 35, which is also around here. So let's zoom in a bit. What we're saying then, well, both of them have gone from the same region. This is like the upper quartile. Think each 1, 2, 3, 4. Each one of those is 25% of people. Bop, 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 bop. We've moved from the upper kind of quarter to the second quarter. How do we do that? It's by jumping over these lines. These lines just represent, oh, I'm the middle number. Oh, look, I'm the middle of the first half. Oh, I'm the middle of the second half. So if we drag these over, where's the middle? What happens to that? They've moved left of the middle, so the middle must move right a little bit. So these two values will shift to the right to allow these to kind of like take the place, do you mean? Because the median has to stay in the same position. So if you end up like taking 2 from the right, put them on the left of it, it's now, instead of being in position number 12, or like position number 50, say, it's now in position number 52. We don't want that. So we need to make sure that we move it accordingly. Sorry, other way. These go left, it drags it with it. Do you mean it drags it with 52 down to 50? Drags it with it. Drags it with it. So both the median and the upper quartile should decrease. So what we can say are two values, the 75, and the, what number was it, 60. They're both bigger than Q2 and Q3. So that implies that Q2 and Q3 decrease because the new values were less than Q2. Yeah, all makes sense. These ones jumped over into that section, so it drags it down with them. It jumped any lines that they jump over, they'll drag them a little bit. When you have odd things, it might, like, it could be that you have two values in a row. It doesn't actually change the value that you get, but it's going to change the index still. Do you mean if you had two 40s in a row for the median, yeah, one of them was this one. These are now moved left. That had to be 3, I suppose. It would now be this value, but that's still 40 in it. So you could have repeated data because you've got multiple kind of people with the same value, something like that. And when you move it, it actually still has the same output, but it's a different, of the 40s, it's a different 40, if you know what I mean. Lovely, that looks good. Are we done? I think so. Just double check that one at the end because it's a bit strange, wasn't it? So it was G. Yeah, they will change lower and be lower. Okay, nice. That's good. Oh, which ones won't change as well? Yeah, which ones won't change, sorry. So all the other ones won't change. Q0, Q1, and Q4 are unchanged. Lovely. Next one, just the last one. It is. Right, last question, this one then. What have we got? We have some normal distribution. So L is going to be distributed normally with a mean of 18, a standard deviation of 4, which gets squared in there because it is the variance. Her calculator requires 4 batteries and will stop working when one battery reaches the end of its lifetime. Find the probability that a random selected battery will last for longer than 16 hours. So, thinking about that, what do we want to do? Probability that L is bigger than 16. Doing that then, change this number back to 16. I did do it slightly wrong a second ago. What's going on then? We get a number out. What do we get? 0.6915. Lovely. Next bit then. At the start of her exams, Alice put 4 new batteries in her calculator. She's used her calculator for 16 hours, but has another 4 hours of exams to sit. Find the probability that calculator will not stop working for Alice's remaining exams. So not stop, opposite of stop working, yeah? So op of stop. Op of stop. So we can work out the chance of it stopping. What that's going to be then is the probability that it's going to last less than 20 hours. Just one of them. Because if one battery breaks, the entire thing breaks, yeah? When only one battery reaches the end of its life. So we can work out the chance of it being less than 20, dying before the 20th hour. But given that, it has lasted 16 hours. So how to do that? We have a given that. We want the intersection between being bigger than 16 and less than 20. So between the two, yeah. So doing that, 16 is less than L, less than 20. And we're going to divide that, if I just give myself a little bit more space, by the second one. So they're given that probably the L is greater than 16. Yeah, making sense? So that bottom bit, we know, is the 6915 from above. And now we want to be between 16 and 20. And we get a new number. We get 0.3829. Right, what this is then, 0.3829 over 0.6915. And I get the number of 55. So 0.5537. This though, however, chance of it not working. So we don't want the op of stop, do we? We want stop. No, this is stop. We want op of stop. So thinking of that then, we're going to do 1, take away that number, 0.53, no, 5537. What do we get? Well, it's going to be a 44, it's going to be a 60, and a 3. Does that look good? Does it? Yes, it does indeed. For some reason, that's the only answer not marked in there. But actually, no, it's not. That's why it's not marked, because we need to do one more thing. That's a 1 battery. So we need to take that thing and do it to the power of 4. Too many bits. So yeah, that's a 1. Let's just label this a little bit. This is for 1 battery. So that tells us then we need to do that number to the power of 4. So 0.4463 to the power of 4. What do we get? 0.0397. Rounding up. Does that look good? Yes. Yes, it does. Beautiful. Let's keep going. This, I think it does say 6. That's just a rounding. Do you know what I mean? You'll get the marks for it. You don't worry about that. Next one then. Alice only has 2 new batteries. So after the first 16 hours of her exams, although her calculator is still working, she randomly selects 2 of the batteries from her calculator and replaces these with 2 new batteries. Show that the probability that her calculator will not stop working for the remainder of her exams is 0.199366. So what do we need to happen? The 2 batteries that are in there, we need them to survive, yeah? And the 2 new batteries, they need to survive as well. So we can think of the first batteries, they need to do at least 20 hours, given that they've done at least 16 hours. The new batteries have to do just 4 hours, yeah? How many of each? 2. And we want all of that to happen at the same time. These numbers we have found. For 1 battery, it was this number, yeah? If it's already survived 16 hours, the chance that it will survive another 4 hours, up to 20, is the 4463. This number we haven't got yet. Let's go find it. Calculator. A 16 times 4. Go to above. And we get a very big number, don't we? 0.9998 times that by itself. And let's plug everything in. 0.4463 squared times 0.9998 squared is equal to 0.199, which is what they wanted, wasn't it? Yep, lovely. It's a 1 at the end. We can do it the 1 at the end if we want. But yeah, that's all good. Next then, what have we got? After her exams, Alice believed that the lifetime of the batteries was more than 18 hours. She took a random sample of 20 of these batteries and found that their mean lifetime was 19.2. State hypothesis clearly, use a 5% level, test her belief. Okay, she's done a sample, yeah? So where we did have L before, the sample mean of L is going to be distributed normally. Same mean. What do we have as a mean? What was it? 18. But our variance now gets divided by how many bits we had. So the 4 squared gets divided by how many there were, which was 20. So thinking about the actual standard deviation then, it's worth kind of writing that down by itself. That's a square root of both this bit, yeah? So our standard deviation, the square of that, 4 over root 20 is 2 root 515. Looks good. So what do we want to do? And let's get that as a decimal because I think I can't put square roots on my thing on the left. Do you mean? What is that? We'll use 4 sig figs, 0.8944. Looks good. So then, what's the question asking about? We had an observation. So let's actually construct our hypothesis test. What are they thinking beforehand? The mean was what we thought it was. So the mean is going to be 18. And our null hypothesis then, what we've observed was 19.2. So generally you'd think that would be a one directional, but let's just double check. Yeah, she's thinking more than. So she thinks the mean's bigger than that 18. We've got an observation of 19.2 hours. And our alpha is 5%. So this is looking good. What we're going to do is take our observation and work out what's the chance of that happening. So the probability of the mean of a load of batteries being more extreme than 19.2. We're looking greater than, so it's going to be that direction as well, yeah? Greater than 19.2. And we want that number, and we're going to compare it to 5%. So let's use our calculator. We have all the same values apart from our standard deviation has dropped from 4 down to 0.8944. That looks good. Does look good. Do we want it bigger than? We do. Let's press calculate. I get 1. What's gone wrong there? I don't want to be above 4, do I? I want to be above 19.2. Calculate. Okay. This gives me 0.0898. Let's write that a bit nicer. 0.0898. Still not very good, is it? But we're comparing that to 5%. So that number, 898, is bigger than 0.05. So the observation we saw, the percentage, like the chance of that happening, is about 9%, yeah? Randomly. If we just did this thing over and over again, what we saw, 90.2, that would happen about 9% of the time. Our threshold for weirdness was 5%. So what we've seen is not actually that unlikely. It's pretty normal. So we're not going to change our mind. So this implies that we do not reject H0. Yeah, we do not reject it. There's not enough information to change our mind. The thing we've seen is not actually that strange. It happens 9% of the time. That's not that strange, yeah? I'm happy with that. All makes sense. Sounds good to me. Let's keep going. So, next paper. What have we got? 3 bags, A, B, and C. Each contain 1 red marble, some green marbles. What have we got? We've got 1 and 9, 1 and 4, 1 and 2. So he gets 1 marble from bag A. If he selects a red one, he stops selecting. So let's make a tree diagram of these things. Yeah, okay. We'll do that. Yeah, lovely. So what can we do? If he selects 1 marble from bag A, if it's red, he stops. So red up there, and then he's going to stop. If he gets green, What's he going to do? He continues by selecting at random one marble from bag B. What's in bag B? One red, one green. So from here we can go to red and to green. That's good. What else is going to happen then? If he selects a red marble, he stops selecting. Oh, from here again. Okay. If it's green, he continues by selecting at random one marble from bag C. Okay, bag C. What can we do from bag C? Well, one red and two greens. So red, green. Let's fill in our chances. What do we have? First choices. It's annoying. I wish I hadn't done this now. In my head there was 3 because the 3 are there, but this is fine still. What we have on the top row with the first choice, 1 red out of 10. For green, 9 out of 10. Then the reds are 1 out of 5 and 4 out of 5, and then we go 1 out of 2 for red. Sorry, 1 out of 3 and 2 out of 3. My 3s need to learn how to be 3s, don't they really? So that's good. What's going to happen now? We'll get some marks first, I think. Yeah. Does it look good? Most likely. Let's just quickly double check though. Not allowed to go back. Go back via this. What paper are we on? 2019? Yeah. So what do we have? 9 tenths, 1 tenth, 4 fifths, 1 fifth, 2 thirds, 1 third. Lovely. Looks good. So find the probability that Sasha selects 3 green marbles. Okay. Anyway, yeah. What we need to do, times those numbers together. So on the top, 9 times 4 times 2, 8 times 9 is 72. And on the bottom, 10 times 5 times 3, 150. Can divide this down. Let's use our calculator to do it for us. 72 on 150, 12 on 25. Lovely. Looks good to me. Find the probability that Sasha selects at least 1 marble of each colour. Okay, well, how could you do that? Is either to get a red and a green like that, or a red and a green like that. Because if she goes all the way down the bottom, it's all greens, yeah? It's all the greens all the way up. Going this way, she gets a red and then she gives up. So these journeys to kind of this endpoint are not allowed, and this endpoint are not allowed. So let's look at going through these paths. This one, we've got a fifth of 9 tenths. So that should be 9 on 50. And looking at this path, times everything on the bottom again will get us 150. Same as the bit above. On the top, 9 and 4 and 1. Times them together, I get 9 times 4 is 36. To find that again, let's have a look. 36 on 150, 6 on 25. Oh, looks good to me. So from there, we take those 2 numbers and we'll add them up. So we're going to do 950. I'll write it underneath the answer bit. At least 1 of each colour. 9 on 50 plus 6 on 25. Thinking about that, that's 12 on 50 plus a 9. 21 on 50. Yeah? Yeah. So, D, given that she selects a red marble, find the probability they selects it from bag B. Okay. So, it seems a bit weird, yeah? We want, given that he gets a red, so a red, the way we can think about that is like not all G's. A red one is just not going that way, yeah? So, we're going to get the opposite of triple G. We don't want that. That's right above. This is the probability of getting a red. A red. Given that, what is it? Given that he selects a red marble. Oh no, sorry, other way around. Other way around. This is the after bit. He gets a red one. Find the fancy from bag B. Bag B. So bag B is this bag. So it's the chance of us going down that way, yeah? The only one we can do that with is, yeah, green and red. So that's what we want. This is G and R. So, writing this then, using the formula, it should be the intersection. So GR intersection triple G, but not all over that given that one. Triple G, but not that thing. On the top then, we need to satisfy both conditions. Well, that's just one branch. So to satisfy this condition, it has to be that branch. The only thing to check, like, is it satisfying this one too? Well, yeah, because this branch is not that branch. Yeah. So the top bit is just that branch from G to, well, going G and then going R. Bottom stays the same, yeah. Bottom stays the same. G, 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 but not that thing. So what do we have? That branch we just were talking about, the GR branch, is 9 on 50. And the triple G branch, I think, did we work that over? Yeah, 3 greens. It was this. 12 on 25 would be 24 on 50. But we want the opposite. So it's going to be 26 on 50. Cancel them 50s off. What do I get? 9 on 26. Does that look good? You know it does, don't you? So, let's keep going. We've got a lovely little drawing or something. What are they telling us? Partially completed box plot. Figure 1 shows the distribution of daily mean air temperature using data from the large data set. Ugh. So, outliers defined by doing these things. The 3 lowest air temperatures in the data set are these ones. Highest one is this. Complete the box plot. Okay, so first thing, what is the IQR? What is the interquartile range? Let's zoom in a bit. This looks like 19.4 on the left, yeah, I'd say. On the right, 26.6. Ooh, didn't mean to do that. Go back. 26.6. I wish it wasn't in the bottom, like that corner. That's where my hand is always. I wish it was the bottom left corner. So, difference between those two numbers? Well, it's 0.6 away in it, so add that one. We've got 7.2. So, interquartile range, 7.2. So, if we want to think about the outliers, both of these are small. Both of these. All 3 of these are small, yeah? This one's big. So, we do need both ends. So, let's think about then, find this IQR, times it by 1.5, and we're going to add it and take it away from these two numbers. So, 1.5 then, times that number. IQR. What does that give us? So 7.2 times by 1.5. I get the number of 10.8. So we're going to take that number and we're going to add it on to both of these. So if we do 10.8 plus the 26.6, we get a number of 37.4. So that's well over here, yeah. 37.4 over there somewhere. Other way around then, 19.4, take away 10.8. 9.6, is it? 8.6. So 8.6, that's on here, isn't it? Yeah. 8.6 down there. So what does that mean? That means that we found kind of a global range of acceptance of our data. Anywhere between, let's do it in blue actually, it's a bit easier. No, do it in red because it's no, do it in blue. It's easier to see. Anywhere between this, or if you think the other way around actually, let's exclude, yeah, on the outside, we're going to have every number outside that range. So every number less than 8.6, or bigger than whatever number was at that range, yeah, 37 something, wasn't it? This range is like a no-no zone. This is the outlier range. So it's like the critical region for outliers. It's the outlier region. And the 8.6 we've just figured out, that is like the outlier critical value. I don't know if you have it called this, but it works in the same way, do you mean? It's the boundary. The very first number that would be a critical value. Are we saying less than, more than, or less than? Yeah, so it's like the last number that's not, but with this being continuous, it kind of is the same in both ways. We do have exactly the same thing going on up there at 37, or 37.4, but we can't see it on the diagram. But it is exactly the same thing, just a mirror image over there somewhere off the screen. All sound good? Yeah? Lovely. How are we going to use that? Look at these numbers we've got. 7.6, 8.1, 91.6. So let's start at the other end. What we can see, yeah, 7.6 is going to be too low down. Let's do them in red. 7.6 is like that bit. Do a bit bigger maybe. 7.6 there and there. 8.1 and 9.1. 8.1, 9.1. So looking at those, what's acceptable? 9.1. But these two are not acceptable. So in that way, what we're going to see, these will be left as outliers. This one, though, will not be. It is just part of the diagram. And actually, it now becomes the lower range, like the where you'd have a normal diagram, do when you have the sticks coming out. That's where the stick will stop. The sticks stop at the last non-outlier value in that direction. So very long, going from there. This end, where was our top end? 32.5. Yeah, it's nowhere near our 37, is it? So 32.5, let's put it in there. And yeah, nothing weird going on there. So we're going to join them up. You should really put these lines. How tall were the ones they did? They're 4. So I'll match what they've done, yeah. And that, just to clarify, is in the middle of that, wasn't it? Was it? Yeah, 32.5 down there in the very bottom. Let's put one of those lines on this end as well. That needs to be 4 tall at 9.1. Lovely. Looks good to me. What's going on now then? Large data set stuff. Use your knowledge of the large data set. We don't have any. Suggest from which month the 2 outliers likely to have come. So when it's very cold in Beijing, that's January, is it? Let's find out. What number is this? Number 2. Is it January? October. Okay, October. Obviously. Big tick. Well done. Let's keep going then. So, using the data from the large data set, you produce these statistics about daily mean air temperature. Blah, 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 blah. Finds deviation. Okay. Oh, it's with this thing. What is that thing again? Let me double check. Oh, that. Okay, yeah, I remember that thing is. So, what we have, sigma, this is a formula. If we think about like how, when we have the definition, you can think about 2 different ways to work out the, we'll start with standard deviation, just about the square root. Either do the formula you have like normally, where we do x squared, or the sum of the squares over n, take away the square of the mean. This, though, is kind of an expansion of the definition of it. So if we look at the definition, it's kind of similar. But what we want to do is take every value and see how far away it is from the mean, and do the average of those things. If we expand them out, it becomes this. Do you mean if you expand the brackets, it becomes that? Oh, sorry, square of those things. Square of those distances. Yeah, expand these out, becomes this thing. What we have, this is that top row. Yeah, this is that top row. This is the same as saying S, X, X over N. Do we need to square it? No. Why not? Because this square is like inside this summation. We're squaring all the values individually, and then we're adding them up. So ordering of it. Do you mean think Bibmus? But now we're getting well past Bibmus. There's too many letters to give it one word. But yeah, square first, add them all up, and then divide by n. So this thing is referring to the entire sum, yeah? S for sum, and x, 2 x's for the fact there's x and x in there. You sometimes see like SXY, and this is like one bracket with x's, one bracket with y's. That's for correlation, but I don't think you'll see that in like in standard maths. You might see it in like further maths, do you mean? So that's good. We just want to use this then. That's for variance. We want to find the standard deviation. So if we're going to stop that bit, standard deviation is the SXX over n, all square rooted. What's that going to give us then? The value we had, the value we were given, sorry, is 4952.906. Underneath, 184. Square root everything there. What's that give us? We get, well, it's a show that in it, so I'm hoping 5.19. And yeah, we get 5.188. Looks good. Next one. What's going on? Simon decides to model the air temperatures with a random variable. Oh, what a day. Using Simon's model, he calculates the 10th to 90th percentile range. Simon wants to model another variable from the large data set for Beijing using a normal distribution. State 2 variables from the large data set for Beijing that are not suitable to be modeled by normal distribution. Oh, sorry. I've just read through and skipped the question tonight. Yeah, so doing this thing. Calculate these bits. So we can be a bit sneaky on this. A little bit sneaky. Why can we be sneaky? Because everything's symmetrical. So this is t, so we'll just call it little t going that way, yeah. We have some shape of a distribution. It's doing something like this. Should be symmetrical. My drawing's not perfect. With a mean, 20.6. And we want to find the 10th to 90th percentile range. So let's draw a line here. And the line here. These bits over there. This bit over there. Should be 10% each. 10%. And that bit is 10%. So the middle, yeah, is 90 in it. So sometimes you can do things where like we're going to go and do some values and do some guessing. I think it's easier to do this one and just find what number's that. So we're going to ask the question, what letter is it? T. Probability that T is less than some number. Let's call it alpha. That's going to equal to 0.1. So basically we're saying that this is alpha, yeah, that number. It's going to be like 20 or something in it, like 19. Maybe it's like 12, 13, 14, 15, something like that. So how are we going to get that? We need to do the inverse normal. Let's get our little calculator. Bottom left, bottom left. So we're told we could do the between, but some calculators don't have it. You could always do between here as well, but yeah, some don't have it. The mean that we have, 22.6. Standard deviation is 5.19. That's not a 9. That is a 9. Area we want 0.1. And we want to be below. So yeah, we get number 15. 15.9487. Lovely. That's our alpha. This is 15. We'll call it 9.5. We'll call it 15.9, yeah, just to write down on here. So, how big is that gap then? Because this is symmetrical, it's the same as that gap on that side. If I'm going to get them just to be separated, they are different. They're the same size, yeah, same size gap. So let's think about it. I've got 2.6 to get to 20. There's another 4.1 of it. So it's going to be 6.7, yeah. So it should be 6.7 this way as well. So adding that on to 22.6, we're going to get, well, those two make it 28. They make a 1.3, so 29.3. That will be like another alpha. Do you mean not alpha? Maybe we call it beta. And that is, what did I say? 29.3. Was that it? I think so. Yeah, 28 plus 1.3, 29.3. So we have those two values, and they are the two ones that we need. So the interquartile range is going to be, well, we didn't actually need that number. It's 2 times that, yeah. Interquartile range is going to be 2 times by 6.7. So 12, nope, 1, 3, 4, 13.4. Does that look good? 13.3, they said. I think my rounding, we should be fine there. Do you know what I mean? Like, we're going to be all right. Hopefully it will be fine. Well, in the exam, don't round. Don't do the rounding. What we should have is 13.3 if we don't round along the way. Yeah, this is actually not 6, 7. What number should it be? A little bit smaller. Well, this was 594, wasn't it? So yeah, it should be a little bit smaller. So we're going to do 6. We'll do like 6.5. Yeah, all making sense. Hopefully so. So what's next then? Done that bit. Yeah. Oh, just a note as well. If we look back, so if we go between an area and make that 0.8, because that's the middle 80%, yeah, 10% either side missing, we should get, yeah, those numbers that we had, 15.94, and this one 29.3. You can see is the rounding of the one on the left there. So that's good. Both ways work. Either way you want to do it. Happy days. What have we got down here then? Yeah, 2 variables in a large data set that are not just suitable to be modeled by a normal distribution. So we can have the that wind speed one. So the wind speed, mainly because it is qualitative. I might be spelling this wrong every time, but who cares? Made of words, not made of numbers. We can't really do normal distribution on words. Well, we can't really do it. We can't do it at all. Oh, Ivory Coast just scored. 90th minute. Go on, Ivory Coast. So that's bad. We don't want that. Another one then. We are going to have rainfall for a different reason. Mainly because it's asymmetric. See if I can spell anything. Let's try again. No. Symmetric. Yep, that'll do. Lovely, jubbly. That's good to me. Let's keep going. Barbara, she's investigating the relationship between average income and average carbon dioxide emissions for different countries. Okay. Takes a random sample of 24 countries, finds the PMCC through this number, state upwards clearly, test at 5% level, whether or not it's greater than 0. So let's have a look. Page 0. We're going to have, we're taking a sample of this, yeah? Do you still do that? What year am I in? You must still do it, surely. I'm not being silly, am I? No. Double check then what's going on. We do just, yeah, I'm not overthinking it. There's another version you used to do of like the correlation mean, like the mean of a sample of correlations. Do you know what I mean? But yeah, don't do further maths. It must be. So our null hypothesis is always going to be there's no correlation. I'll alternate then. What's she asking about? State your hypothesis clearly, whether or not the PMCC for all countries is greater than 0. They literally tell you in the question exactly what it should be. Most of the time, anyway, maybe not exactly like that phrasing, but pretty much always that way around. We got 5% level, and we were told this value. So let's take this and go. Oh, I'm being silly earlier about the mean. There's a sample size. It's in here, isn't it? So yeah, we are doing a one-tailed test. So 5%. We don't just split in half. We've just got 5%, and a sample size of 24. So go to column number, is that 5? And the sample size down to 24. Go back across on the left to the 5% column, which is the most left-hand side one, and we get a number of 0.3438. 0.3438. So just to clarify, it is the row of 24 and like the most left one of that, yeah, of this row, the 24 in it. That number that we've seen there is if you took loads of data, like 20, and you took a sample of 24 of those data sets. No, let me rephrase that. You've got loads of different data sets. You pick 2 of them. You pick then 24 different like data points from each of those 2 data sets, and you're going to plot the scatter graph of them. Looking at their correlation, there's a 5% chance on average that you get a correlation of 0.3438 just randomly. From any 2 things that you could pick, this is the correlation that you would have. The correlation we've observed, this is our observation up here, it's more correlated than what we're saying randomly happens 5% of the time. So that's bigger than the 3438 that we just had over there. So our observation is bigger than the kind of threshold. I call it the threshold. It's going to be a threshold. What's the word for it? Correlation. You can call it a critical value as well. It's kind of the same idea. Threshold, critical value, same idea. It's a boundary between what would change our mind, reject H0, and what would accept H0, like not change our mind. So in this case, yeah, we've seen something like what we've observed is very unlikely. So that means we can change our mind. So we're going to reject H0. In the exam, always put like a full sentence, like with context about this thing. So what we can say is that we have sufficient evidence to believe that there is, where is the actual claim? Yeah, sufficient evidence. There is sufficient evidence to reject the fact that there is no correlation between the countries, or between the 2 things, between emissions and GDP. Vice versa, yeah, there's sufficient evidence to suggest that there is a correlation between them. So i.e. that there's not a not one. Do you know what I mean? That's all good. It's worth on these, like, just when you do a question, read through the mark scheme afterwards and just double check like what phrasing have they used for these. Just see exactly what words they've used, try and copy like how the structure of it basically will be the same every time. This is good then. Let's keep going, smooth it out of the way a little bit. What's happening? Barbara, she believes that a non-linear model would be better to fit the data. So she codes the data using this. Okay, oh god, okay, go on, Barbara. All right, Barbara's doing stuff. She's got this thing. These equal this. Right. The PMCC is found to be this. Explain how this value supports Barbara's belief. So it supports it because if you look at like this number we have, the 882, and this number 89, if you round it, it's basically there, and it like 88 is 89 pretty much, isn't it? Close enough, yeah. So these 2 are roughly the same. So roughly equal. And that's good. That's a good sign because what the correlation is showing is no, actually no, it's not because they're roughly equal. Ignore me. I think that's a red herring in it, and I've fallen into its traps. It's not because they're equal, but these two values, it is still those two values, but not because they're equal. But this is a straight line. And this then is a strong positive correlation. And actually it's a very strong one, isn't it? It's nearly 1. Kind of as strong as you can get, closely. So this is a good sign. We have something that's very strongly correlated, meaning they're following a linear pattern quite well, and we want to plot it in a linear way. The only thing to double check then is they're both positive, do you know what I mean? So this is also having a positive gradient. So that's good. Everything is matching up. All makes sense? So just to clarify, positive gradient, it is just a straight line graph as well. So those two facts together. This one is close to 1, which is good. So that means it's a straight line. And the fact that it's a positive correlation, obviously with a positive gradient. That looks good. That's just 1 mark though. You could probably be a little quicker than that, couldn't you? So what could we say? Barbara, number 3. Yeah, value's close to 1, or there's a strong positive correlation. Yeah, fine. So show the relationship between y and x can be written in this form. Oh, so this isn't stats, is it? This is just going to be what should we call it? Algebra. So or log stuff, isn't it? What do we have? C is equal to that, and x and y equal to this. Okay, let's fill in the bits that we do have. So C is log base 10. Let's do log then, not lg. Log base 10 of y. That's going to equal to negative 1.82 plus 0.89 times by m log of x. Just to clarify, taking this equation, we've got a c and we've got an m. We've got an m and a c over there. Plugging those bits into where they need to go gives us this one. We want to rearrange for y. So what I'm going to do, raise both sides to the power of 10. The log stuff on the left will kind of go away. It's going to be y is equal to, on the right, it'll be 10 to the power of all those bits. So 10 to the power of 1, well, negative 1.82, plus all of these bits. Let's think about how to do that. 0.89 log of x. Where we have additions in those powers, we can change it to be a product of different bases, well, same base with different powers. So instead of adding them up there, we can like times them together and then do the power of them individually. So something like that. So just to clarify, it's now this thing, like times by this thing, where both of them are powers, yeah? 10 to the power of this thing, 10 to the power of that thing, times them together. That's good. Let's work some bits out. Well, this is just A, isn't it, yeah? This thing is just, was it A they've called it? Is that the letter they used? Yeah, that's little A. And here, this is actually N. So this is, we're done already, yeah? Yeah, we are done. What is this first number? 10 to the power of negative 1.82. We get a very small number, 0.01514. I have to round it. And this bit then, 10 to the power of 0.89 log base 10 of x. What's gone wrong there? I think I've just written n and x slightly the wrong way around. What's happened? Oh, am I being silly? I'm being silly. Yeah, so one step to do in here. Let's use the log power laws. This thing is so many things times by a log or something. So those so many bits, the n out the front, can go up to be the power in there. That then, we have the log. We have 10 to a log. Whenever you've got 10, or like a power, to the log of its own base, they just cancel out. So that whole thing, not that whole thing, this whole thing is just what's inside those brackets, i.e. 10 to the power 0.8, 0.89. Does that look good? It does to me. Does the mark scheme too. Let's keep going. What's going to happen next? Magali is studying the mean total cloud cover in octas. Whoa. What are units? Blah, 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 blah. Large data set, blah, blah, blah. 184 days. All 184 days. One of these days is selected at random. Find the probability it has a daily mean total cloud cover of 6 or greater. So 6 or greater. It's all those. So that's the number of days in the bottom row. Add them all up. What do we get? 52 plus 52 plus 28. 52 plus 52 plus 28. Doing that. 184, 124, 132. And it's all over how many days there were in it. 184. 184. Does that look good? 132 over 184. Lovely. Could simplify it down, but you don't get any more marks for that. Decimals as well, do me no more marks, so this gets you all the marks. No point faffing doing extra things for no reason. What have we got now? Whether daily cloud coverage can be modelled using a binomial distribution. She's doing this sort of stuff with it. Find this one. Okay. So let's just go to our binomial calculator in the top left. What values have we got? We have a number of trials is 8, not 10. 8. Probability is going to be 0. Let's make sure we're at the end. 0.76. Yeah, 76. Number of successes, we're looking for 6, not 4. Calculate. What do we get? So we want bigger than or equal to 6. That is that row, yeah, in there. So 70, 328. 0.70, 328. Is that good? Yep, looks good to me. Fine, to 1dp, the expected number of days in a sample of 184 days with a daily mean total cloud coverage of 7. So that's greater than or equal to 6. Do I have to really do it again for like 7? I suppose it's exactly 7, isn't it? Yeah, okay. So, different way of thinking about it. We want to find, first of all, probability x is equal to 7. Because it's not at least 7, this isn't it? This is just saying exactly 7. So, calculator, back on there. Most things are the same, but this little 8 becomes a little 7. Press calculate. Then we want the equals to this top row. So 32, 374, 0.32. Try that again. 32, 374. What are we doing with that again? Okay, yeah. So this is the chance of one of them being exactly 7. We want to get kind of the number of them every 184 days. So we just want to times that thing by 184. Times 184. What does that give us? It gives us a number of 51.7. Rounding that then to 51.7. That should be fine. One decimal place. Yeah, lovely. I will do one more just to show. That was 73. Well, 74. 385 is what follows. So yeah, 74. And that therefore is 51.7. Lovely, jubbly. Let's circle the one above as well. That's good. Part C. Explain whether or not they are support the answer. Whether or not your answer to part B support the use of her model. What have we shown then is that there should be 51 days. They get 7. 70% there. This looks good, I think, doesn't it? Yeah, it looks good. Everything looks good, I think. The 7s we got 51 and there's 52. Like 51.7 and 52. So I think that's fine. 51.7. It's roughly 52. So what does that mean? Like that means that the observation, or the model's the one on the left, yeah. The model was roughly equal to the observation. So that's going to imply that the model is good. It is, we can use it like a reliable. I see what word they use, but they didn't use one. Reliable. Yep, spot on. What's next? There were 28 days that had a daily mean total cloud coverage of 8. For these 28 days, the daily mean total cloud coverage for the following day is shown in the table below. Blah blah blah. Find the proportion of these days when the daily mean total cloud coverage was 6 or greater. Okay. 6 or greater. So what numbers could we get? 5, 9, 9. 5 plus 9 plus 9 over how many were there? 28 days altogether. That's 18 plus a 5, 23 over 28. Is that good? It is. Wonderful. Part E. Comment on Magali's model in light of your answer to part D. So what's part D telling us? On the days when there were 28 days that had a daily mean cloud coverage of 8. For these 28 days, the cloud coverage for the following day is shown below. Okay, so it's looking at the next day. Find out if we get 6 or greater. Well, what we can see, this number, let's get it as a percentage. 23 on that. It gives us about 82%. So that's our chance of being 6, 7, or 8, 6 or greater. We did the same thing earlier. And this one, what percentage was that? It was 71, 72 when you rounded. So those two percentages are quite different, aren't they? So our model does not kind of match up with our actual observation. So your observation is not equal to your model, or your model does not give a prediction that actually was observed. So that means it is going to be unreliable. Does that look good? Am I correct? Yes, spot on. Okay, number 5. Is there number 6? There's not. So I think we'll call it there, and I'll come back in the morning and do the rest, because I've now done 5. Yeah, I've done them in a different order. Like, this is the start. There's 2 of them here. I've done 3 already. I'll do the others in the morning and then edit them all together. That should be good. So what's happening? Machine puts liquid into bottles. Ooh. The amount of liquid put into each bottle for the normal distribution. Mean 25. Okie dokie. So D, distributed normally. Mean 25. Come on. 5. Do we have anything else? Let's find out. 15%. Can I less than that? Find the value of K such that this. We don't have. No, we don't have it. So sigma square goes into there. Now then, what's going to happen? We're told this kind of second fact, that the probability that we're less than, so our D being less than 24.63, chance of that is 15%, 0.15. Let's draw this out. What's happening? We've got some distribution, yeah? Should be symmetrical, but my drawing is never going to be perfect. This is, we'll call it little d, because it's like the actual value we're going to look at. We've got the peak happening at 25. So that's a mean of 25 in there. And from this then, what can we say? Well, we have got the 24.63 and 15%. So let's draw a line at 24.63. About there-ish, yeah? Who knows? That is 24.63. And this region then, on the left, we're told 15%. So that bit is 15%. Now then, we can use that to work out the standard deviation. How we're going to do that is using our calculator. What we need to do is plug in some of these values. So what do we get given? Where am I going? Back here. The right one? No, we're doing inverse normal. Let me get inverse normal. So you'll notice that we need to put in the standard deviation for that to do the inverse normal, but we can't. So how do we do that? We need to use the standard normal. Standard normal is just kind of a shorthand for this. We have some distribution that's just distributed normally, mean of 0, standard deviation of 1. So the standard normal, it's been standardized. The general word that's used for this is to normalize it, but we can't obviously describe this as a normal. That's a bit silly. So we call it a standard normal. I think if you call it the normal, people will know what you mean. Like, it's what I call it when I'm dealing with data. Like, oh, the normal, that normal thing, yeah, that normal. So it's just one that's based around 0 and 1. And it's got the same shape. It's just going to be a transformation. Like GCSE transformations, we have a translation, moving it left and right, putting the mean in the right place. And then we're going to have an enlargement, again, horizontally, making sure that the distribution, like thickness, is correct, how wide it is, how girthy our distribution is, i.e. standard deviation. So what we're going to do is we're going to use the fact that we have some shorthand notation for this. So we have the probability that we're going to be smaller than some number, say little z. We write that as phi z. So same way around then, we can work out the inverse, like what's z going to be? That should be the inverse of the probability. It is this whole thing. I will just write like prob, just to make it a little bit easier for you to read back and look at, do you know what I mean? So, nice. We have another thing to think about z then. Like I said, it's just a transformation. We take our value, we shift it by the mean to the right, and then we enlarge it by scale factor of sigma. Just GCSE transformations, isn't it? -1 there. Let's move that over a little bit, make it a little bit better. There we go. And the probabilities. So this then, we're going to fill in the values we have. X, did we actually know X? Yeah, 24.63. X actually here should be D. Do you mean that should be the little D? Should be the little D. Take away the mean, 25 over sigma, we don't know, is equal to this thing. So inverse phi of the probability that we had, 15%, 0.15. That's good. What we need to do then, area needs to go and be 0.15. Mean, big fat 0. Standard deviation, big fat 1. We want to be below. So we get this number up. This number is negative 1.0364. That is z, like that's z that we're interested in. What does that actually represent? It's a measurement of like how far away our number is. So look here, how far away is it? 0.37, yeah? That is in terms of D, whatever units D has, so millimeters. This value that we have measures how far this gap is in terms of standard deviation. So what we can say, 24.63 and 25, well, 24.63 is 1.0364 standard deviations away from the mean of 25. Yeah, makes sense? Lovely. There's just solving of it, like this equals this, yeah? We want to get sigma. So sigma itself is going to be the bit on the top, the 0.37 I was on about, 0.37 over that number we just got, 1.0364. These are actually both negatives. Sigma will always be positive. Think of it like it's a length, yeah? So it's a measure of distance. So it can't be negative. Not in a kind of normal world anyway. That's a good pun. I like that. I'm quite funny with that. Didn't plan to do that, but who cares? It was good, wasn't it? Lovely. 357. Does it match the answers in the mark scheme? Question 5. What am I doing? Is it question 5? Yeah. What's going on? Oh, I'm not on the last one. Hold on. Sigma. Yes, 357. That's good. Lovely. What else is happening? Okay, well, that's just the first part. Okay, we need to go through then and now use this value, yeah. So doing this thing, we want to find probability 24.63 is less than D is less than some number K, and that's equal to 0.45. I'm wondering if there's a way we could do this like differently, do you know what I mean? Yeah, I'm wondering if there's a way we can do this differently, like just doing some graphical stuff. Like, is it going to work? I don't think it is, because it's not a linear relationship, do you know what I mean? Like, just because this is, so 15%, you think like that's going to be triple it, does that have anything to do with it? No, not really. I think all we need to do here is like same sort of process of doing the inverse normal, to then work out what it should be using these things. Yeah, because we can do the same sort of thing. We can draw a line that's going to come down here, because then we need to be between some number 24.63 and some number K. This green number is K. So this green region represents like the kind of between those two, and that's the 45%. So you can see a few things like this gap is 10%, this gap is 40. That is good. So again, you can see it's a bit easier to understand if you can draw it out, see where these lines are going to go. How we're going to work this out then? We don't know what K is, but now we do know sigma. So we can go over here. The area we want is 0.45. 0.45. Our mean that we had, 25, yeah. And we have standard deviation that we just figured out to be 0.357. Looks good. Just double checking then what's going on. I'm trying to find some area, yeah, and I need to make sure that my area is 0.45. That is for the middle region. But actually, it's easier if I just look at the top. This value is really, let me say it's 40% in there, yeah. Let's actually put that in. We'll do some red zone. That red zone then, 40%. So let's have a look. We want to make sure that we are above something. And actually, we'll go to 45. So just to 40. And we get a value of 25.09 for K. So K is equal to 25.09. Is that correct? It is. It is indeed. Where we put that? We will put that up here. K equals to 25.09. And then we will circle it. Looks good to me. So let's keep going. Part B then. Using a normal approximation. He's done a sample of 200. So yeah, using a normal approximation, find the probability that fewer than half of these contain between these two numbers. So let's think what they're saying. Firstly, chance of us being between those two is what was given to us above, yeah? That's 45%. So we're going to have something. We've got sample of 200 and with a probability of 45%. So that thing is a binomial distribution. This is a new sample. I'm going to call it X. So yeah, it's going to be X distributed binomially, but using a normal approximation. How do we do that? A few ways. Well, one way. What we have to do is think about n times p. So 200 times by 0.45. That's going to give us 90. And then also doing n times p times 1 minus p. So times that 90 above by 0.55. What does that give us? 90 times 0.55 is 49.5. So that's good. These numbers then are the mean and standard deviation of our approximation. So y distributed normally, not the d there, sorry, distributed normally with a mean of 90. And that thing's the variance, yeah? So this is going to go in, but it's worth noting like that is sigma squared. Sigma squared, not sigma. That's good then. Blah, 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 blah. Using a normal approximation. So yeah, we need to approximate, don't we? This is good. So you think we're going to have, how many do we want? Fewer than half of these. You'd think there's less than 100, yeah? Less than 100. Fewer than half. 200? 100 wouldn't be allowed because that's exactly a half. So we'd have to be less than 100. But that's for x. So x being less than 100. What's the issue? X is binomial distribution. So when we look at it, we have discrete values of like this region in the middle, or like this value here can be 100. This is 99. This is 98, etc. and 101 at the other end. So this top row is for the binomial. The normal is continuous. So actually this has all the values. I'm going to move this down so it's like, yeah, it's on the top side, yeah. The normal has all the values. It's continuous. And we're going to approximate this to this. So when we ask our question, x is less than 100, this though is on discrete. data. It's on like the natural numbers, yeah? We're looking at like how many times something happens. What is the thing? I don't know. Where we're doing bottles in it, we're doing things with bottles. But we can't have a 0 or less than 0 bottles. So when we look at the binomial side, it's discrete. This side is continuous. We need to do the continuity correction. I.e., because this is discrete and this is continuous, how can we say, what values do we have, and how do we correspond that over here? So my x being less than 100, what does that actually represent? Is like this window of stuff, yeah? If I draw that out a little bit, because 99. So I think is this better to phrase it like this? No, let's do it slightly differently. We're going to slide everything over just one, yeah, like that. So just reordering these bits. One sec. So now you can see like each number. Do you mean this is when it's like I've got too many hundreds. 101, 102. So yeah, same idea. We want to be less than 100. So it is like from this region, yeah. Look at that line that we have. This is the block for 100. We're going to be less than that block. But if these are the blocks for 100, what's actually separating them out is 99.5. This is 100.5. This side is 98.5. So our continuity correction on the binomial side is just less than 100. But on the normal side, it's actually less than 99.5. So y less than 99.5. And now then, we need to use our normal calculator. Come on. Normal calculator, top right. What was the mean we found? 90. Standard deviation, we actually haven't got yet, have we? No. So this was, yeah, sigma squared. So if we take that then, that tells us sigma 49.5. Square root of that thing. Square root of 49.5 gives me a number of 7.04. That's good, I think. Rings about. From here then, what are we going to do? We are going to... Have I done something wrong? I feel like I've done something really wrong. No, I keep looking at the wrong answers in the in the book that way. I'm looking at like double checking I'm right. I'm looking at answer C, but none of this matches. Everything's wrong. Are we right? It just says the square root of 49.5. Okay, so yeah, that's fine. From this then, let's use this to work out what we're going to have over here. We have the 90 already. This needs to be 7.04, and must be below the 99.5. Calculate, and we get that number there then of, well, I gave myself some space, didn't I? 0.9114. Lovely. Does that match up? It does. Yep. They've rounded it to 912, so somewhere along the way I've rounded a bit. But yeah, we're good, yeah. All sounds good to me. Now then, we're doing a hypothesis test. The machine's adjusted, so standard deviation of the liquid in the bottles is now 0.16. So all of this stuff is like one version of it. A bit better. Now we have a new version. So let's call that A. Distributed normally has a standard deviation of 0.16, so that would be squared in there. Following the adjustments, she believes the mean to be 25. Well, she believes it to be less than, doesn't she? But we're still going to assume 25 for now. Random sample of 20. Okay. And found the mean liquid to be 24.95. I mean, if that's what I get, I'm happy with that. Do you mean? if they're aiming for 25 and they give me 24.94, that's pretty good, isn't it? Not too bad. What is that? 0.08% off, I think, something like that. Either way, pretty good. Maybe 0.80, something like 0.8, 0.08, something like that. It's close. So, what do we need to do? Hypothesis test, yeah? Fill in the blanks, as always. Our H0 is going to be, let's do it up where they've got that other bit over here. So, H0, what we thought originally, the mean is 25. One thing I forgot to do, It's a sample in it, sample mean. So yes, that is how A is going to be distributed. That's correct. But we care not about A, but about the sample mean of A. That's still 25, has the same mean, but we will now divide the 0.126 squared by how many there were. There was 20 of them, so that goes in there. That's good. Now we'll continue. Null hypothesis is the mean being 25. Alternate one, what does she think? She believes the mean amount of liquid to be less than 25. So mu is less than 25. From here then, what do we need to do? Well, let's draw it out. Have a look at our distribution. We have something like this going across. This is our value of A that we've just written. Some symmetrical distribution that's normally shaped. Should be symmetrical, but I'm not very good at doing it. What do we have in the middle? 25. Not very good at drawing fives either, am I? Fives and threes. Fives and threes I can't do. And we're asking the question about, what was it, 20, what number was it? Where's it gone? 24.94. So let's draw a line here. And that can represent 24.94. We're going to find out basically where that line is. So to do that, let's ask ourselves in the calculator, what do we get? The mean has changed, 25 now. Standard deviation has changed too. If we have a look, what is 16, well, 0.16 squared on 20? Like looking over here, yeah. This thing. Again, that's sigma squared. So it implies sigma is going to be the square root of that thing. 0.0358. Move you over. Come on. There you go. 3, 5, and an 8. Double check that's right. Just to not bother doing anything, waste of time. 16 squared on 20. Yeah, it looks fine. They don't seem to write it down in here because obviously you guys won't use it, will you? You'll just use the fraction form of it. I'm going to assume that's correct, and we'll keep going. So from here then, let's work out the chance of us actually getting the weird value we've observed, the 24.94, or something more extreme. We're on the left of the mean, so it's going to be like that way. This as well as well should be the mean of these. That's the mean of that stuff. This then, calculator. We put in those values already, didn't we? Yep, we've got the mean. Standard deviation needs to change. It needs to become 0.0358. And we want to be below 24.94. What's the chance of that? 4.69. So, that's what we've learned then. Move this over a little bit, because it's actually quite small, isn't it? We have, this area is 4.69%. We were asked, for doing some maybe green over the top, to find, not to find the region, but to like see which side of this line we're on. That green region is 5%. We're inside that green region. That green region is our critical region. It's telling us any values in there are so unlikely. There's a less than 5% chance, because that's what we specified. Less than a 5% chance of those happening just randomly. So if they do happen, there's probably a reason for it. And what we've just shown then is that we should probably go and investigate that reason and find out why. Is it actually just random chance? Or is there something deeper going on? So let's just write it down. That number, what was it? 4.69%, wasn't it? So 0.0469. This is less than our threshold of 5%. So we have sufficient evidence to believe something funky is happening, and we're going to reject H0. We reject what we already thought because we've seen too much funkiness. Yeah, thank you very much for watching so far. I'm going to keep going in the morning. I think it is now 2:30. At least what's good, if you are watching this, like to watch the whole thing, I'll speak now while it's at the middle of the video. I figured out a new way to edit stuff. What I was doing before was just very slow. It was taking longer to edit and process than it was to film and do, which is not good. So my goal is now, like, I knocked it down from being, it was taking me about an hour and a half to do an hour. The last one took about 15 minutes, like start to finish, upload everything, do you know what I mean? So that's much better. So fingers crossed this will actually be out, even though for me it's 2 a.m. it may well be in like 12 hours from now in real time that you're actually able to see this, which would be good. Happy days. I will see you for you right now. Right, next paper then. Let's keep going. George throws the ball at a target 15 times. Each time he throws the ball, probably hitting the target is 0.48. Random variable x, number of times he hits the target 15 throws. Find, he does it 3 times. So what do we have? Probability of success. Where's my keyboard? There she be. 0.48, yeah. 0.48. Number of trials, how many times? 15. 1, 5. And we're looking at 3. What do we get? When we equals that top row there, 0.01967. Looks good. Now bigger than 5. Let's change that 3 to a 5. Well, bigger than or equal to 5, yeah. What does that give us? 0.80952. He now throws the ball at the target 250 times using approximation. Okay, on this one then. So if we think about having a number line where we've got x, yeah, going across, and let's have imagine that we have the normal and the binomial. So the normal is continuous, but the binomial is discrete. So if we think about like what is 10 for the binomial, well, let's do the 110, yeah. What's 110 on the binomial? It's anywhere from 109.5 to 110.5. So if we want, in terms of the binomial, to be more than 110, that is that section. It's not these two. So in terms of the normal, it's the same. Binomial, bigger than 110, is normal bigger than 110.5. So we should have some, like, say, y distribution is normal with a mean. It's going to be n times p. So it's going to be equal to the 250 times by the 0.48. What does that give us? 250 times 0.48, 120. And then we times that by q for the standard deviation. So it's going to be np times 1 minus p is that q. Chance of it not happening. So it's going to be the 120 times by 0.52. That looks good. What do we get? 62.4. Look at that though, way too big, yeah. So this is, well, it looks way too big. That is the variance. So not the end of the world. What we're going to do then, we are going to now find out the probability that y is bigger than the 110.5 that we just did. So to do that, we need the calculator. Let's go over to that one. Normal distribution, our mean, what did we have? Mean 120. Standard deviation is whatever the square root of that is. So that's sigma squared. So sigma is root 62.4. In your calculator, you can probably just type in the square root, but I can't on this online one. What do I get? I get 7.899. So let's put that in there. 7.899. And we want it to be above 110.5. Recalculate, we get what, 88.55%? So 0.8855. Is that good? It's very good. Lovely. Let's keep going. Number 2. We're making rods. We have the rods are normally distributed. So L is normally distributed with a mean of 8, standard deviation of x, so x squared in there. Given that the proportion amount of rods less than 7.902 is 2.5%, show that that's true. So what we can do, we can write down the probability that L is less than 7.902 is equal to 0.025. So we're able to use like the inverse normal stuff. Or just actually the inverse, the inverse normal. Yeah, the inverse normal stuff. I was thinking about the standard normal, not the just like a general normal with any unknown stuff. But what we have, we're going to have 0.025. The mean we knew was 8. Oh, we don't know one here, do we? So we will have to use a standard normal. Let's set a mean of 0. standard deviation of 1. So yeah, what we can write down, in general, there's some notation. Z is something that is normally distributed with a mean of 0, standard deviation of 1. So we call that the standard normal. Standard normal. Why it's useful, it's basically a transformation. If we take in any value that we did have, x, I'm actually going to use L here. L, and we take away mu, divided by sigma, that gives us the general distribution that we have, the standard normal distribution. So yeah, showing that we can kind of just move the standard normal over to the right by mu, enlarge it horizontally by sigma, takes it from just being have a 0 and 1 to the mean and variance in there. So that's good. How do we use this then? Well, we have this kind of shorthand. If we have phi of z, that's a way that we just write down. We've worked out, like, imagine using the calculator normally with 0 and 1. Do you mean you've done that stuff? What do you get? So we can use then the inverse of that, the inverse standard normal of the probability we have, 0.025, so 2.5%. That gives us a number. When we do this, what do I get if I go below? You can see I get negative 1.96. And that's going to equal then, so the negative 1.96, that is our z. So it's the z part of this equation. The L value we've used there was 7.902. And we want to take that away from the mean, so 8, divide that by sigma. So sigma should be the difference that we had, 0.098 over sigma. Sorry, over 1.96. Just by swapping those over and get rid of the negative that was there with the one that does appear from the top. So what do we get from that? Let's do that division. 0.096 over 1.96. And I get a number of 0.0489. Well, it's 90490. Does that look good? Question number 2. What do we get? Yep, looks very good. Lovely. What does the z actually represent? This number, this z. So this is z, yeah. It's how far away is our value from the mean, but when we measure it in terms of standard deviations. So we have like this value. That is in terms of, so it's the difference or distance away, distance from mu in the units we had, centimeters. The z is the distance from mu, but in standard deviations. I'll write that a bit neater. So how many standard deviations from the mean are we, as opposed to just how many like units of x are we, or units of L in this case. So that's good. You always need to use that one if you don't know one of the values. So we didn't know what was going on up there. We had to do that to figure it out. I'm going to get rid of that x and just call it sigma. I've only called it x up there. Didn't call it x anywhere else. So sigma squared. Lovely. That is good. Using that then, we want to find the proportion between 7.9 and 8.09. So let's set this back up on our forward normal. The mean we had was 8. Standard deviation was very small, wasn't it? Yep, 0.049. And we wanted be, where was it? Between 7.9, 7.94 and 8.09. That should be quite a large number. You can see on the graph on the left, like how much we're taking up, like how much space that's actually occupying. So yeah, quite a large amount of it. So what did we get? 85%, 86%. I'll just write that up here. So it should be 0.8565. Yeah, that's good. And there was our answer as well. Lovely. What we have now then, the cost of producing a single metal rod is 20p. A metal rod that's too short is sold for scrap, it's for 5p. Good size, 50p. And if it's too big, it gets shorn for 10p and then sold for 50p. Get an expected profit per 500. Okay. So tree diagram, what can happen? We can make one that is too short. Was it 7.94? We can make one that's just right. Goldilocks zone, yeah? 7.94 up to 8.09. Did it include the short end? It did. It's a normal, so it doesn't really matter about including either end. And then we want to be bigger than 8.09. So from that, we can get all like how much money we get out of it, yeah? So if it was too short, what happens? We scrap it, we get 5p. If it's just right, happy days. Sell it normally, 50p. If we go down the bottom end, we have to spend 10p and then we make 50p. So we make 40p, yeah? 50 take away a 10 gives us 40. So let's just think about the actual like possibilities of getting down these branches then. The chance of getting a small one, did we just work that out at some point? No, I don't think we did we? No. We've gone down and we found the middle value though, we did find was this number, 8565. So 8565. 0 point that. We need to work out the branches of the other ones. So let's actually work out now. Doing the same stuff, but we want really like this branch on the top is the probability that L is less than the 7.94. So let's do below 7.94. What number do we get? I got what, 11% basically. So 0.1104. These are the only three options. You could obviously now just do greater than 8.09 on the diagram, but it should be the same. So if we do like 1104 plus 8565, do 10,000, take away that number, and I get 331. Like it should be 0331. So let's just double check on here. If I do go above and then get 8.09, what do I get? Hopefully something 331. 331. So that's good. Either, yeah, these still add all to 1. It's still the same rule, like the sum of probabilities is still 1. Still the same case here. This is like, it's a tree diagram, yeah, but there's no other option, yeah. Like when this happens, we do just sell it. We do just sell them. We do sell it every time. So there's like, there are probabilities here, but they're just 1 everywhere. We don't need to worry too much about that. Nice. So how much money do we get then? Well, expected value, you want to add up all of those values you're going to expect and the probabilities of expecting them all. So that means that we're going to have like 5p. I won't do the p's everywhere. We'll have 5 times by the chance of getting it, 0.1104, plus 50 times by the chance of getting that, 0.8565, and then plus the 40p we can get times by the 3's at the end, 0.0331. Lovely. We then just add those all up. 5 times 0.1104 plus 50 times 0.8565 plus 40 times 0.0331. We get 44.701. Does that look good? What question was that? That's C. Did it say anything about how many did we sell? Oh, it's per 500. So this was going to be our expected profit per rod. Yeah, every rod that we sell, like the average price we sell them for is 44p and 7, like 44.7p. So we want to take that value, not just have that as the answer, but we'll times it by 500. So 500 times by, yeah, 44. Did it want it nearest pound, did it? What did it want for the answer? Yeah, nearest pound. So we'll do pennies first, and then round it. So times by 44.701 times by 500. I get, is equal to 22,350. It's not too bad, is it? And 50p. So we round it up, 22,351. I might have rounded somewhere else. If your answer's close, then you're right, aren't you? Oh, it's pennies, isn't it? Yeah, it's pennies. So actually, it's even easier to round because we round not to the nearest pound, but to that one. So it's going to go up to 400. Yeah, should be 224. Is that right? Am I wrong? Am I really wrong? What's happened? I've ended up being exactly. It seems too close to be wrong. Let's just double check what's happened. Have I forgotten about the profit for how much they buy them for? Yeah, sorry, they need to take away, don't they? So we're going to have this is our revenue. So that was our revenue down there. We spend 20p for each one. So 5 cost a quid. So it's under a quid that we lose, yeah. So we do that. And we will take away 100, take away 100, take away 100. And we're left with 124. Is that good? No. We're slightly off. 112 they have. What's gone on Have I just? I'm assuming I've just done some of the sums. Some of the numbers are slightly wrong. Do you know what I mean? Let's double check. Like some of my calculations, maybe. So we can do either this way round, 50. That one's good, and this one's good. This one is wrong. So I think, yeah, I've just got this number slightly wrong from here. So what do we have? 7.94 and 8.09. Yeah, between them. Calculate. 8565. Why have they got 849? For all the rights. I did get all the same numbers, didn't I? Mean of that, standard deviation of, unless they've used. Yeah, okay. So yeah, we did everything right. They've just used the actual value, like the assumption. So it says show that x was equal to 0.05. I used this value instead. You'll get all the marks either way. I mean, either way you've done it's fine. So just to get you the answer that does change, you get 122 out if you use 0.05, and we get 124 out if we use 0.049. Same steps. That's what always matters, is the steps, not about the actual answer at the end. It's like for your learning process. In the exam, obviously the answer matters, but when you learn it, it's all about the steps. So that was good. Let's keep going there. Number 3, what do we have? Use the large data set, investigate total rainfall for Camborne. Write down how a value of blah, blah, blah is recorded in the large data set. They just write TR, don't they, for trace. Yep, you can't write trace, just important. Oh, they do allow. Okay, they do allow trace, they do allow. So let's keep going. 31 days of August for Camborne. It calculates the following stats. Find the mean. So the mean itself, x bar, well, r bar in this case, isn't it? There's r bar is equal to the sum of the r's over n. That number is 174.9 divided by 31. Whack it in the calculator. What do we get? 174.9 divided by 31. 5.64. Lovely. So for the standard deviation then, we want to do the sum of the squares over m minus the square of the mean, and square all of that stuff. So we have the big number 352.283 all over 31. Take away the number we just found, 5.64 squared, and then we square root that whole thing. If we do that, then what do we get? So 3523.283 divided by 31. Take away 5.64 squared. Square root the answer, and we get 9.05. Do they look good? They do. Always just double check about like sig figs, but I don't see anything on there about them. So I'm happy with that. What's next? Diane, wherever he's called, believes that the mean total rainfall in August is less in the south of the UK than in the north. I'd assume so too, Dean. The mean rainfall in there was Scotland somewhere, isn't it? Even though it looks like it should be France, doesn't it? This number, 1.72 to 2 decimal places. State given a reason whether this provides evidence to support his belief. It doesn't. No, he's not comparing it to anything, is he? He's just got one data point from one place and one time. That doesn't mean anything. That just means it was raining this much in that place at that time. Doesn't tell us anything else about it. What have they said though, to make sure? Oh, do we have stuff about Camborne? Was he comparing it to Camborne? Oh, okay. These values are for Camborne. That makes sense. So, okay, in August we had that, and in Camborne we had this, and in Scotland we had that. Camborne's in the south, yeah. It's in Cornwall, and Luchar's, I think it's in Scotland, isn't it? Yeah. So what we have north here, less than south. So north less than south. So that is like the opposite of what you're saying. So that is implying like it doesn't support it. Yeah, no evidence. And yeah, so north is less than equal to south. Okay, yeah, that's enough. So just one, like, we get 1 mark for noting, like, Campbell's in the south, and I'm going to call it Luchar's. Luchar's is in the north. And then the other fact for kind of spotting the comparison of the actual rainfall themselves. So Camborne being higher than the Luchar's one. So that should be good. Part D then, down the bottom. Large data set to estimate the population, so proportion of days with no rain in Camborne for 1987 to be 0.27 to do this in places. Explain why the distribution might not be a reasonable model for the number of days without rain for a 14-day summer event. Well, what do binomial need? We are going to assume that we have constant p and n. Well, fixed, and not constant, but fixed. You know what I mean? Do we have both of that here? Well, we do definitely have fixed n, don't we? If we're just looking at 14-day event, that's okay. But the p, that's not good. So because we have constant p, like this is not really possible in real life. So this is actually like not possible. How they phrase that, yeah, it's unlikely. This is unlikely. It's not possible. Not probable is a better way to phrase it, isn't it? Not probable. That's what I should be saying. Prob, bab, blah. Yeah, looks good. Nice and straightforward. Let's keep going. A dentist, he knows from past records that 10% arrive late for their appointments. Okay. Please, there's been a change. Yeah, so there's been a change. 10% up there. Random sample of 50. Write down a null hypothesis. Yep. We believe that there's been a change, don't we? But a proportion who arrive late. So he's thinking, or she is thinking, that there is a change in the probability. So 0.1 is our original thought, and just not equal to 0.1 will be our alternate thought. That looks good. Yeah, corresponding to no change in the proportion of customers, and alternate corresponding to manager's belief. Yep, looks good. Use a 5% level, find the critical region for a two-tailed test of the null hypothesis. State the probability of rejection in each tail, which should be less than 0.025. So, what do we need to do then? Let's think about our distribution. We'll use t, and we'll say that t is going to be distributed binomially. We've done a sample of 50 people. Probability is p, but we'll write 0.1 because that's the one I'm actually going to use to do observation, or like to actually find our critical region. So, the shape of the distribution is going to be something like this, where we've got a long tail to the right, because we're going to do 50 of them, but we're going to get 10%. 10% is our chance of success. So on average, we'll get 5, yeah? So this peak should be around 5. And what we're effectively looking for is a critical region. So we can draw a line here, and we can draw a line here. And we're going to have some no-no zones. You go in the no-no zone, you're in the no-no zone. What is a no-no zone? It is basically anywhere where we would change our mind about what we thought originally. So we believe 10% are late. There's going to be some amount. If you've got like 20 out of 50 people are late, you're like, whoa, that's probably more than 10%, isn't it? Maybe we're wrong. Saying this way, maybe you've got nobody being late. Maybe it's less than 10%. So we're finding basically what zones would, what numbers, what percentage of people being late, and this time, like what actually number out of 50 people being late are going to make you change your mind about what you thought originally. How do we find that? A little bit trial and error. Annoyingly, we're going to have to find a couple of numbers. They're the critical values, is what they're called. One of them is there, crit value, and the one's here. They're the first ones. Like if you are stood at the mean, so the mean somewhere in the middle, which is going to be, in this case, will be 5, but that is like, yeah, the mean. If we're stood there, what's the first one you see in the no-no zone? So how do we find those? We're going to go down and basically look at some numbers. So the probability of x being, let's start on the left, less than or equal to, let's just do 0. So it's the same as 0, yeah? What number do we get? So we want to go to a binomial one. I'll get rid of some adverts. There we go. And we want to do probability of success is 0.1. We're going to do it 50 times. And let's start with a 0. We're basically looking for, we have a two-tailed test. So the 5% we were given, go away adverts. 5% we were given is going to get split into 2. And each one will be about 2.5%. 2.5% and 2.5%. So they add up to 5 in total. One-tailed test, you'd have just one big continuous region, like one would be double the other one, do you mean? Well, not double, this would be 5, this would be 0. How we know it's two-tailed, just about the change, they didn't indicate a like direction of the change. Is this percentage decreasing or increasing? Didn't specify, we're not sure. We look either direction just to be safe. So let's look left first. When we do these bits, what are we going to get? If it does it. So the probability, if we look at this row, is like 0.5%, yeah? We're looking for 2.5%. So maybe we're too small here. We change this 0 to a 1 and do the same thing. We get 3%. So actually this is perfect. What we have, less than or equal to 1 is that middle number, 0.0379. And the one above, what we had, it was 0.00516. If I just move these over a little bit, it'd be a bit easier to kind of write down that. What are these? Well, the top one is 0.516%. And this one is 3.79%. So let's make the top one 5.2. Just to have two sig figs, or two decimal places, I suppose. Mainly, we don't care about those numbers, but what we do care about, 2.5%, is slap bang in the middle. So when we go and look over here, we can get rid of the critical value thing. It still exists, yeah, don't get me wrong, it's still there. But now we know it's 0 there and 1 on that side. So 0 is the critical value. And actually, on this side, it's also the entire critical region. Critical value. So that's good. Same thing the other side then. I started this side, there's less options in there. 5's the middle. It's going to be like 0, 1, or 2, isn't it? Now, though, I know it's 5 away that way, so I'll try 10 first, the other side. I'm not sure if this will work, but that's where I'll start. And note now, I'm doing bigger than or equal to 10. I'm always looking at more extreme, 10 or more extreme. By more extreme, like being further away. So it's like 10 all that way. Like trying to find the area of that whole blue region. See what I mean? Not just like this area. If it was just that area, that would be finding like the equals in there, yeah, which is what we do not want. So change our 1 up to a 10. What do we get? Bigger than or equal to 10, or 2.45%. 0.02453. So yeah, 2.45%. And that's too small. So we need to go one step to the right, yeah? Have a look at 11. We could just type in 11 again, but if you see it's going to be like greater than or equal to 11, it's the same as greater than 10, which I already have on this page. It's there, yeah? So 0.00935. So that is 9.35%. No, it's not. 0.94%. Oh, so I stepped the wrong way. Sorry, silly. We should have gone down to 9. Apologies about that. Does that make sense? Like we were too small, weren't we? I needed a bigger area. Let's just clarify that. I was stood like here, looking this way, being like, oh, I can see 2.45%. So I know it's going to be 9. Like it will definitely be 9 here. So let's do that just to confirm. 9 then, what did we get? Greater than or equal to 9. This bottom row, yeah, 5.78%, 5.79%. 5787. So 5.79%. So again, yeah, this 11, just to clarify, did not need that. I had a number very close to 2.5%. I want to make sure I saddle it, and I just set the wrong way. So get rid of that one. Again, 2.45 and 5.79 have 2.5% in between them. So what that tells us then is similar sort of idea. The 9 is the last number on the left there, and the critical value is 10. Our critical region then is either x equals 0 or x is greater than or equal to 10. I suppose we can only be as big as 50, can't we? So we should really write that it's going to be anywhere from 10 to 50, including both of them. All makes sense, yeah? I'll show you quickly how to do this as set notation. We needed to have whole numbers out here, couldn't we? Yeah, we can't get out of 50 people, you couldn't have half a person. So we had to make sure that we were a natural number. You could do integers here, doing the z, but this is going to stop off any like negatives possible. We can either be 0, or what we can do is have the 10, the x, and the 50. So either having like that range, or having just 0. Yeah, we don't need to tell like what type of number it is, because that's just 0, isn't it? So that is just a set containing literally just 0 by itself. So that would be fine. This is the set of all the natural numbers that are between 10 and 50, including 50. So all the whole numbers between 10 and 50, including 10 and 50. This is the number 0. so any one of those is fine, yeah. That's good. The actual significance level, if we look at the two ones that were the ones smaller than that, so this normal number, the small number, and that one. So 0.52% plus 2.45% is equal to 2.97%. Basically, that's the area of the critical region, or like the probability of being in the critical region. It's being part of the critical region. So it's the smallest value. If you think about the 5% level we had, it's the smallest number you could pick there, and we'd get the same result every time. Because what we found is this set of numbers, so 0 or 10 to 50, if we observe that number of people out of 50 arriving late, what we'll think is that we no longer believe there's a 10% amount of people arriving late. Because either, if it's 0, our estimation is too high, and actually we need to think there's less people than that arriving late, or we're observing something that's actually seeing a lot bigger percentage, at least 20% or 100% of people are late. So we need to adjust it the other direction. And what this is showing then is we could shrink these areas down. This side, instead of being 2.5%, you could make it 2.45. And this side, instead of being 2.5%, you could make it 0.52%. And our critical region would be the same. Every input to our test, I got 17 out of 50 being late. That means that we change our mind. We got 8 out of 50 being late. That means we don't change our mind. Every input, output like that is not affected by reducing these down, taking these blue lines to exactly 10 and exactly 0 there. That's what we're saying for this value. What's the smallest area we can have that is blue, where we have exactly the same outputs for exactly the same observations? So just add up the two tails. 5.2, 2.45 makes 2.97. Lovely. That looks good to me. Let's just check everything is correct. Yep, 2.97. Next one then. They observed 15. So yeah, that's in our critical region. So we would reject the null hypothesis. So 15 is an element of the critical region. So that implies we reject the null hypothesis. Always write this in some context. So for example, like 15 is an element of the critical region. So therefore we reject the idea that only 10% of people are late. There's actually a different percentage than that. Even though what we've spotted is bigger, we haven't actually shown that. We have really, because it's smaller, but like it kind of depends how you view it. Like we've shown that it's just a change, but we know that it does fit in that region. We haven't really said it there though, do you mean? This has said it's in one of the blue regions. We do know, just like from common sense, it's in that one. So we have shown it's increased, but you see what I mean? Just that phrase itself doesn't specify like which one of those it actually is inside. That looks good to me. Well, let's keep going. Got some table now. 1825 employees. They're professional, skilled, or elementary. What have we got then? They live in 2 different areas. Okay, some two-way table. Find the probability that they are skilled. Okay, how many skilled ones are there? 275 plus 90 on 1825. Does that look good? Yep, that is good. So it's 1/5 altogether, 20%. Let's actually write it as 0.2. They live in area B and is not a professional. So area B and not a professional is over those. So 90 plus 80 on 1825. Right, next one then. We've got all this information and we want to fill in the Venn diagram. Weird enough, it's easy actually to go up here and try and get some bits. So 65% of professional employees, let's look at this top row, in both areas work from home. So let's work out actually a total. A little column for totals first. What are we going to get? For the top row, 740. Oh, not log. 740 plus 380 gives me 1120. 275 plus 90, so 365, and this will give me a 340. And then what I want is of the professional 65%. So 1120 times 0.65, I get 728. This is home, yeah? People that work from home. 40% of the skilled ones work from home. 365 times 0.4. What does that give us? 146. And the elementary, 5%. 340 times 0.05, 17. So that's good. Let's go and fill this in then on the diagram. F is professional, So why is it not P? Who knows? And H is home. That's good. That makes sense, doesn't it? R for A, obviously. Let's change the R to an A. I will change my H to a H with blue, though, just to make sure I don't get confused by that. What things did we know? Well, professional from home is 720. So if we call this X and call this Y, all those bits, X plus Y, plus the 1, 2, 3, and the 2, 4, 7, i.e. everything inside the home circle, must be like the sum of all these, yeah? 728 plus 146 and 17. Let us collect some tight terms. What we're going to have, well, if we do the 728 plus the 146 plus the 17, we'll take away the other ones on the other side, the 1, 2, 3, and the 2, 4, 7. I get X plus Y is 5, 2, 1. Which looks good. So, from here then, we can do very similar things with the other bits that we are going to know about. What do we need to find? Let's label this one as Z and this one as alpha. Anything else we know? Let's think, what do we have? What is the middle bit? These are people that work from home, A, and they're professionals. So professionals from home from A. Professionals from A, we don't know. But do we know professionals, which are these ones, in A are those. So professionals from home are these. Professionals from home is 728. Aha. So 2, 4, 7 plus Y. That's all the professionals from home, yeah? Because we're in the professional circle, we're in the home circle. So that must equal home professionals, 728. So therefore, Y, what we're going to get for Y? 728. Take away 247, I get 481. That can go the row above then as well. We can get the X straight away is 40 in what am I doing? So yeah, that's 40. Let's do it in red up there. This is going to be 481. Oh, did we know about A's then? Yeah, we know about A's, didn't we? All the A's, let's add all those up. All the A's, what do we get? 740 plus 275 plus 260. I get 1275. 1275. So that's all the A's. From that then, what can we say? 1, 2, 3 plus 481 plus 412 plus Z is equal to that 1275. So doing a quick sum, taking away 1, 2, 3, take away 418, take away 412. I get 259. That looks good. That's going to be Z. What am I doing? Z is 259. Lovely. That goes in there. And now then, just add them all up, take them away from one, what we were given altogether, weren't we? 1825. What's that going to give us? 130 if we do it. Lovely. Any more? Okay, find some of these bits. So not R, intersection F. We want the union of H and R, but not of that. And then F given H. Okay, let's go have a look. Top one then, not R and F. Let me rub out my letters so I can see the old letters again. We want to be in F, don't we? Yeah. So I've got to be in the circle and not in R. So those bits, because I can't be in R, can't be in that circle. So what do we get? Needs to be the probability of those, yeah. What numbers are they? 247 plus the 133 over how many there are together? 1825. We will get some number for that. What number do we get? Yeah, it's 380 on 1825 is about 20, 0.208. So that's good. For the not one here, let's move that out of the way a little bit. So H or R, H union R is that, yeah? So not that bit. Just those bits. 133 plus 1, come on, 30 over 1825. Plugging that in, what do we get? 144. Do we have any more than this? Yeah, okay, I will plug that in now. Where's my charger? There should be. Do you charge? Let's find out. You do charge. Wonderful. So, more maths for us. What do we need? F given H. Well, probability of that is the same as the intersection, isn't it? F intersection H over H. Oh, excuse me. So F intersection H. I've got F there, H over there. Intersection then is going to be the 247 plus 481. And the H itself is all of those numbers in it. I've got 40 plus 123 plus 481 plus 247. And I get out of all of that 0.817. Let's make that a different colour. Colour in blue. Looks good. Looks very good. Nice. Last one on this paper then. What do we have? Some scatter plot. 19 of them all together. We got heart rate, and we got the amount of exercise they do. Blah 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 blah. Obviously exercise over here. This is going to be heart rate. Type of the nature. So it's going to be some like inversely proportional. Inverse proportional. What have they said actually for the words? They didn't actually use that phrasing of it. So all they're saying, they've got even more simple. Do you know what I mean? As one goes up, one goes down. So over the top there, and it's not like inversely proportional. You might not know that, like it's 1 over something, but it looks kind of like that, doesn't it? So what they're saying is like as m increases, that implies that h decreases. Nice. They're coding the data. So we're taking log of base 10 of both of them. The coefficient of the PMCC after those logs is negative 0.897. Find correlation stuff. So our null hypothesis is always that there's no correlation. Our alternate is always that there could be. Let's see if, of a negative correlation actually. So we're going to look at going to the negative side. So less than 0. This is good. Use a 5% level. So alpha is going to be 5%, which is 0.05. Our sample size was 15, wasn't it? 19 even. 19. And the observation that we had is negative 0.897. So let's go to the formula books. In there, and then in the back of the book, we have this little table. We want to find number 19. So we have sample size on the row. Let's go down to where it says 19. Lovely. And then we need to think about, is it one-tailed or two-tailed? We were looking directly at negative, so it's a one-tailed test. So no need to like split it in half. We'll just go to the 5% one. And then 19, yeah. So it should be 3887. Am I getting that right? Let's make sure from the book that is the correct one. Yep, 3887. 3887. We look at the size of these numbers. And what we have is that the observation is much more strange than what we're saying can just 5% happen randomly. Like 5% chance of just randomly getting that correlation. So here we are going to reject H0. What we saw is very unlikely. Very unlikely to be that correlated as randomly. So we're saying that it can't have been just random. It must be correlated. So that looks good. Next bit then. State the critical value used. Yep, that was this value and this value, was it? Is that what we needed? Double check. Looks good though. Yeah, it's just that one. So this is good. So that's the critical value. We have this line of best fit now. Use equation of the line of best fit for the model for H on M in the form of this. Okay, is it just going to be rearranging into that? Yeah. Yeah, so let's see what we had up here and replace our equation. So we just want to basically rearrange for like, take this thing and rearrange for something like that. This is charging. So y is equal to log of h, and we're going to have that then set equal to negative 0.05 of x, which is log of m. Move this all over a little bit. Plus 1.92. So take an e, well 10 to both sides. H, or you could 10 to the power of this stuff. 10 to the power of 0.05 log of m. We can have this like plus over there, or just times it by 10 to the power of this again. 9.2. And from here then, we can use the log laws. This one, we can basically like rearrange this. They're times together, yeah? So you can basically do that to the power of like the other one. And then the bit inside there is just m. So h here is going to equal to m to the power of minus 0.05 times by this 10 to the power of 1.92. The m itself, what will happen is going to be like, yeah, it's just in there, isn't it? So is that all good? H m to the k. Yeah, I think that's fine. We should obviously get the decimals out that we need, whatever 10 to the 1.92 is. Let's have a look. So that should be 83.17. Yeah, is that all good? I think so. Are we done? We are. I'll let this charge for a little bit. I'll see you in 5 seconds. Right, let's keep going then. What do we have in this one? Some Venn diagram. Find the probability of A. Well, just add these two together, yeah. So 0.38. B and C are independent. So we know, not A, sorry, B. When we times that by the probability of C, we will get the intersection of the two. So in terms of the bits we've got up there then, probability of B, you got 5 and 30, 35, plus another one there is going to be 60. 0.6 times by C, which is 0.3 plus P, and that needs to equal the intersection of the two, so 0.3. So thinking about that, 0.6 and 0.3, dividing that over is a half. So 0.3 plus P must equal 0.5. So P is 0.2. That looks good. That looks good. What about Q? Well, let's add them all up. 13 and 25, 38, 43, 73, 93. We must have 7 left over. Does that look good? It does, yes. A given not B then. So we want A intersection, not B, over not B. Doing that then, what we're going to get, A and not B is that bit, just the 1.3. 0.13. Not B then, well, didn't we work out the probability of A? Sorry, probability of B. Maybe we did, yeah, 0.6. So not B, 0.4. What does that give us then? 0.325. Lovely. Next one. We've got 1/7 of a pack of sweets contain a prize. There are 40 packets of sweets in each box. Let's do this. That's P. That's probably N. Yep. So, exactly 6. What we're going to get? Let's go to our binomial calculator. We have a probability of 1/7. I can't do fractions, I don't think. Whenever it lets me write anything. Oh, hide keyboard. Show keyboard. There we go. So 1, 4, 2, 8, 5, 5, 7. That'll do me. Here we had 40 of them. And our successes we wanted were 6. Press little calculate. Come on. Nope, it's not having it. Well, what number do we get? It should be, when I go to the right page, 173. 0.173. And then fewer than 3. So that doesn't include 3, yeah? Wait, let me change this. Let's see, let's try again. 3. Press calculate. No, I'll try to refresh it. But what we got from the book anyway, well, from the mark scheme, we should get 0.0616. That's just a case of looking up from the calculators, isn't it? So next one, Camille Sweet Shops buys 5 boxes of these. Find the probability that exactly 2 of these boxes have fewer than 3 packets. So exactly 2. Well, we have a new distribution there. Let's call it Y, where it's like the chance of a box having fewer than 3. We're going to have that normally distributed where we're taking 5 boxes. Each one has that 0.0616 chance. And now we want the chance of Y being exactly that. Exactly 2. So probability of success, 0.0616. Number of trials is 5 for the 5 boxes. And successes we want 2 out of those 5, don't we? Leave that up there. Let's calculate. Okay, it's working now. So exactly 2. 0.03136. Is that good? Yes, that is good. Next one then. Camille claims the proportion of packets containing a prize is less than 1/7. Less than. Random sample of 110 taken. 9 packets containing a prize. Okay, so we're going to have some distribution. Binomial, where we're doing 110 packets, and he believes it's 1/7, but so yeah, our original thought is 1/7, so P is 1 on 7. His thought then is that P is not going to be 1/7. He thinks it's less than. Okay. He thinks it's less than 1 on 7. Alpha then, our significance level, is 5%. We were told that. So 0.05. And his observation is 9. So thinking about what is 1/7 of 110, it's about 20, and it's just less than 20. More than 9 though. So we have to draw it out. Some distribution. Well, our mean, our expected value, is 110 divided by 7. Like a 1/7 of 110, yeah. We get 15.7. So where we have the 9 is definitely on this side, isn't it? So looking more extreme, x needs to be less than or equal to 9. Lovely. What do we have? So probability of success is a 7th again. So 1, 4, 2, 8, 5, 7. Number of trials we're doing is 110 now. Successes we wanted were 9. We want less than equal to that. So it's the third row down. I get 0.03829. I make it 2. And the main thing, that number that we just had, less than the 5% threshold we had. So observation only had a 3.8% chance of just randomly happening. So that's quite unlikely. So what we say, therefore, there is evidence to suggest that we're going to reject H0. As always, put it kind of in context of this. So evidence suggests there's a less percentage than that, their probability than this one. All looks good to me. Let's keep going. We got stuff about the large data set. How are we going to clean the data? We have to remove the traces. Remove trace. We want all numbers. We don't want any letters, do you mean? No qualitative data, only quantitative. 184 values, blah, blah, blah. Find the mean then. That's going to be the 390 on 184. What does that give us? Number 3. What am I doing? 390 on there gives us 2.12. And then standard deviation, we are going to take the big number, 4336. Divide that by the amount there are, 184. Take away the mean, but we've squared that mean. And then we square root everything there. What do we get? 4.37. Looks good. Ben suggests using the statistic calculator here to estimate the mean. Blah, blah, blah. Why would it not be suitable? So it doesn't cover the whole year, does it? Only covers from October to May. So it's only October to May. Give a reason. How do you expect the estimate to differ from the actual annual one? Well, what we think about, like, what months are we missing there? We've only seen the summer. We've only seen the. What am I doing? It was the other way around, didn't it? It's October to May. May to October. We've only seen the summer. So because we've only seen the summer, not as much rains in the winter. So how do we expect the actual, like, daily one? If you think about the entire year, it should be higher. The actual value should be higher. So we only saw summer, and that has less rain. So actual is higher. Is higher. We estimated a smaller value because we only looked at winter. So only looked at summer for rain. Let's keep going then. What do we have? So heights of men from country A, or region A from country. Normally distributed with a mean 175, standard deviation 6.8. Okay. H normally distributed 175.4. 6.8 squared. We're going to find probability that height is bigger than 180. So again, use the calculators for this. Back that in there. What do we get? 0.249. Lovely. Student claimed the mean height of adult men for region B of the country was different from the mean height from region A. A sample of 52 had a mean height of 177.2. Estimation was the same. Okay, so null hypothesis, what we're going to have? Well, he was thinking that the mean height was different, just different, yeah? So the mean height, H bar, what he's going to say is, so the mean height, so it's going to be mu, yeah? Is not equal to, well, we assume originally that it's equal to the 175.4, and our new value then, we're going to assume it's not equal. Just talking about a difference, didn't give a direction. Look at that difference. Alpha was 5%, but we have two-tailed, so that's going to become 0.025. Observation we had was 177.2. So all we're going to do, we're going to find out what's the chance of us getting that observation or something more extreme. So us being either 177.2 or bigger. What did we get? We got 0.02814, and that number is bigger than 0.025. So what we're going to have, the thing we saw, isn't that unlikely? So we're not going to reject. We're not rejecting H0. The thing we saw randomly, you could just get like 2.8% of the time that happens. Our threshold for weirdness, 2.5%. We didn't hit that threshold, so not allowed. The p-value for this test is now if we take that number, double it, because it's two-tailed, yeah? So the p-value is like the actual probability we found. This is from one end, so we assume it's the same at the other end as well. 2 times 0.02814. So what do we get? It's going to be equal to 0.05628. Am I good? Yeah, 0.056, that's the job. Lovely, looks good to me. Let's keep going. Number 5. So they're playing a game, got a cup, ball, and a spinner, blah, blah, blah. So spinner, chances of landing on each of these different numbers. Then they're standing so far away, throw the ball. Okay, we got the chance of success here, depending on which one we pick from the first round. And, okay, the chance of us succeeding is the same no matter which one we pick. So, what we can say then, let's look at that as a tree diagram, might be the best way. What options do we have? Either we can pick the 20, the 50, the 80, or the 100. So bop, 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 bop. And they have probabilities of A, B, C, and D. And then from here, it's either do we succeed or not, but we only really care about succeeding, yeah? And these branches are all like success, given that we are on these positions. So they're all this thing. Success, given that we've selected those things for the first round. So they're all K on X, where X is that number. So this is K on 20, K on 50, K on 80, and K on 100. Nice. Where they tell us about this then, being the same value, whether like no matter what value of X we pick, getting like going to this state, at the very end success state, is the same no matter which branch we went down. So we can times them together. We'll have AK on 20 equals BK on 50. Not very good. B was it the first one? Yeah, BK on 50, which is CK on 100, and it will be DK on, CK on 80, and it will be DK on 100. DK, that's an 80. Lovely, that's always true. We're also going to add up, when we add them all up, A plus B plus C plus D, that should be, what's it doing? That should be equal to 1, because the choice, we had to pick one of them, yeah? All probabilities add up to 1. So we have these kind of set of equations we can then use to figure stuff out. C and B to figure out first. So select the bits of C and B. What we're going to get from those ones, Well, the k's can cancel straight away, yeah? No more k's in there. And then the 10s can cancel as well. So what we're going to get, b on, it's not a b, b on 5 equals c on 8. And we wanted c equals, yeah. So c equals 8 on 5, lots of b. That's good. Find the probability distribution of x. So that just means fill in this table. We've got that thing. We can do the same sort of like rearrangement then. What else will we get? Well, if you look at it, like the C, which one was on top here? It was the one next to the C. So we're also going to get the A is equal to, like the 5 goes with the B. Yeah, 5 goes with the B. So 2/5 of B, and D is going to be 10/5 of B, so 2B. Very similar things will happen then. We can get relationship with all the other ones, but now we've got rid of B. We can just find a way to write everything else in terms of B, so B doesn't really exist anymore. Let's try and get rid of C then. Can we write A and C together? Well, yeah, in the same way. Like A is going to equal to 2/8 lots of C, so a quarter of C. And we're going to have A is equal to a fifth of D, I think, looking at it. Because you have 2/10, so yeah, 1/5 of D. So now we've eliminated A. Last then, just get C and D together. So C is going to equal to 8/10 lots of D, so 4/5 of D. This is good. Using this then, we can go and write, let's just rearrange everything to be in terms of D. So that last one, D is going to be 5 on 4, lots of D. Up here, D is going to be, sorry, C, D is 5 lots of that. D as well is also, no, this is good, sorry, ignore me. We want to take the thing above, add them all up, but do the bits where we've got D's instead. So A is a fifth of D, plus B is going to be a half of D. C is 4/5 of D, and then obviously plus a D equals 1. Add up these fractions, 1/5 plus 1/2 plus 4/5 plus 1. What am I doing? 1 plus that is 2.5. So D is 2/5. So that's good. Let's go through and figure some bits out then. We know A is a fifth of that. So A is 2 on 25. B was a half of D, so that's 1/5. And we know that C should be equal to 4/5 of D. So it's going to be 8 on 25. And we can just double check, like write them all over 25. So that's 5/25. And D is 2/5, which is 10/25. So we had 10 and 2 makes 12. There's 17, there's 25. That's a very good sign. Bosh, 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 bosh. Do they all match up? We need to have A is 2 on 25, yes. 1/5, 8/25, and 2/5. Wonderful, looks good to me. Next bit then. Nav tries a large number of times to throw the ball into the cup from a distance of 100 centimeters. He succeeds 30% of the time. State, given a reason, why Tissam's model of this game is not suitable to describe Nav playing the game for all values of x. So what we can do is just use the equations, yeah? What he's shown is the probability of success, given that he stands at 100 meters, is 0.3. Did we ever figure out K? I don't think we did we? We can go through and get it. So let's think like A. No, we don't need it for a second, I don't think. But this is what we're saying. This number would be K. So K would be 30%. Like, does it match up with what we found earlier on? Can we? Did we find K? We're sure we found K somewhere. No, I don't think we did. But we can go and get it a different way of just like, okay, all of these. No, they don't, do they? No. How do we get K? Where does K come from? What have we done up here? So, okay, if we just look at doing one of them, probability of S given x equals 20. Do we get that number? This is like from the experiment that he's done. but we can go and have a look then. What would we get? Would be A, which was 2 over 25, times by k on 20. So what should that be? 2 over 20 is 1/10, so it's k on 250. So that should equal to 0.3. And that tells us then that k is 0.3 times 250, so it's 75. Sorry, that number's not k. That should be k on 100 times by d. What's gone wrong? Where we look at one of the probabilities, we get k as 30, yeah? That probability was k on 20, so you'd get 1.5. So we know, like, yeah, if we look at, therefore, like, probability of, we don't need these bits in the middle. Sorry, there we go. K says 75, either way, it's too big, isn't it? If you look at the probability of A, given, success, given that we're at A, or considering that we picked 20, that's k on x, or k on 20. So in this case, 75 on 20. That's bigger than 1. That's not allowed, so k cannot be 75. So this cannot work. Lovely, let's keep going. Medical research hours T for a patient stay in hospital. Okay, use histogram to estimate that. We have the histogram on this page from 10 to 30. So from 10 down to 30. Height of that 4.2 times by the width of 2 is 8.4. There we've got a width of 4 times by 4, so 16. Width of 4 times by 3.5, so 14. Now width of 10 times 1, so 10. So looking at that, 30, 40, 48, yeah, something like that. Yep, 48.4 is what we get. That is out of the 90 people in total. So what's going on now? Yeah, we're done. We just work out what that is. 0.5378. Lovely. That looks good. Next one then. For the 90 patients, we have all of this stuff for a normal distribution. Okay, can this be suitable? Generally on normals, it's all about it like being negative. So thinking about this, mean of 15-ish, standard deviation of 9. So this should go down to like 30 away, timesing that by 3-ish. 30 away from this. You think either side will be 30, do you know what I mean, from that number? So where we've got 15 in the middle, this is obviously going to stretch the negative. So no, not allowed. No, will predict negatives. Nice. We now have this thing. So frequency polygon based on this. X is tens of hours. Okay, show this is true. This is just by parts, yeah. If we have u is going to be x, so u dash is 1, v dash e to the minus x, so v is minus e to the minus x. Sticking that together then, the integral of all of our stuff is going to equal to u times v, so x e to the minus x, but with a negative. Take away the integral of u dash v, so taking away the integral of a negative makes a positive, e to the minus x, but then we do that integral and we get another negative out. So we have minus x e to the minus x, take away e to the minus x, plus a c, and then let's factorize that out. C minus e to the minus x, lots of x plus 1. So that's without any limits. If we think about doing limits of n and 0, we can take away our c's from everything. Still with the minus, don't we? But now n and 0 into these, n and 0. So plugging in n, what are we going to get? N plus 1, lots of e to the minus n, but with a negative. Plugging in 0, that's 1, that bracket. This is also 1, so it's just minus 1, yeah? Take away minus 1, or take away negative minus 1, plus is a 1. Looks good. Show that that's true. Okay, show that k equals 99. We've got this model. It's going from 0 to 4. So let's integrate that model, k e to the minus x from 0 to 4. It's a probability, so that should equal to 1. Without the k, it's just what we found, yeah? And n is going to be 4 in this case. So we can have that thing times by k. So 1 lots of, and now with 4 as n, so 3e to the minus 4. Sorry, 5, not 3. And that should equal 1. So dividing by the k, dividing by that bracket even, 1 over 1 minus 5e to the minus 4. What number is that? Yeah, 99.02. 07, sorry. Which is close to that line, isn't it? Not too far off. Lovely, that's good. What else have we got? Blah, 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 blah. Estimating this. Okay, that's just a calculator one, yeah. Whack in the calculator. Let's see what pops out. We get 0.649. And then using it to estimate this one, here, what you want to do, is it a few marks? No. Are we just integrating? Yeah, we are just integrating, aren't we? I'm not being silly. Yeah, we are. We're going to integrate that thing from 1 to 3 of like the thing that we found. So knowing that, like it's the same integral we've got above, isn't it? It's going to be 99 times the thing that we have, 1 minus n plus 1 e to the minus n. Tell a lie, that's when we plug in n as 0. So let's get rid of that bit. It's when we have the bit just above this thing, but we want to put, so duplicate that. Yeah, we want that thing, but now with 3 and 1 in there. So doing that, what we're going to get 99 at the front. Putting in a 3, we're going to get minus e to the minus 3, and there's going to be 4 lots of that. And then minus minus, so plus. Putting in a 1, we'll have 2 lots of e to the minus 1. Does that look good? Yes, it does. Yes, it does. And that gives us a number of 53. 33.1. So 53. Looking good. Looking good. So I'll say, estimate this, the probability then. So if it's 53, what am I doing? Yeah, we divide it down by 90, don't we? So we want this thing over 90. So 0.59. That looks good. Let's steal the blue circle. Put you on there. One limitation of their model, it's got an upper bound. Stops at 4. Yeah, we could be there longer than 40 hours. So yeah, we might stay longer than 40 hours. So we're not able to model it longer than that. I don't want to be waiting in the hospital more than 40 hours. Mine, not good. So how long are we staying at? Yeah, not good. Is that all done? I think it is, isn't it? Yep, I've got one more paper. Let's get going. They're rolling a fair dice 10 times. Let's get the mark scheme up quickly. 2024. So it's going to be a dice, isn't it? We have something x binomially distributed 10 and a 6. So I'm getting exactly a 3. Well, say it again. You're getting exactly 3 6s. Whack it in the calculator. We get the number of 0.155 less than or equal to 3. We get 775. Looks good. He's doing this again for 60 days. Of course, the number of days when x equals 3. So probably that there's at least 12 days when x was 3. It's a new distribution where he's doing 60 days, and each one has a chance that is like a 15% chance of him getting 3. And now what we want to find is that there are at least 12. So y is greater than equal to 12 given all of those bits. This is good. We get 212. Spot on. Find an estimate for the total number of 6s he'll roll during these 60 days. So, estimate for the total number of 6s. Well, he's going to do 60 days, 10 rolls, a 6th each. So, 100? He's doing 600 rolls, yeah. He should get 100 6s. The way he groups them into days doesn't affect anything. Doesn't change anything at all. That's good. Use a normal approximation to estimate the probability that he rolls a total of more than 95 6s during these 60 days. So, we're going to have some binomial distribution where it's all of the rolls, 600. And he has 1/6 of a chance. That's too big. So we're going to approximate it binomially. This bit is coming from n times p, so it's going to be 100. And then this bit will be 100 over 6. Sorry, 500 over 6. Looking at where they come from, this is n times p, and this is n times p times 1 minus p. So 600 times 1/6, and this is 600 times 1/6 times 5/6. Lovely, that looks good. And now more than 95 sixes. So if we want x to be more than 95, that's a binomial. Sorry, the second one should have been with an n because we have done the approximation. Yeah, that is binomial. So if we kind of draw it out, 95, you can think it's like a region, isn't it? Like anything that's there is 95. Other way around, that should be 94. And that is 96. So this top row would be like the binomial, the discrete version. And let's look at the bottom row with a normal. If we want to say bigger than 95, we actually need to be bigger than this number here, which is 95.5, because everything's going to round up from there. So x being bigger than 95 is the same as y being bigger than 95.5, to make sure that none of the numbers can round to 95. Putting that in the calculator then, just making sure that we're doing it with this version, we get out 0.689. Looks good. Let's keep going. Almost done the flight of birds from his nest, blah, 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 blah. He's got this sort of equation for a regression line. Interpret the regression line. So it's height, yeah, and this is time. So every second, they fall 1.28 meters. Lovely. So they fall 1.28 meters per second. We got PMCC, negative 0.510. Do a hypothesis test. So we're always testing that there's no correlation. Did we spot any difference? Test negative of a negative correlation. So that's going to be negative. Alpha is the 5%. So that's going to go to 0.05. Our observation is negative 0.510. For this then, we go to the... we do something. We go to the book. We had a sample size of... where's our sample size? Am I being really silly? Number 2. Product moment correlation coefficient is this. 10 values. Okay, yeah, 10 values. So sample size 10. We want 5%. So row number 10. 5494. 0.5494. When we look at the numbers and the size of them, so the magnitude, the one from the book was bigger than our observation. So book, and this is your observation, and that was bigger. So what we saw, the thing that we found had some correlation. Randomly, 5% of the time we get this correlation anyway. So what we've seen isn't too extreme, so we're going to not reject H0. Not weird enough. What we've seen is not so strange to change our mind. This is good. Is it going to be an appropriate one? No, so we didn't actually see strong enough correlation. Do you know what I mean? Is what I'm saying. You also just look at this, it doesn't follow a straight line, does it? Like that's clearly like it's not a straight line graph through there. So just say not straight line. Not straight. Linear might be a better word for that. We could then use some like quadratic model. So it obtains this equation. Choose a suitable value for k. Well, this is going to be like completed square form, yeah? So it's going to be the peak. So 3.5. Anywhere from 3 to 4.5. Okay, see the mark there. That all looks good. Let's keep going. Setting the last data set for Perth 2015. We've got temperature. Unfortunately, selected the incorrect variable from the spreadsheet. Incorrect one gave a mean of 5.3, standard deviation of 12.4. What variable could they have been using? rainfall or wind speed. So we'll put rainfall. Calculate the mean. Mean is going to be 2801.2 on 184. What do we get for that? We get 15.2. And then standard deviation, we'll take the big number, 44695.4, divide it by 184, take away the answer we just got, 15.2, but squared, square out that whole thing, and we get the number of 3.34. That looks good. We get some new values for the daily mean air temperature. Give a reason which month, well, these may have come from. So it's in Perth, isn't it? That's Australia. Australia's quite hot, but that's still actually very hot. So we can think about the fact it should be from the summer. Do you know what I mean? The idea it's going to be like it should be from the summer when it's hot. So in Perth, that's actually going to be like winter for England. Do you know what I mean? So it should be from like the closest to December you can get, really. So October for like it's winter in Australia. So sunny. Do you mean sunny? Hot. Lovely. That looks good. Let's keep going. 10% left-handed. We think that if you're under 25, it's different than 10%. Random sample of 40. Okay, do a hypothesis test. So we're going to have some original thought that we have 0.1%. 0.1, just 0.1. So 10%. Our new thought, just different, wasn't it? She just said different. Yeah, different from 10%. So not equal to 0.1. Alpha was 5%, but two-tailed. So we go down to 0.025. X, what we had was, we didn't have one. We're trying to find the critical value. So let's have a look. X can be distributed binomially with a sample size of 40, 10% chance for each one. Let's go and find then probability of some value. So we expect 4 there. So let's actually look at 0. So if I get my calculator, binomial, let it load a little bit. And there we go. So success was 0.1. We're doing 40. And let's try 0 on this first of all. It's a bit of trial and error. You want to find some number that like saddles, what do we call it? In this case, 2.5%. I don't think I can do that. Let's refresh. Type in all my numbers again. It's going very slow, this thing today. So probably success, 0.1. Number of trials is 40, and then let's try 0. What do we get from 0? We get nothing, apparently. So I'm just going to write down the values from the book instead. Is it not going to work at all now? No, not going to do it, is it? So what you want to find, let me draw what's happening. Might be a bit better. Come on. We have some distribution, yeah? And it's binomial, so it's doing something like this. Where this is x, it should go from 0 up to 40. The peak was at 4, 10 times, 40 times 0.1. And what we're going to find basically is like some values here and here, so that each one is 2.5%. And what we say, the first value in that side, so this one will be the critical value. Same this way, critical value there. So we want to find those two values effectively. What do we get? We get the value for 0 is 0.0148, if I can type in 8. And looking the other way around, if we look at above 9, we get that it is 0.0155. So like 1.5% for each, not 2.5. But that's good. That's smaller. What we would show, like what I'd show in the actual exam for my calculator was working, that I'd do the next number, like the one closer to the middle, for both of them, and show that these numbers are like bigger than 0.025, so bigger than 2.5%. Because what that tells us is that like 0, where that blue line, 0 is on one side and 1's on the other. And vice versa up here, 9's on that side, 8's on the other. Like the numbers in between, 2.5% was in between those two values. What that means then, our critical region will either be the 0 the way on the left, or somewhere between 9 and the 40 we were allowed. Yeah, all makes sense. Lovely jubbly. Actual significance level is the area of the blue. So taking these two values, 0.1, that one up there, and this one down here, adding those up to get a value of 0.0303, is it? Yep, 303. That's good. And from here then, just a quick note, you didn't need to put the upper 40 for that one. You'd be fine without it, but like you can see how it is. It is 40. We get 7 as an observation. That's not in our critical region. So 7 is not in the critical region. That tells us we are going to not reject H0. Lovely, looks good. Number 5, is this the last one? No. Nearly. Number 5, we've got height, meters, jumping normally, blah, blah, blah. Okay, so height distributed normally, 1.4, standard deviation of 0.15, which we square in there. We want the probability of height more than 1.6. What that in all the calculators, what we get? 0.0912. We now have time to run 1500 meters, again normally distributed, with 330 and 26. The school's head would like to use these distributions to estimate the proportion of students from the athletics club who can jump higher than 1.6 meters and run 1,500 meters in less than 5 minutes. They have to be independent, yeah, do them both. Independent. So that you can just tie them together. Find their proportion. So we also wanted to run it in less than 5 minutes. So that is 300 seconds. So we want the probability that the time is less than 300. What does that give us? 0.124. So therefore, we want to do 0.124 times by 0.0912 to get a very small value, 0.0113. That's good. I'd assume they're not independent though. If you can run fast, you can probably jump high, can't you? Probably works a little bit together. So now we're doing discus 2. New variable for discus. Okay, we're told these bits. Work them out backwards. So let's go to the inverse. Let's hope this is working. We want to do the inverse normal of those two probabilities, 0.3, and inverse normal of 0.9. Yeah, what that showed is bigger than 29 was 10%, but our inverse normal always does the left. I know my calculator here does the below or above, but generally you're going to want to do the left thing. What's this going to give us then? So we want to be area 0.3, 0.3, and I get a value of negative 0.5244. And for 0.9 then, what do I get? 0.9, 1.28, 1.6. What these are measurements in terms of the standard deviation away from the mean. So if you're at 90%, you are 1.28 standard deviations away from your mean, if you are normally distributed. These then all equal. So in general, we have z, which are like these numbers, equal x minus mu over sigma. The x values we had then, 16.3, so take that away from mu times sigma. And the one underneath, 29, take mu on sigma. So in general, what you're going to see, 29 is equal to mu plus 1.2816 sigma, and 16.3 equals mu, take away that. Take away 0.5244 sigma. So if we take those away from each other, left hand side I am left with not 13 but 12.7. Right hand side, add those up, I'm going to have 1. It's going to be close. 1.2816 plus 0.5244. I get 1.806. Lots of sigma. So it's 12.7 over 1.806. 12.7 divided by that thing is going to be 7.02. That's good. And then we take that back through, find out what the mean's going to be. Rearranging any of these, do you know what I mean? Plug in with the new value. We get the mean of 19.95. So I'd assume 20 was actual value. And we've just done some rounding along the way, haven't we? Is that good? Yes. Yes, it is good. So, last one then. What's going on here? Any two pair of mutually exclusive events, like A and C. Could also have A and D, or B and D. Any two that don't cross over, yeah, no overlaps. B and C are independent. So what we can say, if we work out the area of B, that's going to be 0.32 plus a P times by the area of C. So 0.6, yeah, 0.6. And that will equal the middle, 0.27. So if I divide off by 0.6, I get 0.32 plus P. It's going to be 27 on 60, 9 on 20. So think about that. Is that 0.25? I think it is. 45, sorry. Let's double check. Yep, 0.45. So P is 0.13, yeah. Nope. That's good. Last question, isn't it? So that's good. Greatest possible value of A given B. So that's A intersection not B over not B. B we've just found is 0.45. Yeah. So not B. These should be probabilities of these things. Not B is 0.55. A intersection not B is Q. So that's what we have. Greatest possible value of it. Well, what do we know? We know that the bits left over must, like when we add the whole thing up, it adds up to 1. So let's work out what we have already. This was 0.6, wasn't it? 0.65. Add the 1.3 is 0.78. This is 0.22 at most. Well, these bits add up to 0.22. So this is 0.22 at most. So 2 over 5. That's good. We're told that B, given not A, is 0.5. So B given not A. So B and not A is P plus 0. B given not A. B intersection of B and not A given. Okay, yeah. Okay, I get what's going on. So P is 0.13, 0.27 as well, 0.4. When we think about not A, so that's going to be, we have these bits, Q plus 0.05, but take away those. So 0.0 or 0.95 take away Q. That's equal to 0.5. So what we can say, the bottom must be 0.8. So Q is 0.15. Is that good? That is good. Circle that. They added up to 0.22, didn't they? So P is 0.07. Lovely, that's good. What do we want to do here? So we've got all of this faff. We have an intersection at the end with C, so we only need to consider C. So we can rule out it's not there, not there, not there, not there. And now we need to either be an A, so none of them are going to work. So this is, yeah, intersection of C. Okay, let's think about this bit. A or B? A or B? But we want to not be in that. So rule out any of those bits. What we're left with, just those two. So 0.33. Is that good? Yes. Sounds good. Use set notation to write an expression for the event with probability P. Where was that? It's in the middle, isn't it? So on these, if you're unsure, write the all letters down. A intersection B intersection C. Are we in A? No. Are we in B? Yes. Are we in C? No. Easy peasy. Is that everything? It is. Yep, I've done this already, no. Yep, lovely. Well, thank you ever so much for watching. Hopefully you've enjoyed that. And good luck on paper 3. Evening, mother lovers. So, stats paper from 2025. Let's get going. What have we got then? Bag A has 5 red, 4 yellow, 3 green. Bag B has only got red and yellows. What we're doing? We're taking one from A and then another one from B. We're told here they're getting 2 yellows, so both beads being yellow, 3/16. We're going to find probably of getting a yellow from bag B. So what can we know then? If we get a yellow followed by another yellow, the end of that branch should be 3/16. We can look at top. We've got bag A information. So 4 out of the 12 in total, sorry, 1/3 of them, are going to be yellow originally. So let's just say that we had Y. Let's probably on this one. How do we get down this branch? Well, we timed together to get there. So the third times by the Y should be 3/16. Timed and across by 3 then on both sides. It's not very good. Y. Try again. Will give us 9/16. So that's going to go in that little gap there. Lovely jubbly. Looks good to me. We'll do that bit. Nice. Part 2 of this then is to fill in the rest of the tree. Well, there's only 2 outcomes for bag B. So if we've got 9/16 there, we must have 7/16 on the other one. That will repeat itself then on every single branch, because A and B, like selecting from A, selecting from B, those 2 events were independent. So that means that they don't affect each other. So which one we chose in the first bag didn't change these probabilities from the second bag. Lovely. What are these ones then? Well, it's actually going to be easier. We're probably going to have to time this together, I'm guessing, later on. Yeah, we've been doing stuff with that. So let's make sure all of our probabilities in every row are written with the same denominator. There's actually 12 in this bag, and there 4 of them were yellow. For the red, 5 out of 12, and the green is going to be 3 out of 12. The reason we do that is so now, if we do 12 times 16, we get 192. That's going to be the denominator of every single one over here. So over 192 for all of these. The value that we've got there, that 3/16, let's rewrite that as well as something over 192. What I'll actually do is swap the sides here so everything's matched up. Lovely jubbly. 192 on the bottom then. So that's times by 12 on the bottom. Yeah, it's times by 12 on the top. 36. And now then, to work out the probabilities, we just times the top rows. So 5 times 7, 35. 5 and 9 is 45, yeah. I've got 4 and a 7, 28. 3 and a 7, 21. Add a 3 and a 9 on the bottom there, 27. We can double check that we're correct by adding these all together. 35 plus 45 plus the 28 plus the 36 plus the 21 plus the 27. 192. 192 on the bottom. So that means all of these together sum to 1, which is a good sign and it's correct. If you got that by chance, unlucky. Very unlucky you've got that by chance. Looking at this then, very easy for us to do all these bits of information down here. So exact probability, at least 2 are yellow. So let's look at the branches we're going to get. Anywhere we see a yellow, that branch is successful. So yellow, yellow, yellow on the end. This yellow in bag A leads, therefore, to success as well in every way. So this is also success. So for B, we want to add up all of the branches that contain, well, have those blue circles in the end, yeah? So it's going to be 1 over 192, just to draw this a bit easier. And then what numbers are inside those? 28 plus, 45 for the first one, 28 for the second one. And then a 36, 27 on the end as well. Let's add all those numbers together. What do we get? 45, 28, 36, and 27. 136 on that 192 still. Why this is good as well, it's representing the number of outcomes. 192 is the different possibilities. Do you mean the different arrangement you can get from taking one bag from A and one bag from B? There might be that some of them are actually the same. Do you mean that there are the same arrangements? Depending, like, you take that there's 5 different red beads, do you mean, in bag A? So there's 5 different ones just for like which red one you pick. So some will look the same, but it's like you've actually picked a different bead. Do you mean? So 192 different possibilities if you had different beads for all different colours. 136 of them are going to have at least one of them being yellow. All make sense, yeah? Lovely. So event X is that at least one of the beads is yellow. So that's what we've just found here. Event W, is that a green bead is selected. Where do we have some greens? Let's do a green circle and everything. anywhere we get a green bead. So there's green. Okay, well, that was fun, wasn't it? So we have that one and this one down here. If we again lead into the successes of greens, we want to find a probability that we get a green. I'm going to write underneath that's green, given x, which is yellow. Okay. So probability when we have conditions, we have that formula. What are we going to get? It's the intersection of the two. So W and X, so yellow and green, over the one that must be true, the X. Yellow and green, there's only one possibility in it. I need to go to green and I need to go to yellow. So I've got that 27 on 192. 27 on 192. Divide that by what we have for X, which is just having a single green one in there. You could go and work these out, add these two together, but it's just the same as this branch, isn't it? It should do. Well, it should be exactly the same because these add up to 1. What we're doing to get this stuff is this times this, then this times this. So we could just factorize out, doing cut out the middleman, add these up, and then times by this. Well, these add up to 1, so we do just get this one. Cancel it down, it's 1/4. So we want to figure out what's this going to give us. So 27 on 192. It's like divided by a quarter in it, so it's going to be the same as times them by 4. So it's a 9/16. That looks good. That's a number we've had quite often today, isn't it? So that's, yeah, always a good sign. Lovely. Looks good to me. Next one. What do we have? Runners. What they're doing? Running, probably. He's got 120. That's a lot of them, isn't it? Oh, bloody hell. 40-meter race. Blah, 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 blah. So we have some values for this stuff. What we're doing? Probably mean deviation. Yep. What a surprise. So the mean, how do we do that? X bar. Add them all up. Divide by how many there are. Added them all up. Gave us 6, 6, 1, 2. How many were there? Bloody loads, weren't they? Yeah, 120. So let's do that. What number do we get? 6612 divided by 120 is 55.1. They're moving, mind. They are moving. Give them that. Standard deviation. So sigma is going to be, we want to add up all the squares, divide by how many there are, and then square them in, take it away. That gives us variance. So we square root that thing, and that is the standard deviation. Let's fill in all of our numbers then. It's going to be that big one, isn't it? Oh, look at that. 6. No. Nope. 3, 6, 4, 902. Over how many were? Bloody loads, weren't there? And then we take away the number we just found, 55.1. Give it a square, whack a square root around the whole thing. Let's fill that bad boy in. 364,902 divided by 120. Take away 55.1 squared. Gives me a big old number, doesn't it? Oh, actually quite small, 4.84. Let's square root that afterwards. It seems small already. It's a very small standard deviation. 2.2. The answer being so nice is a good sign, isn't it? 2.2. Lovely. Looks good. Let's circle the other one as well. Beautiful. Let's keep going. The mean and standard deviation for the best times of the 100 runners trained for the 400 meters by Coach B are 55.1, the same, and 3.6 seconds, so more spread out. A 400-meter race consists of equal numbers of the fastest runners trained by Coach A and B. State, given a reason, which coach is more likely to train the winner. Okay, so this is about the spread, yeah? They have the same standard deviation. No, same mean. So when we go to draw them, one of them is going to have that sort of spread. I'll actually draw a bigger line underneath. Oh, come back. We'll get rid of that one. Put a bigger one there. This is obviously time, yeah? Time on that axis. And we have this another distribution with the same mean, whether it's going to be mu or x bar. Well, it should be t bar, shouldn't it? So t bar. The same mean, but different standard deviation. So that means we have less of a spread for one of them. Like one's going to be like shorter, or thinner and taller. So if we think about the best runners, who's the best runners? The people at the very end, yeah? Either way. Running will be faster, so less time. Which one goes further is the red one, the one with the highest standard deviation. So what we can think about is the fact that we want the high standard deviation. Who had that? Was Coach B, won at 3.6. So yeah, more reds. That means we want a higher standard deviation, which implies coach B. Lovely, jubbly. Let's keep going. In the exam, I'd phrase that differently. This is just me explaining it to you. I'd write full sentences like what are you explaining? Do you know what I mean? Put it in words for them. But the general premise is that, isn't it? Like there's people over here that's faster. There's more of them than the blues. So because of that, we pick the red ones. Lovely. Number 3, what have we got? On average, 1.5% are defective. So that's gonna be a probability, surely. And random sample of 36. Okay, so what have we got? Let's say that X is distributed binomially, yeah? We had a sample size, 36. We had a probability, 1.5, so 0.015. Exactly 2 being defective. So the probability that X is equal to 2. Got our calculator on the left here. Let's whack in some values. With my, is it small still? Yep, still small. Okay, right. Probability of success, 0.015. Number of trials, 36. Number of successes is going to be 2. Calculate. We want the exact one, don't we, here? Yes, we do. Top row then. 0.08479. Lovely. More than 3. Okay. So X is greater than 3. Let's do that on here then. So 3. Calculate. X is bigger than 3. That is going to be that 4th value, yeah? So that's going to be 0.00203. That seems very small, doesn't it? But that's not actually too bad. Like, let's just work out the rough, like, expected value we should have. So 36 times that small probability, 0.015, gives me a value of 0.54. So yeah, NP is 0.54. So that's the mean. That's the mean of this thing. Should be that anyway. It's the expected mean. So thinking in that way, getting bigger than 3 when you're expecting 0.51 isn't too bad, really. Do you know what I mean? It's a very small percentage, like 1 in 500, that is, get made this big, which is okay, or like have that high of a percentage. Well, there's that chance. Do you know what I mean? There's a very small 1 in. If you did this 200 times, you'd expect to have 3 components or more than 3 components be defective once. Lovely. Let's keep going. Once every 6 months, the manufacturer tests whether the proportion of defective components has changed. Okay, hypothesis test, yeah. Random sample of 260 is taken, and 8 are found to be defective. So, using a 5% level significance, complete the test. It's a very big sample size. 8 are found to be defective. Yeah, it's a very big sample size. I wonder if we need to do like a continuity correction. Let's have a new distribution. Y, that's going to be distributed binomially. 260. And P is going to be still 0.015. Doing that then, what do we want to find? Well, we're told an observation, weren't we? 8 are found to be defective. Let's have a look at the mean. So the mean of this, that the expected value, we shouldn't really say mean, it is the expected value. It's just that n times p, yeah? N times p. The 260 times the 0.015 we have in there. 260 times 0.015 gives me 3.9. So the 8 that we have is bigger than the mean. If we draw it out, we have our distribution here. Might not be symmetrical, but it doesn't matter too much here. Our expected value, our middle, 3.9. But what we have, bang over there in it, yeah, on the right hand side. So when we're trying to find the probability that we have 8 or something more extreme, we need to be looking bigger than 8. So we want the probability that y is greater than or equal to 8. So let's do that. Number of trials is going to be 260. Probability is the same. Successes now is 8. What do we get? We want to have bigger than or equal to 8. That's the 5th of those ones, yeah, just the one above the mean. So 0.04412. What we're going to do with this is compare it to our significance level. So that tells us, I call it alpha, don't know why, it's going to be 0.05. And that then, yeah, we compare to this number. So we have 0.04 on the left, 0.05 on the right. Which one's bigger? 5's bigger than 4, isn't it? So what this means, the observation that we had, there's a 4.4% chance of that just randomly happening. Our threshold for randomness was 5%. We're saying like, okay, anything that happens, well, it's got more than a 5% chance of happening. We're like, okay, that's acceptable, that's normal. Less than likely, or less than that percentage, we're saying no, too unlikely. So what we really have, this 8 that we've seen over here, there is some zone. If I kind of draw another line there, we don't know what number this is. This is some random number that we're going to call the critical value. Actually, that's the name of it, isn't it? The crit value. And that basically means that this little zone is then 5% of the entire probability, with this side being the other 95. And our 8 sits firmly in this zone. And that's the zone that we're saying, okay, no, we've seen too many defective components for our liking to think that we're still only getting this percentage of them to be, or this proportion of them to be defective. We now think that there's something wrong with it. He's tested either direction, actually, so we've done this slightly wrong. We need to redo it. So we need to redo it. Why do we redo it? Two-tailed, isn't it? So really, this is going to change to 2.5. Everything I did there is correct if it was, if we have one little change. If this said greater than that, he thought there's a higher chance. If he thought his machines were doing worse, do you mean? All that changes now, though, is going to be that this number should be 2.5. And we actually have the same thing on the other side. So bop, 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 bop. That's 2.5%. And when we compared it then, this should have been split up into not 0.05, but 0.025. And that therefore changes the comparison, doesn't it? This is more likely than our actual threshold. Because our threshold got split in two, we're saying there's 5% chance of things that are going to change our mind, but that's 2%, 2.5% on the left, 2.5% on the right. So the 8 we saw actually is okay. It's not past our threshold of like weirdness. It was acceptable. So what does that mean for us? Let's just write down a little note for you to think about in the future. The observation was more likely than our kind of like threshold for weirdness. That's the way I think about it. How weird are you allowing it? I'm allowed to be 2.5% weirdness. As in, like, the smaller you get, the weirder it is. Like, that's how unlikely it's going to be. Only 2.5% times this thing would happen. But what we saw, 4.4%. That's more likely. So, that tells us that we accept H0. Yeah? We haven't seen anything too strange. So, H0 is fine. We've got no reason to doubt ourselves. If this is the other way around, we reject H0. We always commenting on the original thought. That's what we're trying to do. It's basically, this is the first investigation. Like, is it worth us even looking to find out whether we're wrong or not? Now, if we think something's wrong, okay, we'll do this little test first just to see, okay, is our thinking actually valid from the data, or are we just imagining things? If we come back and we reject H0, then we'd go and have a further investigation on H1. But right now, H1 is just kind of a guide for us to be like, okay, how is this bit working? So this bit not equal to tells us it's two-tailed. All making sense, yeah? Lovely. Let's keep going. Number 4. She's doing large data steps. She's doing large data set stuff. Starts with 5th of May. Selects every 10th day after. Name of the sampling technique is systematic in the system. And then nomangematic at the end. Kate wants to find the regression line of Y on X. What's Y? Rainfall. What's X? Sunshine. Using the knowledge of the large data set, explain how K might need to clean these data. I don't know too much about the large data set, but doesn't that have trace in it? So it's like remove trace. I think it's just TR in it, but yeah, remove trace in Y. It's called cleaning the data in it, yeah, that's what they've said. Yeah, clean the data. So the reason why trace is obviously qualitative, it's a word. We really want to have, when we're going to be doing this sort of stuff, and that we want to have numbers to deal with, not words. So it basically just means remove the words, take your words out. Yep, lovely. Use the knowledge. I've got no knowledge, but I can do something else. State the units. Okay, units. Well, rainfall, it's millimeters, isn't it? And we want the gradient, so it is going to be y over x. So it's going to be the y ones, millimeters. Sunshine, is it hours? It might not be hours. Whatever units this is, if I'm wrong here, Jimmy, I don't know the large data set stuff. Let's just double check. What's the large data set for units? Large data set. Edexcel. Sunshine units. What do we get? We get all the large data set. That's what we get. Hours, yeah, obviously hours. So it's going to be millimeters per hour, yeah. Gradient stuff, it's just y over x, dy dx, dy dx. Lovely. Circle these actually. Systematic remove tracing y millimeters per hour. Next one, interpretation of the y-intercept. So that's this one. What that's really saying, well, y is rainfall, x sunshine. The y-intercept, that really means like if x is 0, what's y? So this happens when x is 0. So when if we had no sun, if the sun never rose, what would happen? Well, it would still rain, wouldn't it? Yeah. If the sun rose, it would still bloody rain, wouldn't it? 0.741 millimeters of rain with no sun. Disaster. Yeah, not what we want to see, but yeah, I think that's what it means. Because yeah, if x is 0, then y is going to equal that. So when we have x is 0, no sunshine, we get this much rain. Lovely, jubbly. What's happening next then? Case teacher is claiming, well, she's claimed already, that the greater the amount of sunshine in a day, the lower the amount of rainfall. That's not what we've seen, is it? No, we've seen a positive correlation. Okay, state given a reason whether she's true or not. No, no, you're lying. Oh, you're chatting out your ass, aren't you? You don't know what's going on. So, what's our reason? Yeah, we've got positive gradient. Positive gradient. That's going to imply a positive correlation. Lovely, looks good. The teacher used all the data for these variables from the large data set from Leeming in 2015 as a sample. We've got the PMCC, negative 0.160. In a suitable test, blah, 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 p-value 0.015. Using 5%, state the hypotheses and conclusion for this test. So, hypotheses, let's get a null. Let's get an alternate. What they're actually trying to do, teachers claim, that's what our hypotheses are always about. Teachers claimed that the greater amount of sunshine in a day, the lower amount of rain there should be. So she's making a claim about the correlation, isn't she? That it's going to be positive. Our hypothesis is always that there's no correlation. Looks good to me. And conclusion then, what's going to happen? Are we going to reject H0? Well, we have, what do we have? Let's circle our numbers to make it a bit clearer. This value and this value. We get, and the 5%. This number has been used to calculate this number alongside the sample. So this number and the sample size has been used to calculate this number. So what this represents is the random chance again, 1.5% chance of any two bits of data, any two random variables having a correlation of 0.160, whether it's positive or negative, doesn't matter. But there's less, 1.5% chance of it being that just randomly. Our threshold for randomness was 5% again. So it's the same thing, yeah? It's the same things happening. Same things happening, but now we've got one-tailed because she has stressed it's positive. Let's actually draw it out here again. Yeah, one-tailed because it's positive. This is representing our correlation. Something like this, always centered on 0 for correlation. We're looking to the right, looking positive, and we're told that we have 5% significance level. So we can draw some line there. This is going to be 5%. This again, this is our critical value. Crit value. And what we're told is that our thing had 1.5% chance. So we are, when we go over it, we're well in this zone, yeah? We're sitting here somewhere. That's us. Does it say anything about the number? That's negative. Well, it's going to be on the other direction. 1.60. Am I being silly about this one? I am, aren't I? Yeah, sorry, lower. She's saying negative correlation, she. So I need to draw my graph the other way around. let's just, well, what we can do, sneaky. Whoop. Move you over, move you over, move you over. Steal you. Rub you out. Bop, 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 bop. And then put you on this side. Sounds good. Maybe that arrow needs to be a bit better. And then that can go there like that. And you can move over to there. Looks good, doesn't it? Yep, looks good to me. So what were we doing? Yeah, which again, same thing happens just the other way around. This is negative, isn't it? It's negative. Let's fill that in. Lovely. We got though 1.5% chance. That's what we're being told there. So our green line, if you have like a little green zone at this end as well, the green zone is much smaller. That's only 1.5%. So what we've observed, very unlikely. Our threshold for weirdness is quite high. We're even weirder than our threshold. So again, we're going to reject H0 and have a further investigation into the teacher's claim, which does make sense. I don't think K's got. I think K's mad. Do you mean more rain, more sun? No, not at the same time. One or the other, isn't it? Really, kind of by definition. Like what you need for this, you need the opposite for it. Like it stops this. So it should be that it goes the other way around. It should be a negative correlation. Yeah. Describe a sample. It was only from the dataset when Leeming, 2015. Yeah, it's just all the data from Leeming 2015, is it? I don't think she's done anything less than that. Claiming about stuff. Use all the data from, yeah, she's used the data from all the data for these variables from the large dataset for Leeming in 2015. So that's our sample. Leeming 2015. Again, I would use a full sentence in the exam. Possible population, we could just do like Leeming in the whole century, 21st century. You could do that, do you mean? Even that hasn't happened yet, that could be in the future. Doesn't say anything about the time that's going to happen. If you want to get a little bit more technical, you could rewrite that as like the 2010s. So like 2010 to 2019 inclusive, just to make sure we know we include them all. And yeah, that looks good to me. Population, like, yeah, it means all of them, but it depends on your viewpoint. Like, there's a population of your school, isn't there? There's how many people go to your school. That's not the population of the country or the world. So population is always kind of dependent on the context. So like, what's a sample? What's a population? A survey? No difference really. It's just the size. Are we talking about everyone that we could possibly ask, or are we not? If we are, census. If we're not, sample. Lovely. Number 5 then is the last one. No, it's not. So penultimate one. What have we got? Height of men in a tennis club are normally distributed with a mean of 183. The H distributed normally 183. Deviation 4.9. So that goes in there with a little square. Find the probability that the man's height is more than 186. So H more than 186. What are we going to get? Let's fill in our thing. We need to change our calculator though over to the normal one. Normal distribution up on the top right. Zoom in a bit. Oh, just let it do itself. Change some of these numbers. What do we need now? Move it out of the way. The mean 183. Standard deviation 4.9. We want to be more than, so above 186. Above. Calculate. Is that doing? I'm assuming that's changed. Yeah. Okay. What we got? 0.2702. Don't trust that for some reason. And now next one, between 175 and 185. So I can do that. Between. Move you down a bit. Or over there. 175 and 185. Calculate that. What do we get? About 60%. 0.6072. Do those numbers seem sensible? Well, average height is 183, yeah? This is a 6 centimeters off. And yeah, that looks about good. 1/4 of the people are an inch, about an inch in it. So this is 6 foot-ish. This is 6'1"-ish. Quarter of the people are more than 6 foot. 6'1". Yeah, that seems to match up. How many people are between, what's this going to be, like 5'9", 5'10", and 6'1"? 60%. Yep, these make sense. Looks good. Always do like a little sanity check. The numbers you get out should seem realistic. In stats, the numbers are going to come from something sensible. because that's the whole point of stats as well. It's like, does this make sense? Like, no. Okay, what have we done wrong? Or like, why is that happening? Investigate it further. Right, let's keep going. We got women now. They're playing tennis too. We got a mean of mu, standard deviation of sigma. 40% are shorter than 170, and 15% are taller than 175. Ooh, find these bits. Okay, so let's have height of women. So height of women. This can go up here now. Then it'll be height of man everywhere. Height of man. Height of man. We'll make the woman look more like a woman. Well, it's not a woman, is it? It's a W. But still, there we go. We don't want that. We want it to be distributed normally with a mean of mu and a standard deviation of sigma. Well, yeah, variance of sigma squared. So, what information are we given? Probability that we are shorter than 170. So the height of women being less than 170 is 40%, so 0.4. And we're also told that the height of the women being taller than 175, that is 15%, 0.15. I wrote that as 40. So let's visualize this, make it a bit easier for us. We have the height of women along there. We're going to have our distribution normal again, so doing something like that. Make it a bit bigger, easier to see. Looks good. And we're going to have some numbers. So bigger than 175, let's put that like here, 15%. So that is that 15% in there. And the smaller 170 is 40%. So about there maybe. So that's going to be 40%. That number was 170. This was 175. And now then, we just want to find out where is our mean going to be and how big is our standard deviation. This works in not too bad of a way. It is simultaneous equations in disguise. We're going to use the standard normal. So just a notation, if you're not sure how this works, we have that the standard normal is always written with a Z. Well, like it's just usually written with a Z. I don't think it has to be. Written with a Z. And it's going to be distributed normally with a mean of 0, standard deviation of 1, and variance of 1. That's why it's called the standard normal. Standard in math just means that you've scaled it down to a size of 1, generally, either that or unit, but like you can kind of standardize something, do you mean? Or normalize as well as a word for that. But they've already used the word normal for the distribution. It couldn't be like a normal. It is the normal. Is like probably a correct way of saying it, but standard normal is what we use instead. And we have then a little notation of phi. I think this is phi, and that's the name of it, of z. And this is going to be little z because that's going to be one output. This is the actual kind of distribution. This is going to be one element of that, one value of that. So phi of little z is just a shorthand of us finding, it's like the CDF basically, our distribution being less than that value. So just to clarify, drawing that out again, will be the same sort of shape distribution. I'm trying to do a better curve again. I'm actually going to steal that one. That was a good one. Let's take that. Oh yeah, look, lovely. Color it in though. Blue. Yeah, looks good. So I don't know where Z is, little z, but what we can do is we can just put it on there and say that that is just that. Do you mean it's just that area? That's what it's representing. This is going to be little z. We have our peak of the distribution is at 0, and this is little z. So just a shorthand like notation we're writing that with. The reason we want to use that, it's just a transformation. This is what this standard normal does. It's a way of representing every single distribution you can have in a format like that. You can just transform between the two. When I say transform, I mean literally like transformations at GCSE, translations and rotations and enlargements, that sort of stuff. This is just a translation and an enlargement. So what we're going to have, the value for z, this is true for big Z and little z. It's basically a coding. Do you mean z? I do without that one. Is x minus mu on sigma. So that's true for little z as well, and little x. So it's just saying like this is kind of the general description of the coding of the entire distributions. This then is for the individual coding for one of the variables inside it. So let's think how to use this then, because we have this to be true. So if we can then like inverse that, we have that z is going to equal to the inverse standard normal of like the probability of being in a random thing. So this is just going to be some probability, yeah? I'm actually going to write it a bit neater, and we'll just write it as like P of little z. Yeah, P of little z, which is the things given to us. There, these bits, that's what that represents. Once we have, like, it's still the same probability, we can then set this equal to this thing. So just to explain, once we filled all this in, doing that for these actual values, then we're going to go and have a look on our inverse normal calculator. So we have, for the inverse normal that's standard, it's going to be 0 and 1. If you have a calculator that can do the other bits, just do the other bits, because you can just put in the values and you'll do that, and it will give you the actual values out in a second. I'll show you once we've done this version. So area we want on the first one, 0.4, and we want to be below that. So when we do this, we get that z value. So we can see, if I get a little line here doing the right hand side, that we have inverse phi of the 0.4 is negative 0.2533. This is a measure in standard deviations away from the mean. So 40% is 10% away from the mean, yeah? 50% mean, 10% away, is actually a quarter of a standard deviation. So we've got that one value. That turns into a equation using this thing. So z is equal to that. Z is going to be this number. That is z. So we can start filling this stuff in. This should equal, let's move it over a little bit. Yeah, this thing, the negative 0.2533, will equal x, the 170 inside, minus mu over sigma. So we can times by that sigma and have effectively that 170 minus mu is equal to minus 0.2533 sigma. Yep, lovely. Similar thing then for the other one. You can see where the kind of numbers end up being. We have 175 in there, minus mu is equal to some amount of sigma. And to do that then, all we need to change is this number becomes 0.15, and we change this to be above. So if you do it below, it's just the negative of it, yeah, symmetrical. So 1.0364 looks good to me. From here then, what do we need to do? Well, simultaneous equations. I've got so many mu's, so many sigmas. Let us subtract them from each other. So if I do that, I'll do bottom take top. Let me actually write these upside down just to make it easy to do that subtraction. So move you down, move you down, move you up. So yeah, now doing top take bottom. Left hand side is 5. Just 5. Just 5. And then this thing, take away a negative, is like adding it. So 1.0364 plus 0.25. I'm assuming there's still 3s, who knows? Who knows my writing? What do we get? I'm going to get a number of 1.2897. Lots of sigma. So that means sigma should be 5 divided by that big number. 5 divided by all those decimals, we get, let's write it first. So 5 divided by 1.2897 is going to be 3.877. Yep, that's good for sigma. Take that value then, plug it back into here, work out what mu is going to be. So if you think about that, add this over, take this away. Mu is 175, take away 1.0364 times by that number we just found, 3.877. 175, take away 1.0364 times by 3.877 is equal to 170.98. Yep. Does that sound good? Well, let's look. Does it fit into what we've talked about, what we've discussed? Yeah, it's in between there. It had to be, didn't it? So we can put it kind of like in that region. Yeah, it's in there, isn't it? 171, pretty much. Imagine it actually is 171, the value they've used. We might have rounded some things along the way, not get exact values out. Do you mean? Stats isn't an exact science. it's a little bit wishy-washy, it's a little bit subjective, a little bit, oh, okay, we'll try this, see what it looks like, what actually works, what's easy to do. Yeah, that looks good to me. Find out, we've got these values. Next bit then, probably that both players, or we've got a man and a woman, okay, both of them between 175 and 170. So I will just go above for this. We've got a lot of little notes down there. Let's just move this out of the way, maybe. That's notes about this. Can I move? Yeah, okay, I'll do this. Move you down ever so slightly, and you can slide in the top. Right, got some space. What are we saying? We have a man and a woman, and heights between 170 and 175. So we could write down a lot of bits, yeah? These are independent. They're not affecting each other, are they? If I come in and I'm very tall and then someone else walks in and they're very short, it's not because I was tall. That's not why they're short, do you mean? Or vice versa. Doesn't make a difference. Unless they're related, but like, we don't know that. These are just people playing tennis. So we can just times the two together. We want to work out the probability that we have 170 being less than the height of a woman, and that being less than 175. So a woman being between those heights. And then we'll times it by the same for a man. I'm just going to copy this over, duplicate, change that W for a M, if this will stop moving. Lovely. Where are we going to get this from? I don't know. Well, I do know. That's what I mean when I just show you. We get it from the calculator on the left. What is it, though? It is normals, isn't it? Are we on normal? We are on inverse normal. Let's go to forward normal. Come on, yeah. What was our values again? So for the men, we have 183. Oh no, we'll do the women first on the left. Women, we've just worked those out, haven't we? That's what we've just worked out. So the mean, 171, we'll call that, yeah. The numbers might be slightly different than the actual mark scheme, slightly different than the rounding, but 171's fine, isn't it? The method's really what you need to learn. 3.877 for that standard deviation. And we wanted between 170 and 175. Calculate. I get, what's that, 0.45. So let's fill that in. 0.4507 times that then by the, what do we call it? One for the men. Same range, isn't it? 70 to 175. Well, 170 to 175. The men, though, a little bit taller, aren't they? Only ever so slightly. 183. Deviation 4.9. Bigger range as well. That bit of spread. What's that give us? Oh, very small. That's going to be 0.0473. So let's get our calculators. Times those two numbers together. 0.4507 times by 0.0473. I'm getting a very small number, but this seems kind of normal. 0.0213. So 2% chance. If I go to a tennis club, yeah, tennis, they're giants, aren't they? Tennis players. They are really, aren't they? They're like a whole region of Dutch people, but just like all collated into one club. And we're saying that if we have a man and a woman, then both being, this isn't that tall. This is what, 5'7", 5'8", 5'9", something like that. Man and a woman both being between that height. Woman, yeah. Man, nah. But so both together, nah. Looks good, yeah. Yeah. Last one then. What have we got? Sum discrete random variable goes from 2 to 2n. Let's go by this thing. Okay, show that this is a constant. So in this one, it's always the same idea. Add up to 1, yeah? Let's add these all up. What numbers are we going to get? Well, everything's got over k. So I'll just factor that out straight away. Why not? What's left over is r. That's all these values. Let's just add all those up then. 2 plus a 4 plus a something, something, something plus a 2n equals 1. Got 2's everywhere. Take one of those out. Take 2 over k. What we're left with? 1 plus 2 plus blah, 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 plus an n. That still equals 1. I will move this over for the next step. How do we rewrite this? Well, it's n plus 1 over, and then all over 2. Times in that 2 over k. We'll make a k over 2 over there. We can then divide those 2's off. And I think we have the answer, don't we? K is n plus 1. Yep, lovely. Looks good. When n is 20. So what does that tell us about k? Do we need to know? Maybe, but worth writing down in it. It's 420. Find the exact value of r being between 16 and 26, but it can be 16. That you don't have any formulas for this sort of stuff, yeah? You've got no, like, this is just, it's weird, isn't it? Weird, yeah? I think it's weird. You think it's weird. Everyone thinks it's weird. So, you do weird things as well. What numbers are these? 16, 18, 20, 22, and 24. 26 is no. 14 is no to the other end. They're the only ones available to us. And we know we work out them individually by doing this sort of formula. They're independent. They're not going to affect each other, yeah? We're only picking one, so like they can't affect each other anyway. So what we want to do is add up those numbers and then divide it by k. Because if you think about it, like each one would have over k, over k, over k. So again, just factorizing it out. Same idea we've been doing up there. Adding all this up, what do we get? Well, the middle one's 20. These are equally spaced, symmetrical distributions, every 2 in it. So it's 5 times 20, 100. So the value should be 100 over k, whatever that is. I will plug in, obviously, the value for k. K was 420, wasn't it? So it's going to be 10 on 42. Well, we'll do it like this, 100 over 420. 10 on 42, 5 on 21. Seems good. It's a number they use quite a lot in these past papers. I haven't got the mark scheme for this. So I don't know if I'm right on these numbers. The method should all be fine, yeah? For the whole thing, method should be fine. Numbers might well be slightly wrong somewhere along the way. So n still 20. Random variable g of r is taken. Quadratic equation in this. Find the exact probability that the equation has no real roots. Okay, well, how does that work? We need to first of all make this into an actual quadratic where we have 0 on the other side. So we're going to subtract the 3g, no, we're going to leave the 3g alone. And we're going to take away a 5. This then, whole in the end, that is like our plus c. So when we have no real roots, that tells us our discriminant is 0. So, no, not 0, sorry, less than 0. Because when we look at the quadratic formula, we end up square rooting that thing, but we can't square root negatives. Not allowed to keep real roots. So what do we want to find? The discriminant itself is going to be b squared, which is just g, so g squared, plus or minus, no, that's the bit outside it. The discriminant, no, what am I doing? Minus 4 times a. I shouldn't have the x in the middle. That's what's bamboozling me. There we go. Right, that's better, isn't it? Yeah. Yeah? No. What am I doing? Okay. This is a quadratic. Let's rewrite it equal to 0. X squared plus gx plus 3g minus 5 equals 0. I was half a step ahead. Do you mean in my head? This we want to do the discriminant of. This thing's fine. Yeah, discriminant is negative. So what's the discriminant of this? B squared is g, so g squared. Well, b is g, so g squared. Minus 4 times a of 1 times c of all that stuff in the end. Yeah, 3g minus 5. Okay, lovely. So we know g squared minus that stuff. I'll expand the brackets out. I get 12g plus a 20. That needs to be negative. Factorizing it, I get a minus 10 and a minus 2. Yeah, looks good. Yeah, looks good. And just for those that aren't sure on how to do this stuff when it's a quadratic, if we were just to plot this very quickly, doesn't need to be too good. It's a smiley graph, yeah, positive 1, so smiley. So that's going to be a 2. That's going to be a 10. So we're going to be beneath the curve, beneath 0, yeah. So we need to be underneath. So rephrase that, underneath the curve, so beneath these two numbers. So less than the 10, bigger than the 2. This one we're just looking them up, aren't we? So that's the same as g either being 4, 6, or 8. And here, add those all up, we get 18. So our probability should be 18 over k, which is 18 on 420. So let's do a division on that. 9 on 210, divide them all by 3. Is it 3 on 70? I will double check with the calculator. 18 on 420. 3 on 70. That looks good for me, ladies and gentlemen. Thank you ever so much for watching. Hope you've enjoyed that. I will see you soon.